Alright, hell yeah. So we have JEE Advanced. This is 2016. This is paper number 2. You can look this up. This is the PDF. Sorry it's a little bit grainy. But this is 2 discs, and they're slanted, and they're very lightweight. Well, you know, they're very thin. And then they're on a rod. And even here, you know what I mean? I made the mistake. Even it looks like it's connected. You know, I thought the rod was just all the way through. But no, the rod is just here. This just gives you some perspective that as this thing is rolling, you know, just by its own nature, it's going to spin a circle. So if we have a top-down view, you know, I mean, this thing's going in a circle. Here's the center. Maybe here's the outside wheel, and then here's that inside wheel. And they're slanted, so the wheels are going to look like this. You know what I mean? So that's kind of a hey, that's a pretty decent view, I guess. So anyway, and this one's definitely a little bit bigger of a wheel. Okay, so you know, obviously, if you got this in a test, the only way that you're going to be able to solve this in the test, you know, situation, it talks about angular momentum. So you have 3 problems. It's multiple choice. Let's talk about the multiple choice part first. You know what I mean? It says, hey, look at this. The angular momentum about the center of mass. Cool. The angular momentum about this axis. And then 3 is the angular momentum about point O. You know what I mean? So 3 questions involve angular momentum. You know what I mean? And so we have an equation for angular momentum. And we'll get to that probably a lot later. You know what I mean? It's the distance from whatever axis or point, you know what I mean, you're going from. And it is a vector, you know what I mean? That's because we're not just going to be like linearly across, you know, we're going to be, you know, we have a vector towards that direction. But anyway, it's just the cross product between just normal momentum. You know what I mean? Just hey, some sort of mass out here is moving that way. Hey, this is rolling, so some sort of mass right here is totally stationary. You know what I mean? We know some things about wheels that the contact point of a wheel is not moving. You know what I mean? But hey, this point is moving twice. It's moving hella, and then obviously the center of mass is just kind of, you know, moving tangentially as we would probably see it. Just like a car going down the road. Yeah, let's talk about that. So a car going down the road, you see it going like, hey, that fast, right? But the contact points of the wheel are not moving. And then so the tops of the wheel, I don't know, it'd be kind of interesting, like watching a car kind of go slowly. Just like, you know what I mean? Especially just watch the tops of the wheel. I'm going to do that next time. I'm going to watch the tops of the wheel and see if I can visually see that the tops of the wheels, you know, look like they're going twice the actual velocity of the car. I don't even know mentally if you could, you know, visualize that. Anyway, so but angular momentum, we'll get to it a lot later, because what we're just going to do is just solve the problem D and call this part 1. You know what I mean? Well, we're going to throw in the towel. We'd see this and be like, nah, thanks, we failed. You know what I mean? And we wasn't ready for it on a test. But anyway, so angular momentum is just mass. So it's the distance crossed with momentum. You know what I mean? So sometimes you see it as is just R cross P. You know what I mean? And that probably doesn't do it justice, because unless you've done a hell of a lot of momentum problems and you're calling this P, you know what I mean? You know, just write it as mass times velocity. And you know, I really want to solve about 20 different problems before ever doing this one. Like, you know, just even a wheel rolling down an incline. You know what I mean? I want to do a problem related to the momentum of that and how that's related to F equals ma. Because if I can't do a problem and relate it to F equals ma, you know what I mean? It's not my style. You know what I mean? But and every problem can be related to F equals ma. We just have a lot of shortcuts. Just as energy is, you know, potential energy is mgh, you know what I mean, like where that comes from, kinetic energy 1/2 mv squared. Well, same thing with like momentum. You have like moment of inertia. We've talked about that in other videos. But yeah, let's spend about 1 more minute talking about momentum and then just move on to this this part D problem. Okay, but what we do see on this momentum term is we have a distance to some sort of mass and it has velocity. So I think we can all see if this thing's going around the circle, that even we'll just pick the center right there. And let's just say, hey, this whole disc weighs 4 meters. Let's just say for whatever reason, this very center of it is 4m. I mean, so they're not even saying, you know, this problem is all in letters anyway. But let's say the whole disc weighs 4 kilograms, and we're just gonna choose like the center. You can just imagine maybe weighs 1 kilogram, and then I know this center has some sort of movement. You know, it has some sort of tangential velocity. And in this problem, hell, at least we know the angular speed. You know what I mean? So that's going to be this omega term, and it just says so. It just says, hey, it's actually rolling around in a circle with a constant angular speed. You know what I mean? So yeah, and that's the omega. So if that's the case, then this chunk of mass has some sort of tangential velocity, just like we're on the surface of the Earth. Well, if you're on the North Pole, you're just spinning around in a circle. You're not flying around. If you're at the equator, oh hell yeah, hang on for the ride. You know what I mean? You're going 1,000 miles per hour, and you can kind of figure that because you got 24 hours in a day, and each time zone is about 1,000 miles. You know what I mean? So think about that. Every time zone you drive through, if you live in a big country, or whatever, if you get to drive across a big landmass, about 1,000 miles gets you into the new time zone. So that means you're going 1,000 miles per hour. You know what I mean? And this is going to vary. I live up in Montana. We're 45 degrees. You know what I mean? So we're only going 750 miles an hour, maybe. So anyway, but we have this understanding of at least tangential velocity. That's why we're just gonna do this problem D and just choose the easy fruit. You know what I mean? Because and we'll see. You know, we'll see if this is a 10-hour problem just for me to just like, hey, because we're gonna take something complex and at least see if we can make it basic. And maybe we can. And, you know, and in a couple hours, maybe we can turn this into something basic and chisel out some sort of numbers that are representative or close to these. Okay, wait, let's focus. So I want to get back to momentum. We'll talk about it for another 5 minutes, and then we'll get on to the easy stuff. So yeah, you can envision that we have like maybe 1 kilogram and it's going that way. Cool. That is the definition of this term. You've picked out that you have 1 kilogram and it has a velocity. You know what I mean? And I don't even know what this distance is. Well, let's just say this is 1 meter and this is 1 meter. And let's say the angular speed is just 1 radian per second. You know, you get to choose this. So we have a radius of 2, and I'm just going to say, if you ever have radians, you know, I do this a lot, radians per second. If you have radians per second, no one knows what that is. But if you multiply by the radius, you get something normal, and for our problem, that's tangential velocity. So we're going to say 1 radian per second times 2 meters. That's going to be 2 meters per second. So now we have this idea that we have 1 kilogram going 2 meters per second. Cool. So that's this part. You know what I mean? So I guess let's spell it out. So angular momentum is going to be the distance to that. And then let's say we are going about the z-axis right here. So we're just going to go all the way over to that 1 kilogram. So it took 2 meters to do that. And then we're going to multiply by that 1 kilogram mass. So we have 1 kilogram, and we need to know its velocity. Well, that's going to be that 1 radian per second times 2 meters. So cool. Radians is dimensionless. This is going to be meters per second. This is going to give us our velocity. And again, this was angular velocity times radius, and this gives us our tangential velocity. This was the mass, and this was that R term, R crossed momentum, R crossed MV. You know what I mean? So, you know what I mean? This is just a useful term, and I guess I'm not going to get into it right now. But yeah, sometimes, hey, angular momentum is conserved. And even that one, it took me the last couple weeks to think about that. And I was just like, well, what are the scenarios where that's useful? Because a lot of time, angular momentum isn't conserved. And And there's some interesting problems. Yeah, the problem that messed me up was just like, hey, you have a sliding block, and it hits a little curb. And the second it hits that curb, it hits that curb, it starts to rotate up. And, it starts to, it starts to rotate with an omega. And then there was a way to say angular momentum is conserved. But it's just like, it doesn't look like it's conserved. And holy hell, I might even be spouting something that's totally nonsense. That's the idea. It's like, I don't want to tackle this problem until I get a sense of like what angular momentum is. That's the first three. You know what I mean? The second one just says, hey, the center of mass of the assembly rotates about the z-axis with an angular speed of omega divided by 5. So we're slowly getting to that one. Well, I don't know, choose the center of mass right there, and then it's going to be going around. But it doesn't really matter, if this is going around in a circle, as some sort of, it wouldn't matter if this point out here or this point right here, that's going to be going the same angular speed. You know what I mean? So if I say the angular speed is just omega divided by 5, you know what I mean? Or just 1 radian per second, the angular speed of this point is the same thing as that point. Like this rod is moving around the circle constantly. Now the wheels. The wheels are spinning, so they're going to be different. But yeah, so every point along this rod is going to be the same. So we'll get to that one. Okay, but in this problem, this one messed me up because it's just like, and I might be saying this wrong. But when this block hits a curb, it puts a hell of a force right on the corner. But we're treating this as a hinge, I still don't see it. But angular momentum is conserved if there's no torques. So if I do a free body diagram, just with an object in outer space, I'm just going to give it some downward velocity. You know what I mean? And then what I'm going to do is I'm going to put a force just right on the corner. Well, I would say I generate a torque on that. You know what I mean? It seems to me that I would. So anyway, so I think I'm gonna throw in the towel. You know what I mean? But we're gonna come back to that one. Okay, so what we're gonna do now is we have, well, let's talk about angular momentum one more time. And then this is always good because we talk about, the wrench. I bring this one up quite a bit, is that if I have a wrench, I'm going to put a force over here, and then it's going to be some distance away. And this is going to be very useful. Like, this is the only way to actually wrench on something. You know what I mean? Put a force at a distance, and if it's perpendicular, hell yeah, you get a wrenching action. You know what I mean? We're going to be turning this thing that way. Okay, so now, and this is the definition of torque. So we say torque, for our purpose, is just, F times D. But if you write it like torque is equal to D times F, and then if you write it like torque is equal to D cross F, and then you can see that this is just a general, radius from the center. Now we have torque is equal to R cross F. And in general, this is what we call a moment. You know what I mean? This is a moment of force. So we have moment of force. We have some sort of force, and it's a distance away. That's it. That's all moment of forces. It's like, hey, we've identified a force, and guess what? It's a distance away from some point, and that's going to give us a value. And in this case, it gives us, well, if we're at perpendicular angles, because if we're just trying to find the scalar component of this, it's just going to be R times F if we're at a 90-degree angle. And so that means that we have sine of the angle. So if the sine of the angle is 90, sine of 90, hell yeah, that's going to be 1. And then we're just going to have that distance r times F, and that's going to be the torque. Now, what would happen if this angle was 0? Well, if this was the case, if we just have, if we bring this angle, let's say this is our angle theta, and we bring this all the way to 0, well, now we just have the force in line with, like, obviously we're not wrenching no more, you know what I mean? So if we're saying torque is a wrenching motion that needs a force, some sort of force, at least not in line with the hinge, you know what I mean? So in this case, we would have R times F sine of 0 degrees. And if we put the force this way, we open up the angle to 180 degrees. Same thing, we have R times F sine of 180. And we know sine of 180 is 0, sine of 0 is 0. So then we would have 0 torque. And then so for our problem, we're going to have, because then if we ever got like a wrench problem where it's just like, hey, let's like, what type of angle should we do? Should we do, hey, maybe we're trying to wrench on this like normal, but we just can't really get, like, all we can do is pull. And we're going to say we're pulling at a 60-degree angle. You know what I mean? So now my force is this way. And then we're going to compare that to pulling on this wrench at a 30-degree angle. You know what I mean? So this way. If the angle is 30, and that's just a little bit less than 30, but there you go. So let's say, so we have a 30 degrees and 60 degrees. Well, now, because what we want to do to this problem is just really simplify it and say, who cares? You know what I mean? If we can say, like, who cares, and then, who cares that these things are slanted? You know what I mean? Hey, let's just make them horizontal, and then put the ground down here, and then we have one disc there, and then put another. You know what I mean? Maybe this is just a terraced table. Like this part's higher, and then we step down to a lower part, and that's part lower. And then, you know what I mean? So there you go. We just got rid of like that. And this looks like a pretty shallow angle. So in our problem, if theta is 60, well, we said it needs to be 90. You know what I mean? So that's what we're shooting for to torque a wrench. But if we're measuring from here, 60-degree angle is, you know what I mean? It's kind of like measuring from here. If we say this is an angle of 30, it's just like, well, well, I guess not. Let's stick with 60, because one of the axioms that I use all the time is, like, if you're doing something at like a 60-degree angle, it's pretty much identical that you're just doing that same thing at a 90. You know what I mean? So if I have a force of 100 pounds that I'm pulling at a 60-degree angle for this problem, I would just bring it up to perpendicular and say, hell yeah, that force is 100 pounds. And if you do the sine and cosine, you know what I mean, jazz, hey, this force is it's 86.6%. That's going to be, because if here's my angle and I need the vertical component, hey, the sun is shining on the sine, so it is the sining component. It would be sine 60, and sine 60 is 0.866. That means 86.6%. And we do this a lot with sines and cosines. They're just numbers between 0 and 1, and they're fractions. So they're like 0.5, 0.866. Halfway is 75, is 0.707. You know what I mean? And so those are the three that I would definitely memorize to 3 digits. Sine of 45 or cosine 45 is 0.707. Sine 60 is 0.866. It's 86.6%. But it's just like, the who cares is just like, call it full. Call it 100% and just get on with life. And then so there you go. So if we have an angle of 60, we're just going to call that 100. Now, if we have over here an angle of 30, if we're saying we're pulling 100 pounds and we're trying to wrench on this bolt, well, hell no. You know what I mean? You're not 100% at all, and we know that the sine of 30 is 0.5. So really, the only component, the component this way of it, you know what I mean? the force in the X is only going to be 50 pounds. So this is only going to torque 50. So if we go back to our problem, for this one it's going to be R times F and then sine 30. And we're just going to say, hey, that's 0.5 or 50%. So we only have 50, so we have 0.5 times RF for that one. Now this one, true to spirit, it's RF sine 60. That's going to be 0.866 RF. But you could just say it's pretty much just RF. You know what I mean? Hey, good enough job. You're just off by a small angle. Alright, hell yeah. So yeah, I have no idea if I'm going to do this one in, you know, multiple parts, you know, break it up. Obviously, we haven't got to question D yet, because, I mean, this problem centers around this idea of angular momentum. And we just came up with one scenario that it's actually, so if you're getting your car changed and you're just like, ask the mechanic, is just like, yeah, how many, what torque did you torque the bolts? And they said 100 pound-feet, you know what I mean? So they have a torque wrench that's 1 foot long, and then they're reefing on it with 100 pounds. Now obviously torque wrenches, you know, aren't they? They're longer, you know what I mean? And then so you're gonna put, you know, you're gonna get that though. You're gonna get the 100 pounds pound-feet, and yeah. And that's why also torque wrenches kind of have handles that swivel, so you want to make sure the handle is balanced, so then you're putting a perpendicular force. That forces you or challenges you to put that perpendicular force on, and you're not just turning this handle to where, you know, you're reefing down at those 60-degree angles. But we just said it's like you can't be too far off if your angle is just a little bit sloppy when pulling. It's not that big of a deal. Okay, so now what we're gonna do is so yeah, did we cover at least like how angular momentum? I mean, we really haven't covered like why angular momentum is useful, and I think that would be a very critical part of doing this problem. You know what I mean? Else it's just like a math problem where you're just like, okay, I've used numbers before, and then someone gives me a challenging number problem to do, and then I figure out how to do it, but I have no idea what its useful application is. You know what I mean? So you could tackle this one that way, but probably not. That's the cool thing about physics problems, is they have some sort of underlying meaning behind them, and one of that aspects is this idea. Let's get into it. Let's stick with angular momentum. Talk about the theory of momentum, and then we'll at least set the goal to at least tackle this easy part. But let's talk about multiple choice. You know, we've already said it's just like there's no, this problem is 4 problems. I would not treat a multiple choice problem like it's just like, oh, just try to pick the ones, because it says, hey, which of the following are true? They might be all true, or 1 might be true and 3 might, you know, there's so many combinations. So you have to just treat it like 4 problems. Like, hey, find the angular momentum about the center of mass, and then get a number on that. And if it's not the same, then that one's not true. If it's the same, it's true. That's what we're shooting for. Find the z component of the angular. Find the angular momentum about the z-axis. Actually, I don't even know if that's the same. The z component of the angular momentum. I would imagine that's the angular momentum about the z-axis. I'm not quite sure. Oh yeah. So we can talk more about this wrench because we have just talked about. So when we put this force on, hey, it was all, so a cross product gives you a torque. So when we do this, when we torque that wrench, we use I guess the right hand rule. So we're torquing the wrench that way, and then you know, the distance is where our finger goes, the force is with these fingers, and then our thumb is down into the page. And even if we were at a horrible angle or a 60-degree angle, we still have some component of the force this way. The component of the force that's either this way or that way isn't part of the torque at all. but in all three of those scenarios, our thumb is totally down into the page. You know what I mean? So the torque is going to be hinged about my thumb. You know what I mean? So that's important because that gives. I mean, I guess what I'm saying is that this cross product, if you have a cross product, you don't just get a number, you know what I mean? You actually get a vector. So, and that vector does have a magnitude. You know, that vector still has a number for its magnitude, but it has a direction. So, so with the torque, with the right-hand rule, is this torque is going to be basically into the page like a hinge about that bolt that you're torquing, and that's the direction. So yeah. And so the way to make this problem more complex is instead of just pulling this way or downward, let's say that I'm pulling at some sort of you know, and we know how a bolt works. You want to pull in line, in plane. You know what I mean? So if here's the bolt head, you know what I mean. You want to be torquing along that surface. But let's say you know this is hinged, and then you can like bring it out and up, you know, up towards us, and then pull. So let's say you're going to have like a 30-degree angle here. Well, now when you pull on that bolt, hey, you just moved the torque. So now the torque is acting at an angle like this, and so you have some sort of portion that's turning this bolt head that way, but then you also have a component that's wanting to kind of like rotate it this way. You know what I mean? Like a let's get some more sheets of paper and talk about that. Alright, hell yeah. So we're back, and we're going to take a look at this bolt. And then here's the top of the bolt head. And then we're going to throw our wrench on. And then this wrench is different, where like, hey, it can hinge, and now the handle is going to be straight up at you. You know what I mean? I don't know how to visualize that. But, you know, a side view would be like, hell yeah, the wrench is straight up, and then here's the bolt, and then there's just a 90-degree angle. Cool. And so that's what we're looking at. And now, if we wrench on it this way, you know what I mean? Obviously, we ain't, and, you know, I even want to say that the wrench handle is directly over the bolt, you know what I mean? And so if we're wrenching on it this way, well, hell yeah, we're not turning the bolt at all in this scenario. All we're doing to that bolt head, or that bolt that's in something, you know, in a chunk of metal, is all we're doing is we're just like putting we're putting a torque on it. And a torque is also a couple. So I would say we're trying to turn that bolt this way. You know what I mean? So that's the motion that we're trying to turn it. And so we're basically trying to, you know, torque the bolt head. So the couple would be a force here, and then a force here. You know what I mean? So that's kind of the couple that we're putting on, compared to just how we normally torque a wrench. Is that you know, we put a force on it, and this is the same thing as taking that bolt and putting a force this way and a force this way. You know, if we do that, we're putting a couple on this bolt, and that will also turn it. Now, in this case, I'll throw this as F prime, because obviously if you did this, these would be way larger than your actual, you know what I mean, the force needed to do this. And in general, this is FD. Yeah. So anyway, but yeah, so there you go. So now if we do this, the cross product would be, hey, the distance from the bolt is up towards us using the right hand rule. I got to go this way. So now this turning motion is there. So this is the direction of the vector of torque in this case. And if we stick our thumb in that direction of torque, you can see that here is the way we're trying to turn that bolt. Compared to how we just would do it normal, you could obviously see that this is the turning motion. I'm going to stick my thumb in the direction, or I'm gonna take my right hand and then sweep the direction that we're turning, and then my thumb goes right through that bolt. So obviously that's the way to go. Compared to this way, take my fingers and then sweep into the plane that's turning, and man, we're just trying to just reef this bolt, you know what I mean? So that's what we're doing there. So here the turning motion would be over the top, and so I would say, hey, for this one, here's the turning motion, and then I'm just putting a my torque. That's the direction of my torque vector, and again, it's just trying to turn it. So yeah, so you have two different things to get used to. Is like you're like, okay, when I torque a bolt, like I notice that I'm turning it in this plane. You know what I mean? Like I never think of it as like a right hand rule that, oh, I actually have a vector going into the page, and that's going to be my torque vector. You know what I mean? So, let's get a side view of that. So if here's my bolt, and here's my wrench, and then I'm putting a force, and then sometimes you just do this, like for force into the page, and then I'll like, hey, so you can kind of tell it's into the page, and so we're gonna put a force that way. Here's our distance R, and then so we're gonna have there you go. This will put a torque. That's the vector of our torque. This is going to be R cross F, and that's the direction. Cool. Yeah, and then if we have this on a handle, and then we bring it up to here and kind of do the same thing into the page, then our torque's going to be up here. You know what I mean? That's going to be, if we're calling this F prime, that's going to be the direction of our torque. So not only, so in this case, yeah, there's a component of this that is this way. You know what I mean? This is the useful component for actually turning the darn thing. And then this component, this component of the torque, and how do we do that? So we stick our thumb in the direction of the torque that's useful, and hell yeah, we're turning it. If we stick our thumb in the direction of this torque, well, now we're just trying to like over top this bolt. We're trying to like rotate it into a circle that way, and really reef the bolt head that way, which also puts an upward force. You know what I mean? A couple. We're trying to take that bolt this way and try to do this, and you know it's already in something. Alright, hell yeah. So that's the full deal on cross products, you know what I mean? And that is like the entry to do this problem. That's a huge component of knowing how to do this problem is cross product. And the easiest cross product analogy is the wrench. And what we're saying is that, hey, we've identified a force and it's a distance away, and we're saying that's the moment of force. Cool, you know what I mean? Identify that force and it's a distance away, and this is what you're going to tell your mechanic. 100 pound-feet, please, you know what I mean? Wrench my lug nuts to 100 pound-feet. And then so same thing with angular momentum. Angular momentum is a distance crossed with a mass times a velocity. Now so this is the moment of momentum. So we have the distance, that's the moment part. And then we have momentum. Cool. And then so other terms that will probably come up is that we have this term called second mass moment of second moment of mass. So let's just spell that out. So and then the other thing, this is moment of force. You could also call this first moment of force. And I think that's very useful at the basics. You know, every time you kind of see like a moment, be like, hey, yeah, I know that's I know, hey, put a moment on it, or a torque on it, a couple. But then moment is kind of like the go-to fundamental, because then you can say, hey, it's a moment of force. You know, it's a force that's a distance away. And it's the first moment. And the first part comes that you're just multiplying by the distance once. You're saying, hey, there's a force over there, and then we're just going to multiply by the distance. But anything that you hear is second moment, it's not that it's just like second in line or just like second in importance. It means that you're taking that distance and then multiplying by the distance twice. So second moment of force would be that distance times that force. So it would be that distance squared times force. That would be the second moment of force. So now we have the second moment of mass, and that's going to be that distance squared times mass. You know what I mean? So we have r squared times m. And this is also written like this, mr squared. And that's the thing that I do not like. There's a lot of things. Like, I don't like Avogadro's number named after Avogadro. You know what I mean? It seems like you're in a club now. You know what I mean? To learn anything about the way the world works, it feels like you have to just jump through the hoops of club. You know, club oriented. Now, there's nothing wrong with things being named, but even like pi, it's such a disservice to mathematics. You know, just by naming this, it should just be called 3. You know what I mean? I don't know what kind of tangent I'm going on, but and then he, you know, so there is that aspect, and then there's taking something that would make so much more sense. Second moment of mass. If you wrote it like this, and then just like, nah, we're just gonna write it like that. You know what I mean? Well, thanks. That's less helpful. So I guess you know what I mean. Apologize about Avogadro and pi. You know what I mean? But it's a buried entry. It's just like if you hear the word pi and you're like, not for me, then obviously pi is not a useful term. You know, if you're trying to get people to be more excited about math and numbers and mathematics or physics, there's some things that are just detrimental to the community. That at least there should be 2 paths. You know what I mean? There should be, hey, let's start calling this something different than pi. And then that'll help that community right there. You know what I mean? Alright, hell yeah. So I can't imagine this video is going to be good, but it is just one that's just like, hey, this is a problem that I cannot do. I could not do from the very get-go. I didn't even know how to make it simpler. I really didn't even know what momentum was. So I took about 3 weeks to actually kind of figure out what momentum was. Cool, we have an equation. And even from there, we should, because that's all it's asking. You know what I mean? It's just like, hey, what's the momentum? And so we should be able to use a simplified approach, because now what we're saying is just, hey, angular momentum is just the first moment of momentum. It's a distance away from a mass that has some sort of velocity. And so obviously, back to our problem, is like, hey, this is a lightweight rod, does not have any mass. Or does it? I don't think. The rigid rod of length L, yeah, it does not have any mass. It's like, yeah, it's a massless rigid rod. So our only mass is stored up into this disc. And we know the mass, the chunks of mass that are around the center of this disc only have, you know what I mean, they don't have zero velocity down here and twice the velocity up here because they're a spinning wheel, but they just have that tangential velocity. And then so from that component, hey, we have a mass, like we just said, the angular momentum of that mass might be, hey, that might be, hey, this distance, the first moment, so that'd be like 2 meters, times the mass, maybe that's 1 kilogram for that one, and then times the velocity. And then we only know that we have a rotation, let's say 1 radians per second, so our angular velocity is that 1 radian per second times that radians times radius is something normal, and that's going to be tangential velocity. So we have 2 meters. You know what I mean? So even from there, like this problem doesn't have numbers to compare it to, but yeah, we have something to go. And even like, I swear, even like right now, we probably have enough to go by that. Probably not. because we have to talk about, like, we have to talk about, hey, is the mass up here and the mass down here, are they providing angular momentum? You know what I mean? Yeah, and there's a couple different ways to look at this. So yeah, that's fascinating. But even just right here, hey, it looks like we have a number 4. You know what I mean? And then what's the units on it? Well, we have meters twice. So we have this should be in mass. I mean, it should be in distance times mass times velocity. So that should be but the velocity is omega times r. So here's your 2r, here's your r squared m omega. You know what I mean? So again, this r squared m shows up like that, and we call this the moment, the second moment of mass. And no one calls it second moment of mass. It gets its own, instead of calling it second moment of mass, it's just called moment of inertia. That's right. Moment of inertia. Yeah, it's called moment of inertia. Yeah. Which probably does not do it justice. Because inertia sounds like, I don't know, to me that just sounds like momentum. Like, oh, some sort of inertia. And that's what you're trying to find. You know what I mean? You're obviously, hey, we have chunks of mass that are... but in general, for this moment of inertia or second moment of mass, all it is saying, the simplest one to do is just like a string with a mass and then some sort of omega here, and then we have 1 kilogram. You know what I mean? So now we're spinning around this circle, and so and then from this point, from the origin, what is the second moment of mass? And then we're just going to say, hey, this is 1 meter. And then so it looks like we're going to have 1 meter squared times 1 kilogram. So the second moment of mass is going to be 1. And the units on it will be 1 meter squared kilograms. So is that what we have up here? Yeah, we have meters squared kilograms, and it's probably kilogram meter squared. You know what I mean? It's probably written like that. All right, hell yeah. All right, this is cool. I think I'm doing this problem like I was in prison, and they're just like, hey, you got one chance to say, you know, which one of these are true, and if you get it right, then you get out of prison. If not, you're going to be locked in prison for the rest of it. You know what I mean? I think that's my style. It's just like, if I can't like 100% prove, you know what I mean, the concepts, then it's not worth, you know, just writing an equation. You know what I mean? Because even right here, like, well, isn't this his equation? Don't we have angular momentum is I omega? Well, sure, but hey, we have an angle here, and then so it's not going to be in line. But if you don't care about that, and you just step down the problem and then put this on a ledge and then this on a smaller ledge, then you don't have an angle. You know what I mean? So if I use the cross product, because we said angular momentum was R cross mv, and so yeah, let's get our handout for this. So we have that chunk of mass, and we're going to stick our fingers in that direction, and then hey, that chunk of mass is going tangentially, and then so booyah, we're going to have so whatever this angle is, that's this angle, and this is our angular momentum. That's the vector for our angular momentum of that chunk of mass. Okay, sweet. And this chunk of mass that's connected to the ground is just not moving. You know what I mean? So and then let's take a look at this chunk. This chunk of mass is actually, and then it is kind of interesting. This chunk of mass is moving 2 times the tangential velocity that way. And so if we go from here to that chunk, well, cool. If this is the angle, You know what I mean? Hey, it looks like this is just twice the angle. You know what I mean? So there you go. So now we have, you know what I mean, kind of twice the angle up to there. And that means that this chunk, that chunk right there will have angular momentum in this direction. So it'll have that kind of component. Now again, if it's asking, hey, what's the component in the z-axis? So if this is our vector for angular momentum, well, it's got a component that way and it's got a component that way. If all I'm interested is in this component, like we said, you know what I mean, hey, it looks like if, well, let's break out a triangle. Even if it's like 30 degrees, if I say this is like 10 inches, or whatever, and then I say, hey, how long is that one? Well, let's split this one in two. That's an easy thing. Hey, this one looks about 5 inches. Cool. Well, how long is this one? You know what I mean? Even if this angle is 30. Well, you can just say it looks about 10 inches. So that's sometimes the approximations that you can make to make a problem simpler. You know what I mean? You might as well do that first. You might as well put this thing on a table and then... Or, I mean, yeah, so this angular momentum, even if we solve for that chunk, we would just say, you know, it's about the same. All right, hell yeah. So, okay, so now I definitely want to take a break from the angular momentum side and just kind of solve something easy. Because it says the center of mass of the assembly rotates about the z-axis with an angular speed of this, 1/5 times some sort of radians per second. Cool. And so if we can find, you know what I mean, how fast any part on this moves, like this rod in general, then we can compare it to this number. So yeah, hell yeah, let's do that right now. Alright, hell yeah. So before we move on, and I'm going to end this video, but because this was just kind of an introduction to the problem, and I don't even think it was that good. But at least we introduced what a cross product was, and but still, I don't think we have a tangible idea of what the hell angular momentum is. And so I'm going to try to briefly, just in words, say what this is. So, you know, I try to do F equals ma, and so we're going to do the whole, like, hey, jumping off a cliff into some water, you know what I mean? So that's us. We have some mass, and then we have a force on us, you know what I mean? That's the force of gravity. So the force on this mass is going to be, holy Toledo, lose my mind, but mg, cool. And then, you know, we can find the acceleration, and so, you know, the acceleration is just the g, because this side equals that side, mg equals ma. And then we know our acceleration, and in 5 meters, we now have an angular, I mean, we have a velocity of 10 meters per second. So holy hell, that's basically all I was trying to get to, is that now we have a mass with some sort of velocity. And it took the force of gravity, it took this force, you know, like 1 second to get this mass up to that velocity. Cool. So now, let's just say, for whatever reason, this mass is just now into deep space. There's no other forces on it, but we're going to say it's 10 meters per second. And it has a mass, and then, hey, let's say we just dropped a 2.2 pound rock, so it's just 1 kilogram. So we dropped a 1 kilogram rock off a cliff, and now we're saying this is 1 kilogram. So now we're going to take this problem, put it into deep space. We just have 10 meters per second. So now this is what F equals ma says. If you want to stop that, if you want to have this go from 10 to 0 meters per second, well, it says that you have to apply a force to do that, and I guess and I guess in this scenario, I guess we brought up the term, hey, we applied some sort of force times some sort of time factor, so F times change in t. You know what I mean? We applied a force for 1 second. But whatever that was, whatever that force per time, oh hell. But anyway, let's say for our scenario, is you need to stop this in 1 second. You know what I mean? So if that's the scenario, this thing's floating in deep space and you have to stop this in 1 second. Well, and you can only apply a constant force. You know what I mean? Well, it looks like you're going to have to apply a force that's equal to mg. You know what I mean? You're going to have to apply, and this is 1 kilogram times about 10 meters per second squared. You're going to have to apply a force of 10 newtons. So sweet. That's what gravity was doing to that to get it up to speed. And so that is the force. 10 newtons is required to stop that mass. Okay, so with rotational problems, hey, we're gonna treat it the same way. You know what I mean? So now let's say I just have a disk that's spinning, and this disk just has a mass here and a mass here. Actually, it's not a disk. It's just a chunk of mass. It kind of models a disk. When it's spinning, it might look like a disk. Or this is how we're going to try to model a disk. Maybe a disk, you know, looks like this. And then maybe actually it's 1/5 of its mass is in the center, and then 1/5 is at 4 corners. You know what I mean? Or, you know what I mean? Hey, you know, 1/9 of its mass is in the center, and then 1/9 is on the outside, but we have 8 of those. You know what I mean? But if we do this, if we have a circle that's moving, and we're going to say this is 1 meter, and then we were rotating with 1 radian per second. So actually, we're going to say we're rotating with 10 radians per second. So our tangential velocity, oh hell, and then we're even going to make it even simpler. So we're just going to take a center and then just 1 mass. I mean, because we want our problem to be, we're trying to introduce the idea of rotation and how it's related to F equals ma, and that F equals ma says if you apply a force on a chunk of mass and you have a net force, you know what I mean, a force net, that chunk of mass is going to change in velocity, you know what I mean. It is going to go from some velocity, whatever its velocity was, it's going to change by that amount. Alright, cool. So we're going to say, hey, this is 1 kilogram. And now we're going 10 radians per second. And so what's our tangential velocity? Again, we know 10 radians per second. Radians times radius, so we have 1 meter, is something normal, and that's going to be tangential velocity. This gives me Vt, and that's going to be 10 meters per second. So in this, we have a rotational problem, but we've identified 1 kilogram of mass that's traveling at 10 meters per second. If I had to stop in 1 second this mass, and the only way that I could do that is to put like a, and then I'll just do it tangentially, put a force, you know what I mean, like on this, or like, maybe you could also do it like this, where you have, you have an upside down rocket, you know what I mean, that has to, that you turn on, that can apply a constant force, you know what I mean, and this force is going to be that way. And you get 1 second to do that, and that force has to be constant, and you have to bring that 1 kilogram mass to a stop. So what force is that going to be? Well, we have a velocity, we have a mass that's traveling. We have a 1 kilogram mass that's traveling at 10 meters per second. And to stop that in 1 second kind of goes back to our problem of just dropping something. If it gets up to speed in 1 second because a force of mass times gravity is on it, and that was going to be 10 newtons, m times g, for our problem that's 1 kilogram times 10 meters per second squared, that's 10 newtons. And again, F equals MA. The units on this is 1 Newton is equal to 1 kilogram times 1 meter per second squared. We have 10 meters per second squared, 1 kilogram, so we must have 10 newtons. You know what I mean? Cool. So I guess that's it. That kind of concludes, and so obviously to slow this thing down, even though it's like spinning with some sort of angular velocity, to bring this thing to a stop that has rotational speed, we have to apply 10 newtons. Cool. And let's make the problem now. Now let's say we have 1 kilogram mass there, 1 kilogram mass there, 1 meter, 1 meter. And this thing's still going 10 radians per second. And I got to stop it in 1 second. Well, it looks like I'm applying 20 newtons. You know what I mean? And the more we make this a circle, you know, so now I have 4 kilograms. 1 kilogram there, 1 kilogram, 1 kilogram. And I still have that same 10 radians per second. I have a tangential velocity, and this is 1 meter, 1 meter, 1 meter, 1 meter. I still have a tangential velocity on all these of 10 meters per second. Each of them are a mass of 1 kilogram, so I have to apply 10 newtons to each of these. And so if all I do, though, is apply a rocket to just a 1, I have to apply that rocket at 40 newtons to stop this thing in 1 second. Okay, hell yeah. So how does that relate to our problem? Is well, look at this. You know what I mean? So isn't this disk? Couldn't we model, like, is it the first thing we want to do is just model this problem like this? You know, just on 2 flat surfaces, and they're going around in a circle. And I don't know. We're just gonna say this is 1 meter, 1 meter, and but then we definitely want to take a side view of this, because if this thing is rolling this way with some sort of omega, then let's take just a side view of that. And so, hey, we have an omega that way, and then we're going to simplify this thing into like basically one, and this says 4 masses. So yeah, we can simplify this and put it into 4 different chunks of mass. And again, we're just going to say 1 kilogram there. They're all 1 kilogram. You know, I guess we're just going to make up like say these are just 1 meter radiuses. And we have some omega. So and then so what we want to know is so let's ask the first question. What's the momentum of this? You know what I mean? If this is going 10 radians per second, each of these has a tangential velocity of 10 meters per second. And so this setup is synonymous with a 1 kilogram block, or let's say it's synonymous with 4 1 kilogram blocks, each traveling with 10 meters per second. Cool. It's also synonymous with a 4 kilogram block traveling 10 meters per second. Okay. So now, what's the definition of momentum? That's mass times velocity. Cool. So we have 4 kilograms going 10 meters per second. So our linear momentum, you know what I mean? Just the moment, and I think like that's what I think I can do going forward, is relate rotational problems into this idea that you have some sort of mass, and if that mass has velocity, like, well, a lot of problems are just like, hey, the initial velocity was 0, the initial like angular speed was 0, and now we actually got it up to some sort of angular speed, you know what I mean, omega prime or v prime. And if we did that, well, hell yeah, we had here a bunch of mass, but it was going 0 miles per hour, you know what I mean. So we didn't have any momentum, and then we do have momentum. And then from our scenario of dropping something off a cliff, same setup. We do have a mass. Its velocity is 0. It's v naught. And then, hey, 1 second later, that mass does have some sort of velocity. So we do have some sort of momentum. And to do that, that took a force to do that. Other problems might be, hey, you might have some sort of speed and you want to get it to 0. So again, if you're trying to stop this thing and hover it right there, well, it must have like a little rocket on it, and the force that's going to be required is going to be the same force to get it up to speed. You know what I mean? And like and so if it's 1 second to get it up to speed and 1 second to not, so this is where I could also be valuable. You know, someone's like, hey, can you teach aerodynamic problems or like aerospace problems? Well, it's like, sure, you know what I mean? Because you know, you can kind of simplify them down, and maybe it actually takes longer or shorter. Maybe you can stop this in 1/10 of a second because you put 10 times the force. 10 times the force for 1 second. Hell yeah, that thing is going to come to a dead stop in a hover. But, you know, maybe it takes 10 seconds to actually slow this thing down and get it to stop. Well then your force is going to be 1/10, you know what I mean, mg. Alright, hell yeah. Alright, so I love this problem. You know, this might be a 10-hour video, and it might just be total trash, but I think I kind of am able to answer my first questions. And it's just like, so how like maybe how is angular momentum useful? And I don't even think I'm there yet. I don't even think I'm, because right now I'm just looking at like just normal momentum. And so what I want to do is come up with this scenario where we have you know, so a sideways view, we have a mass here, and a mass here, and we're going to say, so all of these are 1 kilogram. So cool, 1 kilogram. We have it's rotating, and we're just going to say 10. I like this. I think this 10 radians per second now is sticking in our brains. Like we can visualize that. That is the same. You drop something 5 meters. You know, that's the speed of that mass, and then, you know, that the force of gravity is what got it up to speed. And to slow that thing down, you're going to have to, you know, put a force in the opposite direction to stop that. Cool. And in our problem right here, like obviously these are like point masses, or, you know, kind of small and condensed. Lightweight rod, and it's spinning around the origin right here. And so, so for our momentum, you know, for this, and this is 1 meter, 1 meter. Cool. So I think we got it. We got a tangential velocity of 10 meters per second, and so our momentum for this one, mv1 plus mv mv2, you know what I mean, or whatever, you know what I mean, just mv1, mv2. And this one is going to be 1 kilogram times 10 meters per second. So cool, we have 10 kilogram meters per second. You know, that's going to be the units for momentum. Momentum is going to have kilograms, meters per second. That's the units. I don't know. Well, I guess we'll just get used to it. But you're going to have 2 of those, because this mass 2 is also going to have 1 kilogram, 10 meters per second. So cool, add both those up, you're going to get 20. So we have 20 kilograms meters per second. Or I'm just going to say you have a momentum of 20. Cool, so for this we got a momentum of 20. But now what we're going to do is, what we're going to put it, yeah, I guess we'll just do it 1 meter away. I kind of want to do it 2 meters away. Hopefully it doesn't wreck the problem. But now what we're going to do is, this is 1 meter, this is 1 meter. We're going to have those 3 masses. But now it's like spinning about, this is also a lightweight rod. This is a lightweight rod that's able to spin. So we're with some sort of omega. And we're treating this like a wheel. You know what I mean? So as this thing spins, it's going to spin around this circle. And if this is going 10 radians per second, oh yeah, this is fascinating. So this would have a tangential speed of 10 meters per second. And so working backwards of what this is, we're just going to call it omega prime. And we might change this problem up, because I thought it would be better if just this was 1 meter, and that would make more sense. So yeah, let's do, well, first, like, I always have to keep it super basic. You know what I mean? 1 radian per second times 1 meter, that's going to be radians, times radius is something normal, that's tangential velocity. So if I'm trying to find radians, then I just, hey, get this equation and then solve for radians. So radians is tangential velocity divided by radius. And so hell yeah. So let's just make this 1 meter, and I think we can still visualize that. Because now our this omega prime will be 10 meters per second. Yeah, and can we prove that this oh yeah, it's so fascinating, like how wheels work, you know what I mean? Like, obviously, if this is going 10 radians per second, the surface has a tangential velocity of 10 meters per second. But with a wheel, this location isn't moving, but the wheel in general is rolling forward. Ah, damn it! I hate the mental blocks. But yeah, you know, I apologize for not even telling you what a radian is. I mean, if we're saying this is if this is our radius right here, because I usually do this every video. You know what I mean? If this is our radius right here, cut a string that length and then start draping it around the circle. You'll probably get to about there visually, right? And then that's going to be 1 radian. You know, so that's an angle of 1 radian in radians, and it's associated now if our that's going to be 1 radian no matter what. Like, even if this is 2 meters, we would cut a 2. You know what I mean? Obviously, our circle would be twice the radius, and then we would cut a 2 meter string, and then we would drape it around the circle. We'd still get to that location, that same angle, and it happens not by magic or coincidence, but just by defining it to be so. You know what I mean? The fact that we can say, hey, if I measure this radius with a string and then drape it around the circle, and I'm just going to say, hell yeah, that is 1 radian. Well, then that's kind of cool, because not only is this circle spinning at 10 radians per second, like you know what I mean, we'll go 1, and then there's about 6 radians in a circle. There's 6.28. That's the 2 pi radians in one revolution. You know what I mean? That's the factor label. And then so let's just visualize this. In 1 second, we're going to go 6. And then plus 1, 2, 3, 4. So we're going to go 0, 1, 0, 1, 0, 1. So we're going to go 1, 2. Yeah, we're going to go 1, 2, 3. So we're basically spinning that fast. You know what I mean? So there you go. But how this is spelled out is that we're also, you know, this linear distance is getting laid out every time. So in 1 second, we're laying out this linear distance. So we have a tangential velocity of the radius every 1 second. So our tangential velocity for this is going to be that radius, you know, per second. You know what I mean? It's going to be 1 radius per second, per 1 second. And that's going to be our tangential velocity. Now, how does that, Yeah, I'm even like baffled of how does that look like radians? You know what I mean? I think, and it's just defined to be so. I'm gonna take another pause. Oh, my bad. No, I made a huge error. We're saying our problem goes 10 radians. So if we have this like 10 radians per second, that's the other thing. Anytime you hear the word radian, you know what I mean, like 10 radians per second. You know what I mean? You should also write it as 10 radiuses. You know what I mean? Make it plural so you don't confuse it with radius. But 10 radiuses per 1 second. Cool. So now that's going to be our tangential velocity. So I apologize here, but yeah, we're going to have 10 radiuses per second. So we're going to measure the radius, and we're going to have 10 of those per second. So right here, you can obviously see this was the angular velocity. This was the radians. I'm sorry, the radius, and this was our equation: radians times radius. I was just showing that you know, if you lay that down. We're going to lay down 10 of these radiuses per second. So yeah, that's going to be very useful for me going forward. Angular velocity, 10 radians per second. Just say 10 radiuses per second. And then measure the radius. You know what I mean? And so whatever the radius is, you're going to have 10 of those. 10 radiuses per second. So we're going to have 10 times the radius. You know, every second. That distance, 10 times the radius. This is going to be a distance, and then divide it by seconds. And that's what angular velocity is, 10 radiuses per second. So you can imagine the radius being played out. So every second, we're going to have 10 of those radiuses. So there's 1, 2, and then obviously... Hell yeah. I mean, this thing's going to rotate once, because we have 6 of them. So it's going to rotate 6, 7, 8, 9, 10 of these radians. So, yeah, it's going to go over 1.5 times in 1 second. All right, hell yeah. So now I think that was a very good tangent of just like... And that's what you're never going to work on. You know what I mean? Where you're just like, hey, this problem isn't about... You know, working on basics of radians and angular velocity. It's working on angular momentum. But if you don't take the time to just kind of hone in your basics and knowledge, and then try to spout it out, differently each time, you use kind of a different method or different words to say the same thing. That's the only way that it is going to stick. And then that's why I'm glad I started this problem out. With using the wrench, because you know, even last time I did the wrench, I was confusing, like you know what I mean, if you're still pulling in this plane, well, hell yeah, you're still wrenching the wrench in its normal direction. Well, no, damn it, no, that's not true. So yeah, let's go back to this wrench just for a split second. If I do put a like a 60 or 30 degree angle, well, hell yeah, I have one component that's this way, and we know that the wrench is into the page. So if I look at a side view of this wrench, then now this component is actually I don't know how they do it. Is this into the page or out of the page? I think this is out of the page. So we have a force that's out of the page, and that's gonna move the bolt head, force it that way, and put a couple on it that way. So that's gonna be the torque in that direction. So even when you're applying a crap angle on a wrench, even if you're in plane this way, you're still trying to overtop the bolt this direction. You're trying to rotate the bolt. See how oh man, and then this is really difficult. So, but let's go the other direction. If this is the crap component that way, I stick my fingers in it, and so that there you go. So the bolt is trying to be over top this way. The vector on that is this way. So this is the component of that vector that's useless. The component of this force vector that's good is going to be the one with the circle and dot, and that's going to be into the page. That torque is the useful one, and then this torque is the non-useful one. Okay, I'm glad I mentioned that, because obviously this problem will involve cross products at the very end. You know what I mean? After I do all the who cares stuff. Okay, so right now we are just analyzing if this thing is spinning around a circle, because we want to, what I want to know is just how fast are the masses moving. And so yeah, let's grab another sheet of paper and do that. Alright, so we're back, and yeah. See, but this problem is a little bit different. We don't just have a wheel in space, because if we did that, we said we had momentum of 20. But now, this chunk of mass is not moving. It's stationary to the floor. That's an aspect that just happens with wheels. And this chunk of mass, the center of mass, is going the speed of 10 radiuses per second. And so, and then the radius is 1 meter. So this center of mass, so now this mass is going 10 meters per second. So cool, that mass is 1 kilogram. So right there, we have our first momentum is going to be 10. You know what I mean? Originally, if this thing is just spinning, it's going to be 20. But now check this out. This mass is going, if this mass is not moving, you know what I mean? And the center of mass is going 10 meters per second. This chunk of mass is going 20. Its tangential velocity is 20 meters per second. The other way to look at that is like, hey, disconnect the wheel from the ground and just have it spin. It's no longer spinning around this axis. And if you did that, it's going 10 meters per second. But the second you engage it to the ground, the rule is that this chunk of mass is going that spinning, that 10 meters per second, but plus the velocity of the center of mass, which is also 10. But then the other way to look at this is just by, you know, it's still connected with a lightweight rod, and it just has to be the case. If you're saying for sure the center of mass is going 10 meters per second, then if we draw a line from here to there, you know, in just a little bit of time, this mass is going to be right there, and this mass has to follow. You know what I mean? And I need to make videos on this. That was going to be the first videos that I made on angular momentum. Is if you treat this like a wheel, and now we're just playing to the page. But if we are spinning that way, hey, in a little bit of time, this top of the wheel is over here, and this part did not move, and then this part's right there. So right here, if we're saying the center of mass of this wheel, and then you just repeat, you know what I mean? You just say this process gets totally repeated. So now I'm just saying, hey, this center of mass, when you're, so if we're going from 0 to 1, now this is 1, and then you have a new mass up here that's doing the driving action. And this makes sense as if you're on an incline, because now you have those 3 masses. Due to gravity, you know, this happens, and then you just start the problem over. So this is what a wheel does, just on repeat. The force of gravity is forcing a small component this way of these 2 masses, and because they're connected, you know, it's also like a pulley problem where you know what I mean? Oh yeah, because. Yeah, it's kind of fascinating, because if you have this, and I think this one's a good one to do. If this is just a rope, like let's say there is no rope. Well, in 1 second, this one's going to fall, well, let's just say to there. And this one's also going to fall to there. Okay, but now look at this. If we connect this one to a rope, well, this one didn't get to there. And then if we connect this one to a rope, this one got farther. So if you do this scenario, and I should just do this, and then insert it into this clip right here. Alright, hell yeah. So we're going to show linear momentum, dropping 2 golf balls on a string. In slow motion, we'll notice that they drop or fall at the same speed. But then due to continuity, you know what I mean, something happens. So we're going to say, hey, that inner golf ball, its angular velocity is a lot faster because it has to go around a smaller circle. Now, the outer golf ball has to go a farther distance, and so its angular velocity is a little slower, so that's why it lags behind. Alright, now we got a massless rod and 2 golf balls, you know what I mean? So we're going to drop this scenario and then watch it in slow motion. And what you'll notice is that inner golf ball, heck yeah, it drops and then immediately stops and then kind of whips the outer golf ball. So continuity, you know, really shows its form. And this, in demolition, is how towers, when they fall over, the lower portion of the tower stops and then the outer part whips and breaks. Alright, hell yeah, we're back. And man, yeah, we got a clip, so that's pretty cool. I think you saw it. Hopefully we put it in. And it wasn't worth it. You know what I mean? That literally took, I swear, like 2 hours because I uploaded it and I was trying to make it into a YouTube short or whatever. But anyway, so now we have something to kind of go by, you know what I mean? I forget even where the hell we even are, but, you know what I mean? We're just showing how this is the rotation of a circle. And, yeah, you have a little bit of, you know, you have a gravity force, you know, a small component in this direction. Gravity's down, the force of gravity is down, but you're going to have a small component, you know what I mean? Like, hey, if this is the direction of motion, well, a small direction of that is that way. So cool. You have a, is that how it works? I forget. So I think we just need to move on. But cool. So I think we're showing how this is. Oh yeah. So yeah, this is, yeah. Back to this. You know what I mean? So this was going twice the velocity. I think that's all we were shown to prove, and then, you know, continuity there. So sweet. So I think we might be even able to, let's just get fresh sheets of paper, kind of use this method to even get kind of an answer, you know what I mean, to our problem. And yeah. So let's do this one just kind of one more time. So if this was just a wheel spinning, you would have 1 meter, and we're going to spin it 10 radians per second, and each of these is 1 kilogram, and so you would have a total linear momentum of the system would be, hey, that's going to be 10 meters per second, 1 kilogram, basically mass times velocity. That's linear momentum. We're going to have 2 of those, so we're going to have 20 kilograms meters per second. And then we just showed if it's going this way, and with that same angular velocity, that this one is also, yeah, holy Toledo. What were we saying? Yeah, so the tangential velocity here, the velocity tangential here, if it's also, if this is 1 meter and it's spinning around this way, that tangential velocity is going to be radians per second times radius. You know what I mean? We have 10 radiuses per second. Yeah. So yeah, radians per second. So 10 meters per second. Cool. Yeah. Now I think we need to visually link those two together, and because we're saying this one does not move at all. This one is now going 1 meter, yeah, 10 meters per second, and yeah, hell yeah. And now we know that this one is going 20 meters per second. Cool. So now we do the linear velocity, and we're going to have 1 kilogram going 10 meters per second, plus 1 kilogram going 20 meters per second. Cool. So we're going to have a total linear momentum of this of 30 kilograms meters per second. So we have, so in this scenario is still, hey, this thing is still, you know, if you get rid of the ground, like visually this thing is still spinning, but it's also translating that way. But yeah. So if this is happening, and it basically just kind of proves this, is that if you have a wheel, and I like this example that this is kind of a wheel pinned, and now we're spinning it. this will have a linear momentum of 20. And let's go this way with it. So then we're, you know what I mean, this is not attached to the ground, and it's just a spinning wheel. Like if you jacked up a car and then the wheel's not touching the ground, you know what I mean, it'd be really easy to spin that wheel. And I guess a car's not a good example because it's connected to a huge chunk of mass. But yeah, let's say you just spun that wheel around a fixed point, even a car wheel, and then you decided to have this wheel go the same speed. You know what I mean? Now just rolling across the flat. So you got it up to 10 meters per second. And 10 meters per second, you know what I mean, just for the Americans, that's 22 miles per hour. And that's a good one to memorize, you know what I mean. It's probably like 22.3 actually. But there you go. And so cool. So in this scenario though, when it's rolling this way, we get that same setup where we don't have any motion of the masses near the surface. This center of mass is still going that 10 meters per second. And this chunk of mass is going 20 meters per second. And, you know what I mean? And if we do it like our scenario, where this is going to be our wheel, hey, we get 30. 30 for our linear. So linear momentum term is 20 in this one, and it's 30. You know what I mean? It takes, and to put some idea on this is like, well, to get this wheel, to get all these masses going that fast, it requires some sort of force. You know what I mean? So we have the same, we have 1 kilogram there, 1 kilogram there, but we're getting this one up to 10 and this one up to 20. So that requires, like, you know what I mean, this amount of force. This one, hey, this one stays put. This one is going 10 meters per second that way, and then 10 meters per second that way. So it only takes, you know, we basically have, it's going to take less force. You know what I mean? So less force to get these from a stationary, you know, velocity 0 up to 10 and 10. And it's going to take more force to get these from 0 up to 10 and 20. And so that's the whole visual, visually, that's going to be the analysis there. And, cool. And just like F equals ma, well, if we have 1 kilogram, and then we change its velocity, you know what I mean, in 1 second, you know, if we have an acceleration of a number, you know, per second, and then we multiply by that 1 second of time, you know what I mean, hey, we get a, what do we get? Oh, man. Oh, yeah, we get the force required, we get the force for 1 second required to change that velocity, you know what I mean? Because if we do put a force for a second, we are going to get a change in velocity that's equal to this term acceleration, as long as the units are meters per second per second. Alright, hell yeah. So, either this section of the video is just gold or garbage, you know what I mean? But I'll do this better, you know what I mean? This is just kind of my first round, and again, it's just like, I'd want to tackle like 20 problems like this before I can you know, tell you what's going on in this problem. Now, if you're just using the letters and the cross products, cool, and then, you know, angular momentum. But if you don't have any idea of what angular momentum is, and because like in this, hey, we're finding momentum, you know what I mean? And so so if this is momentum, you know, if this 1 kilogram mass is going 20 meters per second, what is the angular momentum? You know what I mean? Oh, and then this is fascinating. Because if we take the angular momentum about this origin of this wheel rolling, the angular momentum will be, you know what I mean, r cross the momentum. See, and I just have I'm not very good at figuring out what the hell angular momentum is. Anyway. Yeah, and maybe that's a dumb place to take the angular momentum, because if we do it from here, we don't have any momentum in that one, and we don't have any distance to this mass that is moving, but we have a distance of 1 meter to that one. So we say 1 meter and then times 20. So that 20 is the angular momentum of this, and it's in units of meters, mass, and then meters per second, or kilograms meters squared per second. Now the angular momentum of this about the origin, and I think this is good, because I apologize, I have no idea the usefulness of angular momentum. I know that it can be conserved as long as there's no net torques, and even before that, I knew it could be conserved, but I didn't have a grasp of like what the hell the no net torques means. And we're not going to go into a tangent about that because I'm just not prepared for that. But anyway, so if we take the moments about this origin for a wheel that's not touching the ground, well, hell yeah. Now you have the distance is 1 meter, because we have r cross momentum. And then we have the momentum, which is a mass of 1 kilogram, times 10 meters per second. And check it out, we're going to have the same setup to this one. So we're going to have twice that. So we're going to have 20 kilogram meters squared per second. Okay, so it looks like from the center, these momentum is the same. But now let's take it from the moment from just the ground. And we're going to say this one's very close to the ground, but not touching. Okay, so if we take the angular momentum from the ground, this mass... well, this mass isn't moving anyway, but it's also, there's no distance to it. So the angular momentum from A is going to be, hey, this mass, that's going to be a distance of 1 meter, times the, times this momentum, that's 1 kilogram, times the velocity of 10 meters per second. But then we're going to add it to this one, which is a distance of 2 meters away, times 1 kilogram, and times... it's momentum. So it's distance times momentum. So we have distance of 2 meters times 1 kilogram times 20 meters per second. So now this term becomes 40/50. So now here we get 50 kilograms meters squared per second. That's the unit of angular momentum. Now if we go over here and do it about this point, well, this point isn't moving, and then we just have that. So the angular momentum about A this is the only mass that's moving. This mass is moving, but it's at the same location at A. So the distance away of this mass is basically the same. And then so we have 2 meters times the mass of 1 kilogram times the velocity of 10 meters per second. So so we get 40. So yeah, it's not nothing, you know what I mean? So this one had an angular momentum of 50 from that point. This was 40, and from the origin they were the same. So now we kind of show that, hey, the angular momentum can be different from different points. Like obviously, if you take it to the extreme and you go infinity down, you know what I mean? Or, you know, like if you take the angular momentum from the center of the Earth of this spinning rod, or of this spinning wheel, you know what I mean, you'll go all the way up, you know what I mean, to this point, and see that it's moving that way. That's going to be the distance. So we have the distance is the radius of the Earth, and then you would have the mass is 1 kilogram times 10 meters per second. So, yep. But then I think, and don't quote me on this. Yeah, no, I have no idea. I mean, yeah. So, yeah, and then that's it. I really don't know anything more about angular momentum. But that's why we're doing these problems to, you know, get to a point where you're just like, yep, that's it. But I guess, you know, I started with momentum because I do understand momentum. If I have, you know, something that jumps off a cliff and we have the force of gravity on it, heck yeah, it is a mass, and at some point it's going to have some sort of velocity due to that force, because F equals ma. It's going to change its velocity due to that force. Cool. And then so at any given point, this thing is going to have a momentum. It's going to have a mass times the velocity. And I get that this momentum is just a characteristic of a chunk of mass. If we say we have a chunk of mass and it's moving with some velocity, then we can characterize it as momentum. You know, mass times velocity. And the only way to actually get a chunk of mass from a velocity of 0 to some sort of velocity is to put a force on it. That's going to be the F equals ma. If you have a mass that's not moving, and then over here it has some velocity, well, you must have changed its velocity, and that's it. There you go, change in velocity. Even if you don't know the time frame on that change in velocity, you know you changed the velocity. And so if the velocity got changed on that mass, then you know that there was a force in that direction to cause that. You might not know the magnitude of the force because you don't know the time frame. You know what I mean? If you see a mass and then 1 second, that's why the easiest thing to visualize these problems is just work in increments of 1 second. If I see that it's stationary here and then 1 second later it has that 10 meters per second, you know, that's free fall. Well, hell yeah. Then I can say the acceleration was 10 meters per second, and then I have a mass of 1 kilogram, and then definitionally I can see that that's 10 newtons. There was 10 newtons of gravitational force on 1 kilogram to make it go 10 meters per second in a second. Okay, so now, yeah, so that was that. And I don't know if this is the whole intro to this problem. And then, you know what I mean, I eat a sandwich and then come back and then just tackle it. That's what I'm going to do right now. So I'm gonna kind of have a hard break in this video where I just come back and pretend like that whole first half didn't happen. But we learned about cross products, we learned about torque, we learned about first moment of force, and then we learned about moment of inertia, the second moment of mass. We learned about rotating things and how, hell yeah, you can simplify them just by, you know what I mean, making the mass out at the end, but you got to do that in a way that makes sense. You know what I mean? You have to take a circle, and that's why you just use the formulas for moment of inertia of a disk, and you know all that stuff. But hell yeah, we're gonna do a hard stop, and I'm gonna start this problem from D, and we'll see if that helps my game. Because that was the deal. It's just like I was just like, yeah, tomorrow I want to post 1 video. You know what I mean? Just on like, hey, if there's only one thing I can do with this problem, it's going to be this angular speed. I know what that is. I'm still real bad at angular momentum. And so, all right, so before we do the hard break, yeah, this problem sucks because it says the magnitude of angular momentum of the assembly about its center of mass. Yeah, so I think before we do that hard break, I want to learn as much as I can about this problem. Because the angular momentum about the center of mass, well, let's talk about that. So what we're going to do is we're going to do this problem and kind of make it a little bit simpler. So we're going to have 1 meter here, 1 meter here. It's going to be spinning around, you know what I mean, here's the radius, and then here's the radius of the inside. Okay, I'm just going to say this is 1 kilogram, 1 kilogram. I think we got that much. I like this 10 radians per second. It's visually makes sense because I know that if this is 1 meter, I know this is 10 meters per second, and then this would be 20 meters per second. Okay, cool. So now, and I know the center of mass is right here. You know what I mean? So I'm gonna call that C. I'm gonna call that C. And so the center of mass between this, and you know, even this, we can connect it with a lightweight rod, just like our problem. And so, I want to know the angular momentum about this point right here, about the center of mass. Yeah, that's a tricky one. It's kind of bizarre to me, actually. So yeah, let's try to make it simpler. You know what I mean? Let's say we have a mass on a string, and then we just have a mass right here that just spins around the axis, but then we have a string out to this mass. So the center of mass is right here, and I'm gonna figure out what the angular. Let's first figure out what the angular momentum is around this z-axis. Is that what we want? Angular momentum is r cross mv. So it's the the distance out to this mass is 1 meter. So we have 1 meter. The mass is 1 kilogram. And then we're going to say 10 radians per second. And so the velocity is 10 meters per second. Cool. So then we're going to have an angular, what do you call it? Angular momentum. You know what I mean? Yeah. It's the moment of it's the moment of momentum. Angular momentum is the moment of momentum. It's the first moment of momentum. Just like torque is, we'll say distance times force. The torque is and I think that's why it's just like torque usually gets written force times distance. And it's like, even like that, that's a disservice. But, you probably have to write it like this because this looks like the derivative of force, dF. But just know that, you know what I mean, if we're talking about generically, torque can be like R cross F. You know what I mean? That's going to be torque. Even though when we write it like this, it's force times distance. Okay, so we have first moment of momentum. That's angular momentum. And then we have just a value of 10. Like, who cares what the units are, but they are kilogram meters squared per second. Now, let's take the angular momentum about, you know what I mean, this point. Well, just visually, that's going to be 0 because there is no distance to this mass, and that's the only mass that's moving. This mass isn't moving. There's distance to it, but it's not moving. So if I call this B, point B, the angular momentum about B is just 0. There is no angular momentum about B. Even though it has linear momentum, if we take the angular momentum about that point, there is just no... okay, so I get it now, you know what I mean? Because if we go back to the wrench, you know what I mean? We say, hey, we need the force out there, and we need it perpendicular. Cool. And then here's the bolt head. And so we need the force at some sort of distance. So, saying... okay, and then so right here, this is the mass, that's the mass, and then this is its velocity. Cool. And so what we're saying is the same thing here. If you make this a wrench, then we're saying, hey, this is the mass, right? Oh, sorry, we're just making, engineering is hella sucky, because you're just going to make phallic, I tried not to mention it all the time, and I tried to get it, try to do everything as boxy as hell, but sometimes you just mess up, so I apologize about that. And that's all. Even when I do the wrenches, you know what I mean, I'm just like, holy hell, how do I make a wrench not look phallic? Okay, so so it's the same thing. So we have force times distance, but let's say just out here we have same wrench, and we're just saying, hey, we have some sort of mass out here. I'll just make a square box. So we have some sort of mass, and it's got a velocity this way. Cool. And its distance away from this point, you know what I mean? Now we're talking. It even looks like if we have some sort of mass and velocity, it's very similar to what a force would do at a distance. All right, hell yeah. And man, this video ain't gonna be good, but it's gonna really help me. And I'm just gonna double down. I swear, because there's gonna be things that people don't know, and if you try to make a video like this, and just be open to the things that you don't know, and even to the point where it's just like, be okay to make mistakes. Even because that's what it's just like. I don't mind if I do problems completely wrong. Just the fact that I tried my best, and then, because I'll think about this stuff hella, like, after I do this. So it's just fascinating whether this is even worth it. Kind of a long format video of this JEE advanced problem. But I just want to show you like the kind of the full scenario. And I'm trying to teach it as I do the problem, you know what I mean? Like, obviously, if I just wanted to get to it, I could probably, but that wasn't the point. I want to have a general understanding of what's going on with this problem so I can intuit. So then when I see this number, like 17 ma squared omega divided by 2, that means something to me. You know, because right now this means absolute nothingness. And the fact that this is 55, you know what I mean? I guess I get that because check this out. So even right there is like the first aha moment. Even from that diagram of hey, a mass right here out to a string, and then the mass that's actually moving. And then if I take the momentum about the z-axis, hell yeah, we get some angular momentum. That value is going to be 10. If I take the moment about b, that angular momentum is going to be 0. 0 L about b or L about the z-axis. Okay, so same thing here. This thing is hella moving. It's got the most velocity tangential. And it's got other stuff that's also hella moving. Like, and we can just say, hey, this is a 3 mass wheel. You know what I mean? Just like we did. And so this one's not moving, and this one's moving twice hella. You know what I mean? So that one's twice. Okay, sweet. So and again, like, who cares about this angle? So if we wanted to say what's the angular momentum, L. So hell yeah, we could probably do this. So there you go. See, this is where the light bulb turns on. It's just like, you know what I mean, go through the theory as much as you can, and then apply it. Because what's the definition of angular momentum? It's distance crossed with momentum. And now we know what the hell that term is. You know, we did the wrench analogy, got a little embarrassed, and now we're pumped up. And so hell yeah. So and even this, we're just going to make L 1 meter. Cool. So this is 2 meters, and then we're even going to say this omega is 10. You know what I mean? I have no idea what this omega is, but well, and then check this out. It's saying this omega is we're going to say, you know what I mean? Hey, maybe this omega is 10. Is 10 radians per second. Hey, maybe it says this is 2a. Yeah, I kind of just want to make 2a equal to 1 meter. You know what I mean? So I guess a is 0.5. A is 0.5 meters, because we'll have to throw that into the equation, because even right here, if a is 0.5 meters, a squared is going to be 1/4 of this generic term of meter. You know what I mean? Oh, but there's no L term in here either. So yeah, there you go. So L is equal to 1 meter. A is equal to 0.5 meters. So then L is equal to 2a in our problem. So if we get an L, we can switch it with 2a. Oh, this is hell yeah. No, yeah, because I'm probably going to start the video at some point and then do that problem. But I don't know, maybe not. I mean, no one really cares about this. It's the easiest one to find. Like, I was just like, hey, if this is spinning at omega, you know what I mean? Then I was just trying to find the linear speed of this, you know what I mean? And the tangential speed of this wheel around the circle is just holy Toledo. Yeah, it's bizarre looking at a circle and then a circle that's attached to the road. Okay, let's get back to this one, though. So we're going to say, oh yeah, and why I did that is, yeah, because it already spells it out. Like, I've at least done D, and I have a check on reality, that this omega, this way, is 1/5 this omega. So if this omega is 10, this omega, omega prime, we'll just say, is 2 radians per second. So it's 2 radians per second around there. Cool. Oh, you know what we could do, though? You know, I think this would make the problem... Yeah, no, we already set 2a is equal to 1 meter, and that was pretty good. just visually, it looks like L is twice 2A. You know what I mean? Because we could say this is 2 meters and this is 2 meters. Hopefully that doesn't get us in trouble. But we can say that L is 2 meters, and then 1A is just 0.5 meters. So that means that L is equal to 4 times A. So yeah, so maybe this will be good. You know what I mean? Because that's more representative of the problem. If you're saying, hey, it looks like 1 meter is equal to 2A, and then L, 2 meters, is equal to 4 times A. Alright, hell yeah. So, yeah, can we figure this out? We're saying this is 10, if this is 10 radians per second, that means that this is going to be stationary. This velocity, tangential, is going to be omega times r. It's going to be radians per second times the radius. That's tangential velocity of the center of mass. You know, that's the interesting thing about a wheel. When you don't have a wheel, then hella, yeah, these ends are going to move with a velocity tangential of omega r. You know what I mean? So each of these would be going at 10 meters per second, 10 meters per second. But when we have a wheel on the ground, this one's going 0. This one, which direction are we spinning? You know what I mean? I guess this one's spinning this way, this one's spinning that way. Yeah, and this is going... so the center of mass is going 10 meters per second. This is going 20 meters per second. That's just the nature of the wheel itself. Because you're putting down a linear distance of this tangential velocity. And we've already explained that in radians. You know what I mean? But if you're going 10 radians per second, you know what I mean? Hey, this radius is what you're going to be doing every second. And that's going to be the tangential velocity. That distance in 10 radians per second is your velocity tangential. And the radius is 10 times 1 meter. And this 10 divided by seconds, that's the definition of a radian. Radian is dimensionless divided by seconds. So, hell yeah. And I don't know, even though like this problem sucks and I'm just going to do it and make a 10-hour video or whatever, you know what I mean? Hey, that's a little piece of gold. You know what I mean? Just the fact that no one's going to come back to things 1,000 times. Yeah, I'm like the memento of physics. Like, holy Toledo. Alright, so, yeah, so I think we can do this now. So we found that this one is going 0. This one is just going 10 times, we're saying this is 1 meter. Thank God. Yeah. Just visually, this is 1 meter, this is going to be 2 meters. Okay, so this is going 10 meters per second, and this one is going 20 meters per second. Cool. So now, because we want to know what the linear, because angular momentum is the first moment of momentum. So it's kind of cool to know what momentum is. So just how I do F equals ma, like in these angular momentum problems, I want to know what the linear momentum is, because that is king. You know, if you have all these chunks of mass that were not moving, and then all of a sudden you start to rotate, you know what I mean? Because this problem is you have no change in angular momentum. Like the angular momentum in the system is constant, but if this was going from 0 velocity and then you got it up to this 10 radians per second, well, then all those chunks of mass would not have any velocity. And then once we get it going, hey, we're going to say this is these 3 chunks of mass and this is these 3 chunks of mass. And now we only have 6 chunks of mass to kind of play around with, but we have to know, like, hey, when this is doing this, we can figure out the velocity of each of those. You know what I mean? These ones are not moving. Hey, hell yeah, that takes 2 out of the system, and then these are just moving double. So finally, mentally, I just have like an idea where it's just like, hey, it looks like we've made a simpler problem. Alright, sweet. And let's see. Okay, so yeah, this is the momentum. It's that 1 kilogram. You know, I don't want to forget that kilogram term, but it's just 1. So it's basically the momentum, if these masses are 1 kilogram, is essentially just the velocity. You know what I mean? This has a linear momentum of 10, this has 20. And linear momentum, again, the units on linear momentum is kilograms, meters per second. Sorry, meters per second. Angular momentum is this times distance, that would be kilograms meters squared per second. Cool. Okay, hell yeah, but we can get a term for this z-axis. I mean, we're going to neglect the angle, we're just going to assume that they're totally straight. But yeah, that, well, yep. I was thinking, like, wouldn't that be the same as taking the angular momentum about the o-axis? But I don't think so, because look at this. Like, this tangential velocity, because, like, and again, we're like, I'm assuming that this thing is totally horizontal. So, this tangential velocity, this tangential is twice this. But if this thing's at a hella angle, that is not true. You know what I mean? Because things on the inside will have less. This will have less. It won't be twice. So even right there, we know that whatever answer I get to this simpler problem, you know what I mean, might be less. But honestly, the huge hiccup is calling this disk just 3 chunks of mass that are 1 kilogram. Like that is probably not representative. Like maybe more representative is calling this 5 chunks of mass, you know what I mean, with 1 in the center. But even that's probably a horrible representation. But until I do more of these problems, you know what I mean, then I'll figure out what jives. Because maybe just increasing this mass in the middle to be like double. No, I don't think you would do that. I think more of the mass is on the outside. But yeah. I don't know what would be representative. Okay, so let's at least get a number for this. So if we're going about the z-axis, assuming there's no angle, angular momentum about the z-axis, finally. Just for these two is going to be 2L. So we have, yeah, I guess I'll just do it with letters. 2L, or I don't want to do it with letters. So we have 4 meters. 4 meters is the distance. And then we have this one going 10. And then we have 4 meters, and this one going 20. They're going 20 meters per second, and then we got to multiply by 1 kilogram. You know what I mean? That's just 1. So here we got 40, and here we got 80. So there you go. About the z-axis, we have this one is 80, this one is 40, so we have 120. So we have 120 kilograms meters squared per second. Okay, that would be the angular momentum from my dumbed down problem. Now let's try to get letters on that. So we have angular momentum is r cross momentum. It's the first moment of momentum. And we have, with letters, all these are going to be 2L. So that's going to be our distance. To the first one, we have its mass, just m. And I'm saying m is 1 kilogram. Its velocity, which is omega times the radius, and the radius is 2a. So we have mass times velocity, that's going to be omega times 2a. Cool, so this is the term for that first one. Okay, now let's do the second one. We're still going to do 2L over to that mass. So we have distance times the mass and times the velocity of that mass. Well, this one, that mass is going to be twice. It's going to be twice the velocity of that one. So I'm just going to throw the 2 in right here. And then we have omega, and then we have 2a. Sweet. So, yeah. I think that's good. Let's clean this up. So this is going to be 4Lm omega a plus, and this is going to be 8. This is going to be 8Lm omega a. So now we have 12Lm omega a. And now we used letters, but we kind of have an idea of what, we're not losing, you know, too much just by doing letters. You know what I mean? Kind of what's going on with the problem. Alright, so, but they don't get their problem in terms of, they don't get their problem Yeah. And check this out. They're saying this is 4m. That's the mass of the full thing. So we need to take that into consideration. So if I'm breaking this up into thirds, like it's not very useful. But like one of those is 4/3 m. So that's what we have. I mean, it's an approximation. So let's do this again. So we have a distance of 2L. So that's our distance. We have a mass of 4/3 m. Cool. And then we have a velocity, because we're trying to find the velocity. That's omega times the radius for this one. That's going to be 2a. So this is omega r, and that's going to be the velocity tangential. This is the mass, and this is the distance r cross mass. Okay, so now we have the second one. It's still 2L away. We still have 4/3 mass for this one. Alright, hell yeah, we're back. Got some more juice in the camera. So we're doing r cross momentum. So we have the distance, 2L, the mass, 4/3 m. And now we have the velocity. That's going to be omega r, that's tangential velocity. And so we have omega, and then the r. But the actual tangential, the velocity of this is 2 times that. So I'm sorry about not putting the 2 in right away, but we'll do the 2 right there, not to miss it. Okay, so now we have 4, 8, 16. So this becomes 16 divided by 3. So we have 16/3 Lm omega a. Is that right? 8 times 2 is 16 divided by 3. Okay, so this one is going to be 4 times 4, that's 16, times 2, that's 32. So this one is going to be 32 divided by 3, Lm omega a. So I'm just going to use, I don't want to make mistakes, so 16 plus 32 is 48. So now we're going to have 48 divided by 3, Lm omega a. But for our problem, they don't want to use, and even right here, they're saying alpha, they're saying length is square root of 24. So square root of 24 is basically 5. We're saying L is 4 times A. So we're going to be off there. But I don't know. You know what I mean? Like, who cares? Like, that's fairly close. Visually, we were just like, sweet. But now we're going to use our method to get this with just A. Just the A term. And, yeah, that's interesting. They say this is omega divided by 2. But anyway, I guess they're getting the A term because we're changing L to A. So if we say L is 4A, so let's do that. So we got 48 divided by 3. We got 4A mass omega A. Cool. So now we'll get that A squared. And we got 48 times 4. So we got 192 divided by 3. And they got 17 divided by 2. So 17 divided by 2, that's just 8.5. Let's see what we get. We're probably nowhere near that. But so we get 48. Oh, and my bad. Holy Toledo. No, we messed up the problem. Like, obviously. Because when this thing's spinning, sure, it is spinning with this 10 meters per second. But this technically is only going this way with omega divided by 5. You know what I mean? So, damn it. So, yeah, that's interesting. Yeah, oh, that's bizarre. So, yeah, I messed up because, yeah, this tangential velocity is way less than what I gave it. So, yeah, so saying this was 192 192 divided by 3 is just a horrible guess. They got 8.5. So if we take that in consideration, and visually, I can't even visualize that. It's like, oh man, this sucks. Well, let's maybe flatten it out. All right, so I mean, all we're friggin' is analyzing is just this one. So we have 2L, and then we're gonna say, hey, we have a circle here, and we're gonna model this as our circle. These masses are 4 divided by 3m. This thing is, and you know, I guess visually we'll have to give it 3 dimensions, because we're gonna say it rotates this way. Man, but then this whole thing will rotate this way with omega prime. So this is 2 radians per second. So, yep. And then we're going to say it goes on a table where, you know what I mean? Hey, if this is a wheel on a table, there is no velocity to this mass. This velocity is 0. This velocity is this radius, 2L. So the velocity tangential of this one is the radius, or omega prime, radians per second, times the radius. So that's going to be 2L. And for our problem, that's going to be 2 radians per second times 2, and then these L's. Yeah, and let's do it like they do. So L is equal to 5A. So we're going to at least do that. And so these are just 2.5. Yeah, we're saying, for our problem, we're saying 2A is 1 meter. So 4A is 2 meters. 6A is 3 meters. So 5A. 5A is 2.5 meters. So these, instead of being 2 meters, are 2.5 meters. Okay, so we have a check on reality there. All right, hell yeah. So now I feel like if our model works, maybe we can get somewhere close to this answer. Hopefully. All right, so yeah, so this one is only going, its tangential velocity is only going that way, just because it's not going, you know what I mean, like these are going like up and down as well as moving that way. And that's where you have to analyze the wheel. Like a wheel moving this way, if this is your wheel, this one's not moving. We're saying the center one moves at, well, let's do it. So 2 times, what's L? 2.5. So there you go. So this one is going to be 5 times 2. This one's going to be 10. So we have 10 meters per second for that one. Just definitionally, this one now is moving 20 meters per second. Oh, and that's fascinating that the problem worked out that way. Yeah, it's the same setup that we just came up with. If this was 10 meters per second, this one is traveling, and 2A is a meter. This one's traveling 10 meters per second. So that's what we came up with. Oh, that's bizarre. Oh yeah, because this problem, it doesn't matter that it's going around in a circle. Essentially, yeah, that's duh. Okay, essentially we just have a wheel. Who cares if it's going around in a circle? We just want to know like these tangential velocities. Yep, but we are getting a hella different answer than this one. But you know what I mean? That's why this sucks. It's not saying that is the answer. It's saying, hey, this probably is or probably isn't. You know what I mean? Prove it. Prove that. The angular momentum of the assembly. Oh, yeah, duh. So this isn't even the one we're doing. We're trying to do this one. Because this one, we'll have to get back to it. You know, that's this. You know what I mean? Hey, if we have, if this is our setup and this is going around, the center of mass is right here. This was B. We said the angular momentum about B was 0, and we get that because there is no linear momentum. And well, no, there is mass times velocity of this. It does have linear momentum, but there's no distance to the center. You're already at the center, and nothing else is spinning. So, and if this is the center of mass, then obviously the angular momentum about the center of mass, now you're going to have this. So we could do it for this problem. Let's do that. So about the center of mass is just as R cross mv. And now we have, and these were 1 meter total. So now we have 1/2 meter times that mass. That's going to be 1 kilogram. And in all our scenarios, we're doing 10 radians per second. Because it kind of mimics free fall, you know what I mean, that velocity after 1 second of free fall at 10 meters per second. And so, but in this scenario, our angular momentum is just 5. You know what I mean? So we only have 5. Angular momentum about the z-axis is 10. So now we have now we have this like representation where. And that was for this scenario where it's like, hey, if we took the z-axis right here and said, you know what I mean, like, hey, our angular momentum's 55. Yeah, because this is 17. This is 8.5. Yeah, 17 divided by 2. 17 divided by 2. Yeah, so now we have a visual representative. If our z-axis is right here, and all the angular momentum is coming from that disk, going, you know what I mean, for our setup, and then we say, what's the angular momentum just right here? Well, it's going to be 1/4. We just found out that it's is it half or 1/4? Oh, damn it. I guess it's just half. Okay, so yeah, so if the angular momentum would be half. So if this is the angular momentum would be half right here. But that's not the scenario we have. Because, hey, this is the z-axis, and look, like this, like let's say all the momentum comes from this. Like we just have a tangential velocity, all the mass comes out here. This is our angular momentum. It's this distance that's 2L, and now we're just saying, hey, what's the angular momentum about L? So we can totally do that one visually, because that's this scenario. Like all of our mass is at 2 meters. So we have 1 meter here, 1 meter here, and then what we're saying is the center of mass for this is at 1.5 meters, and then this is only 0.5 meters. So if we have a big number, well, I guess we're just going to use 10. If we have 10 meters per second on this 1 kilogram mass, and the angular momentum from this z-axis is r cross mv, you know what I mean? Alright, this is exciting because this is like the first time where it's just like, okay, hell yeah, I can kind of visualize what the hell is going on. You know what I mean? So we have, well, yeah, we're going to say, hey, that momentum is 10, 1 kilogram times 10 meters per second. The distance is 2, so we have a number of 20. Okay, but that's from the z-axis. Now we're going to come from the center of mass rate. You can treat it as an axis too, but just the center of mass. Our distance is 0.5. And now our momentum is still 10, and so now we have 5. So we're going to have a quarter. So hell yeah. So is 55, if we say 55 divided by 4, you know what I mean? Hey, we're in the ballpark, you know what I mean? So now we know that we get it. We get why the momentum about the center of mass is about 1/4, you know, for these scenarios. And, you know, I mean, hey, we can say, for our problem, like, what could we do? I don't know. I mean, I guess you could just call this, you know, you could have 4 of these masses, and then here you only have 1 of these masses. And then you could, you know, see if, I don't know. You know what I mean? You could maybe get a better approximation. Okay, so let's go back to our scenario, because we're almost there. We found out what the velocity of this was. It was you know, the 2 radians per second. Well, we just found it out to be 10 radians, or 10 meters per second. That was going to be the velocity of this. Cool. So that means by definition, this one is going twice because this one's going 0. So this one's going 20 meters per second. And the angular momentum from the z-axis is the radius. That's going to be 5. So we have this r cross mv. We'll do one term at a time. We're going to do this one. So we're going to have 1 kilogram. Now times the velocity is 10 meters per second. We're going to add that to the same distance, 5 to this mass, 1 kilogram, and this is going 20 meters per second. Cool. So this is going to be 50. This is going to be 100. So we have 150. All right. Hell yeah. So okay. So that's going to be our value for angular momentum, 150. But now let's throw letters at it. So our, have another sheet of paper. Hell yeah. Z-axis, we have 2L, that's 2.5 meters. We have those 3 masses. This one's not moving, 10 meters per second and 20 meters per second. Angular momentum about the z-axis is going to be 2L. And let's write what angular momentum is again. It's a vector of a cross product of distance times mass times velocity. Cool. And again, so we can talk about this because I'm just saying these velocities are tangential, and then so if we do the right-hand rule, if we're going the distance that way, and then the velocity is tangential, well, hell yeah. In this case, our angular momentum is just you know, just straight up in the z-axis. Oh yeah, okay. So no duh, the component of the magnitude of the z component of the angular momentum. Yeah, I might even have this. Well, no. Yeah, if this is, yeah, that's like saying we have an x, y, and then the z's coming out of the page. You know what I mean? You know, and then we throw a wrench on this, Yeah, it's coming out of the page, and then here is our force on the wrench. Well, hell yeah. So, or I guess we'll do it this way. So here's our force on the wrench. Then the torque is in the z direction. This is the torque vector because you have this is your r cross f, and torque is equal to r cross f. And you're going in the direction of the radius, and then you're going that way with your force, and then up out of the page. So this direction, that direction, up out of the page is the direction of the torque, and that's going to be in the z direction. So hell yeah. So that fits our problem of you know, I mean, go in this direction out to these masses with velocity. That's the momentum. And the angular momentum will be in the z direction, and we're just bringing the whole problem down. So everything is in the z direction. That's how we're simplifying it. Okay, so we have 2 times L times the mass, and the mass is 4/3 m. Oh yeah, see, back here I just called these 1 kilogram masses again, and so yeah, that was dumb. That was dumb. So anyway, so our just using letters, so our mass of these 3 things is going to be 4/3 m, and the middle one is going to be going omega times the radius, which is 2a. Okay, now we're going to add it to this one, which is still 2L away, 4/3 m. Times omega, so we got 2 of them, and then omega times 2a. Okay, so this is going to be 8, 16. So this is 16 divided by 3, L, m, omega a. And then this one was 32. So this was 32 divided by 3, LM omega A. So yeah, we're getting the same thing. And so we got 48, 3 L omega, LM omega A. And, but yeah, we're doing this one. We're comparing it to that number. Okay, so now we have to figure out, they just have it in terms of A. So we're saying that L is 5, and it's not quite, but we're saying this is a square root of 25. That's our assumption. So L is 5A. So let's do 48 divided by 3 times 5A. That's it. Mass omega A. So right here, even these 3's and these 5's cancel, and look, we got 48 MWA squared. You know what I mean? 48 is very close to 55 MA squared. So even from, so finally, so I'm pretty satisfied that our 3 mass wheel, and I've had, that's the thing, it's like I'd want to spend, you know, a few days doing problems with a wheel and figuring out what the actual angular momentum of a wheel is. And holy hell, let's do that before we clean this up. And well, let's do it. So 48 times 5 divided by 3, and oh, that's not even close. Holy, 48 times 5 divided by 3. So we get a higher answer. We get 80 M A squared omega. So this is, I mean, it's but yeah, like I said, this is a true and false. I have no idea. You know what I mean, if this is a good representation. But I'm thinking like, hey, this is oh, this is interesting, because here's something that you could do that's very intuitive. Even though you have this wonk angle, and you're only going to have a component. So yeah, check this out. So if, yeah, and you have to do this, you know what I mean? So let's now figure out the angle, because this was the angular momentum, but it's in that direction. It was perpendicular to what we wanted. And it's actually perfectly legit. So what we did was perfectly legit. We just got it in that direction. So we just need the component. So we need to find this angle, and you know what I mean? To find this angle, how the hell do you do that? Okay, let's slow it down, and let's even, like, sometimes if you wig out about trigonometry, go back to 8th grade and be like, well, this is the hypotenuse, and this is one part, and this is one part, and so you know what I mean, just say sine of an angle is opposite over hypotenuse. So that's going to be A divided by H. Cool. And, you know what I mean? Hey, let's do cosine. Cosine. This is one way where you don't even need to know tangent. You know what I mean? Because here we don't know the hypotenuse. And it'd be cool if you knew tangent, because the trick way, the engineering way, is like you just have to memorize this equation. Hey, if this is my angle, sun is shining on this. So this is the sine and component, and you just need to know that tangent of an angle is sine theta divided by cosine theta. It's the sine in part divided by the cosine in part. So the inverse, the angle is inverse tangent of the sine part, A divided by L. And we're saying that, and we're still saying that L is 5A. So that's going to be 1/5, yeah, A divided by A. You know what I mean? So it's 1/5. So we have inverse tangent of 1 divided by 5 is our angle. So inverse tangent of 1 divided by 5. So our angle is 11, and it's pretty much like, yeah, like if this was 30 degrees, yeah, the cosine component, like I said, is just almost 100%. So the cosine of 11, so I'm going to store this as angle. So yeah, the cosine of our angle is literally 98%. So we just go 80 times 0.98, and this only comes down just a little bit, 78.4. Cool. So we know we can do that. We know once we, like, this angle is so almost meaningless because these distances are a lot farther. This is 5 and this is 1. So yeah, we have the inverse tangent of 1 divided by 5, and again, that's 11 degrees. I mean, if yeah. If this was 0.5 and this was 0.866, well, we'd have inverse tangent of 0.5 divided by 0.866, and you know what I mean. Hey, the angle's 30. So just, you know what I mean. Throwing a couple ones that you know is kind of a neat thing in your calculator, just to have a check on reality that you're doing it right. All right, but now I'm fairly confident I have a way to simply prove without knowing a whole lot, and not just doing the problem, because that's the thing, you know what I mean. I'm just pretending like this stuff is too complicated, and it probably is, you know what I mean. It really is. And if you just know the equation, who cares? No one cares that you know the equation. It's almost playing around with it and seeing what the masses are, seeing the momentum of each of the masses. That's more important, I think. Alright, hell yeah. But I think I spoke too soon, because we actually are going to say, well, what equations do we know? Like, we know if this is omega, and we know the moment, the mass moment of inertia, which is the second moment of mass. It basically takes a disk and say, hey, yeah, this mass, we get it, is this far away from the radius. So if this is the radius, hey, we know. You know, and this mass might be 1/25th of the total mass of 4m, you know what I mean? And then we have 25 of these little circles. And then you do it even more, you know what I mean? You break up this, you know, infinitely into littler chunks, and you want to know what, like how far all these are away. And that's where you take, you know, just to figure out what the hell's going on, you do a hoop. If I just have a steel pipe that I chopped into a slice, you know what I mean, I only have like an inch of it or something, like all the mass is on the perimeter, you know what I mean? So if I divvy this thing up into 1/10 the mass, you know what I mean, and then these are just a radius away, I can just say that, then what I want to know is the mass. So these are in kilograms. And I want to know the first moment of mass. You know what I mean? So I want to know. I want to have that distance term crossed into the mass term. You know what I mean? I want to have the radius times the mass, and hell yeah. And that's going to be just like distance times force. Even though you wouldn't write it like this because it looks like it's df. That is going to be torque. Well, this distance times mass is going to be the first moment of mass. And for a hoop, like, hey, let's pick that one. So we're going to have 1/10 the mass. Sorry, let's do the distance first. So we have the radius times 1/10 the mass. Cool, let's add up the next one. Plus the radius, 1/10 the mass. Okay, let's add up the next one. And you can see that you can factor out the r, and then we're going to have 1/10 plus 1/10. We're going to have that 10 times. So you're going to have 1/10 times 10, and now you're going to have, for this one, you're going to have r. Oh no, I apologize. I did this. Wait, did I do this wrong? I don't think so. No. Wait. R mr squared? Holy hell. Oh, whoa, is this term second moment of mass? No, my bad. Holy hell. So, yeah, you probably have to go back and then just, yeah, angular, I'm getting it confused with angular momentum. Angular momentum is the first moment that's the distance part, of momentum. And I think that's where it's going to get confusing, where you have an M term, first moment, that's going to be the distance part, and that's the first part, first moment of momentum. But my bad. Angular momentum is the second moment of mass. You know, still has nothing to do with any sort of velocity at all. You could care less about what you're just saying. Hey, I pick some mass and it's that distance away. But instead of saying the first moment, you know, this would be the first moment of mass. We don't want that. I is denoted as the second moment. So we're going to take that distance and we're going to, so it's r cross, I think it's just, ooh, is it just r squared? I don't even know how you would actually do, because is I a scalar? I don't think so, because the moment of inertia is about a particular axis. So if we have this axis, if this is our x, y, and our z-axis is coming out of the page, well, hell yeah, like, hey, you're crossing into that mass, and then, ooh, I don't know about this one at all. No, see, yeah, I don't even know. Is it just a scalar? Is second moment of mass, does it not have a direction? Oh, this is hella confusing. And if you did the cross product to this mass, like, well, where would you put the, like, the mass doesn't have a direction. Yeah, so the mass doesn't have a, the mass is not a vector. So it's a scalar component. Do you still call it second moment of mass? Oh, that's fascinating, because even an I-beam, I'll have to redo like a video on this. Because even with an I-beam, you say, hey, look at that area. Look at that area up there. That area is coming out of the board at you. So you have a distance here, and then you would say, like, hey, from this axis, you would go up D, and then the area is coming at you. So that would be that would be that way. Okay, so I think what they're saying is, like, I get it now. This is second moment of mass, but obviously this thing is rolling, and you're concerned at the perpendicular. You know what I mean? The direction of mass facing the perpendicular direction. So even right here on an I-beam, you're like, hey, look at that mass, it's facing us. So we go from our distance up to that area, and then this term for moment of inertia of an I-beam is d squared times a. And I guess you don't write it like that. I guess you do a d squared. So it's the and maybe you do write torque force times distance, and then yes, the moment part is on that side. So it's the moment of force. You know what I mean? This is the second moment of area. Yeah. So my bad about flipping those around too. But hell yeah. So second moment of area is you take the distance, you definitely square that distance, and then you go this way with it. But I just, as a vector, and so as a vector, this is going to be the vector r squared cross area. And it's the vector of the area. Area is coming out, and that's going to have a term along this axis, you know, maybe in that direction. Yeah, I've not thought about that, of second moment of area or second moment of mass being vectors. But I think they are. Especially if your angle is a wonky angle. I think they explain that in the text, that typically you try to treat this as a scalar, and just use it where you know you're going to use it. But yeah, I think it definitely can be a vector term. Alright, hell yeah. So let's use what we know now, because we know a disk. So for that hoop, for that hoop, you're going to have a term that's, the second moment of mass is going to be the mass times distance squared. And you're going to have r, so you're going to have mr squared. But for a disk, you know what I mean? I don't want to get into it. You don't have masses at the perimeter. Your masses are you know, only inside mostly, and not quite at the perimeter always. So for a disk, your moment is just 1/2 md squared. So if we know that, then we know this is our omega term, and what we say is oh, this is a bummer, because yeah, now I need to I can't use my scenario of just saying, hey, let's figure out these as tangential velocities. You know, each little mass, and this one's not moving, And yeah, so, but let's, okay, yeah, I guess I don't want to go this direction yet, you know, with the actual equation. What I want to do is do this. I want to say, hey, there's 1, 2, 3, 4 of these masses, and then a mass in the center. Cool. And what we know is that this mass isn't moving. This mass is going to be moving at 10 meters per second. We already know that. This mass is going to be moving at 20 meters per second. These masses, though, they're kind of interesting. So if we're rolling this way, this mass is going to have a tangential velocity up of 10 meters per second. You know what I mean? It's not multiplied because it's not at the top. And this mass will have a velocity down of 10 meters per second. But this will also, this whole system is rolling that way as well. So it'll also have a component that's 10 meters per second this way and this way. So and then you can see this is just like a right triangle. So it's the total vector is like that. And we know that to be the square root of 2, which is 1.4142, or just 1.41. 1.41, that's a multiple of 10. So these are going to be 14.1 meters per second. All right, hell yeah. So I took a big break, and that was totally necessary because, man, this problem is too much for me. But you know, we'll figure it out. We'll definitely figure it out. So what we want to do is we know that when we have a spinning disk, the angular momentum about the center of a spinning disk. This is the angular momentum is I omega. You know what I mean? And yep. And because it's perpendicular, we know it's I think like along the coming out of the page. I think, you know what I mean? Because we said if we had a mass up here, we were going to do the radius, and it was going to be, so it's either out of the page or into the page. So I think it's into the page this way. This is going to be the vector for angular momentum. But we know the second moment of mass, or the moment of inertia, or the mass moment of inertia, is going to be md squared. Oh, whoa. And then this distance is the radius for a disk or a circle. So we have mr squared. Okay, so this is going to be mr squared omega. And for all the problems up to this point, our omega is 10 radians per second. Our radius has always been 1. Our mass has been 1. So this will have an angular momentum of 10. Cool. So that's the angular momentum about the center. Holy Toledo. No. For a disk, it's 1/2. Sorry about that. So there you go. For a disk, it's 1/2 mr squared. So we have 1/2 mr squared. We have a radius of 1 meter, a mass. Oh, well, now in this issue, like how are we going to relate it? You know, because if we related it back to our problem where we said, hey, this was a circle, you know what I mean? We thought this was fairly representative of a disk. You know what I mean? Maybe it's not, because you know, we have 1 meter for radius, and here this mass would have a mass of 3 kilograms. So this is going to be 1/2 times 3 kilograms times 1 meter squared times 10. So the angular, and then if we just said this disk has a mass of 3 kilograms, now this, if we have a disk with a mass of 3 kilograms with a radius of 1 meter, then this is its actual angular momentum and an angular velocity of 10 radians per second. So this is going to be 30 divided by 2. You know what I mean? So 3 times 10 divided by 2, we get 15. So this is the actual, and this is going to be in kilograms, meters, squared per second. Now what I wanted to do was just compare it to this scenario. We said if this was spinning this way at 10 radians, we would have a tangential velocity of 10 meters per second. And we would have a tangential velocity this way of 10 meters per second. Now, this is where this isn't rolling. It's just a disk spinning around a pivot. And here, we were going to say the distance to here to there is... and then here, what we used was, we used the angular momentum is R cross MV. You know what I mean? So here, this, and then, so we need to figure out why this is the case for that scenario. And, all right. And then, so this was going to be, well, we have one of these that's 1 meter away. Its mass is 1, and its velocity is 10. And we got 2 of those, you know what I mean? So we have 10 plus 10. This one's going to be 20 kilograms meters squared per second. So this actually is an overshot of what's going on. This overshoots it. To actually figure out, like, this mass, if this was 1, 1, and 1, like, what would this mass need to be? You know, so that's another question. It'd be like, well, if we are going to represent a circle with 3 masses, 2 at the extreme and 1 in the center, you know, how do we make a quick equation to show that? Well, we're going to have a distance of 1 meter away. We're going to say, hey, we have some sort of mass. We don't know what that is. We're going to have this thing twice, so we're going to say we got 2 of these, and then we have the velocity, which is 1 radian per second. It's radians per second times radius. No, we got 10 radians per second, but the radius is 1 meter. So this is omega r. So here we go. So we have the distance. This is r cross m. That's the m term. And this is the velocity term, which is omega r. Okay, so we want to, and we got 2 of those. So right here we basically have 2m is equal to, and we need to equal it to this number, 15, because that's the actual number. So our mass is... oh, no, I'm sorry. This is 10, this is 2, so we're going to have 20m. 20m is equal to 15. So m, the mass of each of these, would have to be 15 divided by 20. That's 5 divided by, sorry, that's 3 divided by 4. That's 3 quarters. So we got 0.75 is the mass, or 3 quarters. Sorry, so yeah, in the mass. So we have 0.75, and if we're saying initially this is total of 3 kilograms, like that's what the actual mass is, or is that what we're doing? No, just each of these is 0.75 kilograms. And so if that's the case, if this is 0.75 kilograms, this is 0.75 kilograms, and this whole thing is 3, well, then this middle mass has got to be 1.5. And then that's what I thought in general, you know, I mean, even though I didn't spell it out with this, but, you know, because a circle is kind of bulbous in the middle. So, you know, I mean, in kind of a two-dimensional way. Because obviously, if you throw a mass out here, this might actually be more representative of a circle, but we just wanted to represent it with just 3. So yeah, that was kind of interesting. But yeah, so if we double the mass inside, so now we can represent any circle, I think, with like a 2 kilogram mass inside and then 1 kilogram at the extremes, and then we're going to set this at 10 radians per second. Now we're going to compare it to 1/2 4 kilograms times 1 meter squared times 10. Now this is going to be 40 divided by 2, it's 20. So this is going to be 20 kilograms meters squared per second. That's going to be the units on angular momentum. Whoops. Alright, so and then if we use our method down here of saying, well, hey, this one's going 10 meters per second, it's 1 meter away, this one's going 10 meters per second, so now we're going to have two of those. The distance is 1 meter. We're doing the mass. The mass of these is going to be 1 kilogram. And then the velocity is going to be radians, 10 radians per second times the radius of 1 meter. Cool. And that is going to equal 20. So cool, 20 kilograms meters squared per second. Nice. So hell yeah. I mean, this is what I would have done in just a whole video of just being like, hey, who knew that a circle, you know what I mean, just double the mass right here and then just have a mass, and you can kind of make a circle kind of in a linear line, and then it tips. So that's a pretty good representation of a mass, because now what we'll do is we'll go back over here and change this problem around to look like that. So I think that's the first thing that we gained from using this 1/2 mr squared term, knowing that this is 100% gospel truth. But even this 1/2, like, this would be a hell, I think it's a hard proof. I don't know, maybe there's ways to use calculus to figure it out. But how I would do it is I would model it, I mean, just one way to for sure know, I would model it in Excel, you know what I mean? I would take little chunks of mass, you know what I mean, and I don't know how I would fraction them, and then figure out their distance, and then we have an omega, so each of these would have a tangential velocity, and the ones on the outside would have a, you know, a velocity, or near the outside, because none of them, the center is actually on the radius. All the radiuses are just a little bit inside. But yeah, it just happens to be that it's just 1/2 mr squared, where if you had all the masses in a hoop, you know, on the outside, that's going to be 1/2, I mean, that's going to be mr squared. That's going to be your I term. So this is our I term, and then we multiply it by omega, and that's where we get the angular momentum term. Okay, so cool, man. So let's do that. Let's model this using that scenario and see if we get any closer. All right, hell yeah. So I'm almost at the point where I just want to give up, you know what I mean, just on doing the video, because like this is, I'm not teaching this well at all. I'm just kind of learning for myself. But I guess what I realize is that if you have a disk and you do that angular momentum is I omega, you know what I mean? Well, obviously the velocities, like the mass, are going to be chunks this way. The velocities are all going to be tangential, and then so you're going to get an angular momentum component in the direction of this disk. So if everything's spinning this way, the angular momentum component is actually pointed right at A. And then I was just like, well, does that mean that the angular momentum about point A is 0? And it's like, well, no, because you have two different things going on here. One is the spinning disk itself. That generates an angular momentum, I omega, through that point. I think that's kind of how it works. But you also just have, just in general, this disk moving that way. So like the center of mass of the disk is moving tangential. And so obviously that definitely causes a moment. The moment arm is this 2L, and you have a moment that direction. And that is associated with this this omega prime, you know what I mean, which is 1/5 this omega. So if this is 10 radians per second, which we've been saying, this is 2 radians per second. And then You know what I mean? Like, could we just get a general, you know, maybe we should just try to get a general gist of what that would be. Because if we, you know, if we have a mass of 1 and a mass of 5, you know what I mean? We have 4. If we have 4 kilograms and then 1 kilogram, well, where's the center of mass? It's oh yeah, this is interesting because this is a statics problem unto itself, and it's just like, you know, you might look up the equation for where the center of mass is, but you can think of it this way. So put it more, you know, kind of in the horizontal. So we're saying, hey, there's going to be a force on this of 4 kilograms times 10 meters per second squared. This would be, you know what I mean, 4m times g, 4mg, you know what I mean? That's the force. You know what I mean? I think we can agree with that. Force of gravity is mg, and this is 4mg. Cool. And then you get this one over here, which is just 1 mg. So we have 1 kilogram times 10 meters per second squared. So sweet, you got a force of 40 newtons here and a force of 10 newtons here. So now what you need to do is you need to find a way to balance these. And now, I mean, obviously, just somewhere you just need a 50 newton force, you know, because you're because this is how I do free body diagrams. Is like cut the darn thing and then just throw it into the deepest reaches of space. Because what we're trying to do is like, hey, some distance x, we're supposed to put a force to balance this. You know what I mean? Where 1, our observation, is that it's not moving that way, it's not moving that way, right? If we had a force net this way, we would be changing our velocity. But in this scenario, this is a statics problem. Our velocity is 0 and it maintains 0. The other thing that we don't see is we don't see any rotation on this. You know what I mean? Because if we had and this is an interesting one, because what I like to do is take it into the deepest reaches of space, put the known forces on it. Well, shoot, we got a 40 and a 10, so we must have to balance it with a 50. You know what I mean? So that's the obvious. But now we just don't know where to balance it so it doesn't start spinning. Because if we put the 50 Newton force right here, well, hell, this 10 newtons is going to make it spin that way. You know, if we put the 50 newtons force right here, you know, well, this 40 newtons is going to make it spin that way. You know, you'll have a torque. Okay, so that's where it brings up the equation of some of the moments are 0. And it's kind of interesting that you can take the moment about anywhere. So it's kind of like this thing in deep space, you put the force in the right location at some distance x, and it's just it's not moving up and down, left and right, but it's also not spinning. And so what I like to do is just imagine that you could theoretically put a thumbtack it anywhere, and it's not going to spin around that thumbtack. And that should be just obvious. If it's not going to spin, it's not going to spin. So you can pin it anywhere. So you can pin it at a point over here, and then be like, well, if I pin it over here, aren't these forces trying to turn it? You know what I mean? It looks like they are, but this force is also trying to turn it the opposite. So this force is trying to turn it this direction. This force is trying to turn it the opposite direction. And you can do that at any point. You can pin it right here, and same thing. This force is trying to spin it that way. This force is trying to spin it that way. And so we don't know what distance x this is. So I'm just going to say, for our problem, I'm just going to say this is 1 meter, and this will be L for our problem. Well, I guess for our problem it's 2.5. So there you go, 2.5 meters. So we said L was 2.5 meters, and that was a pretty good approximation. And yeah, so we're gonna sum the moments about this. We're gonna call this point A, this point B. So we're gonna sum the moments about point A. We're gonna say those are 0. So we're gonna have an upward torque of 50 newtons times x. Our distance x we don't know, and it's gonna be subtracted by a 10 Newton force at a distance of 2.5 meters. So this is equal to 0. So you could also set this up where you just said, hey, 50 newtons x is equal to 10 newtons 2.5 meters. You could just equal these, and that would make sense because, like, hey, this torque 50 times x is equal to this torque. You know what I mean? Thumbs down, thumbs up. So we have all right, so x is just going to be this divided by 50 newtons, and we get 1/5 of 2.5. So 1 divided by 5 times 2.5. We get 0.5 meters from this direction, from that direction. No, from the bigger mass. Oh, yeah, so we got 0.5 meters that way. So there you go. So 0.5 meters is where the center of mass is. So cool. So we solved one thing on it that's actually legit. Nice. And now we could we can maybe, like, I forget how you do. Well, yeah, because all the spinningness is towards O. So the magnitude of angular momentum of center of mass about the assembly. So I think it's just taking 5m. That's the mass. And we want to know the angular momentum, so let's get our angular momentum equation. That's R cross mv. So 5m is going to be our mass. Our distance is going to be L. Oh shoot. So yeah. So what is this distance? If this is 2.5 and that's 0.5, 0.5 divided by 2.5. Or basically this distance is 2, so 2 divided by 2.5. So we have 0.8 L. So we have L plus 0.8 L. So we got a distance of 1.8 L. Cool. So now we have our angular momentum about O is going to be 1.8 L. Our mass is going to be 4m. And then our velocity of that mass. Well, we know that the velocity of that mass is going to be omega prime times the radius of 1.8 L. And we know omega prime is 1/5 omega. And I apologize, we haven't solved this one, but I think this one is true. You know what I mean? So, because that was the first one that I solved in a different video, not attached to this video. So we haven't even done that one yet. But this is the easy one to do, and I probably should do it like right now. All right, but let's focus. So now we have so the tangential velocity is going to be radians times radius. That's going to be 1/5 omega times 1.8 L. And what's 1.8 as a fraction? That's 9/5. So we have 1/5 times 9/5. So that's going to give us 9/10. No, holy Toledo. Yeah, it's going to give us 9/25. So we have 9/25 omega L. So that's going to be our velocity. 1.8 times 1 divided by 5. And that's 9/25. Cool. So that's going to be our velocity component. We already have the mass at 4m, so we have 9/25 omega. Omega L. Omega L. All right. So let's see. And so it wants it in A. It wants it in A squared. So we know that L is equal to 5A. And so we can throw 5A in here. So we get 1.8, 5A, 4, 9/25 omega times 5A. And let's see what we get. You know what I mean? We got 1.8 times 5 times 4 times 9 divided by 25 times 5. Hell yeah. And we get 64.8 and that's 64.8 m, yeah, so there's m right there, m a squared omega. Cool. And again, I just don't even know if that's accurate, but I think up to this point I think that is. And I didn't. Oh man, I glanced at the solution. So the solution was 3 of these. 3 of these was true, 1 was not true. So I think I'm just going to guess that this. I think I'm pretty accurate on this. So this one is not true. If I'm playing my cards right, if we're saying, hey, the spinningness, the angular momentum of the disks rotating is going to put an angular momentum through this point, and that is just not how. Yeah, it would be like if we have these X, Y, and Z, and we have our nut, and our nut's kind of in the Z direction, and then we have our wrench up in the Y, and then we put a force on it, and we asked, what is the, yeah, well, let's see, what would this be like? Oh, yeah, this is pretty good. And then let's say I put like a, oh shoot. Yeah, I just want to pause on this and be like, sure, this might be right, not quite sure. Alright, hell yeah. So let's move on to at least D, you know what I mean? Because we thought we were going to do this right off the bat. So at least we know that tangential velocity of a disk, and if it's connected to the ground, its center of mass is going to travel. I mean, you're basically going to have this omega in radians per second, and then radians times the radius. It is, so 2a, so we have omega 2a. This is what it's going to spell out every second, you know what I mean? So it's going to, if the radians per second was 1, so if omega was 1, hey, like this is the radius, and this is the radius right here. So it's going to spell that out, you know, around this thing, you know what I mean, around this path. And it's going to do that in 1 second. You know what I mean? So it's just going to lay that path. So the tangential velocity, yeah, and that's kind of interesting. Is now is that a full proof? If I have a wheel, and well, let's do this. So I have a wheel. The radius, hopefully I've got enough. The radius is 1 meter. So that's the diameter of 2 meters, you know what I mean? So, and let's say, hey, we got a pretty good representation that's 1 meter. There's 2. 1, 2, 3, 4. And for our problem, we're just going to say, hey, if the diameter's to there, this is going to roll 3 diameters. So once it gets done rolling once, it's going to be over here. And the center of mass travels that distance. And this perimeter gets laid out, you know, radius per radius. So the radius goes 1, 2, 3, 4, 5, 6. You know, you're laying out 6 radiuses. And you know, for our problem, it should be 6.28 because that's 2 pi. But, you know, we're laying out 6 I don't know. It's like sometimes like this stuff gets me just all the time. You're just like, well, I can't even wrap my mind around a wheel. The fact that you're you know what I mean, you're rolling it, you're laying out linear distance with the perimeter, and that's going to be the same velocity as the center of mass. Like you know, you're laying out, you know, 1 meter. If this is 1 radian per second, if that's your angular velocity, you're laying out 1 radius per second. And so, yeah. And then it won't be a full revolution until you go 6, and this is 7, 5, until you go 6.28. So once you get to here, the whole thing will revolve 1 time. You know, so you're going to if you do 6 radians, you'll just get to here, but it won't be a full revolution. You'll have to go that 0.28 radians. So if this is my radius, that's half a radius. This is 0.28 a radius. But yeah, I think we got it spelled out. That, heck yeah. So 1 radian per second is going to, this is going to go to there in a second. It's going to, and then it's going to roll there. Yeah. So, and by the time it rolls 1 full circle, no duh. So if it actually just rolls to here, this distance from there to there is 1 radius. So yes, if it rolls to here, your center of mass rolls, holy hell, I don't know why that was so complicated. But yeah, so it's just interesting. So if you have an omega, the center of mass, the tangential velocity of the center of the circle is going to be omega, is just going to be omega, radians times radius, and the radius is 2a. Whew, that was brutal. Okay, so now once we get this, that we have omega times 2a, now we need to figure out what the, and we're going to call this omega prime. So omega prime is going to be, let's spell this out. Radians times radius is tangential velocity. So if I want to go the other way around and find radians per second, I'm going to say radians is equal to tangential velocity divided by radius. Cool. So if I want to know this omega prime, I'm going to take this velocity tangential, omega 2a, and then I'm going to have to divide it by this distance. Cool. But I don't know what that distance is. Yep. And yeah, it is interesting. Yeah, 'cause I need the oh, you know what I mean? And I don't even think I did the problem that way. You know, I don't care about the center of mass. What I was interested in was just the fact that because it works 2 ways, you know what I mean? If we just said this is laying down track at one radius per second, and then the center of mass is going to be the same, well then here we can look at this and be like, well, what is this laying down? It's laying down track at this linear distance is going to be you know, if this is 1 radian per second, you're going to lay down 2a every 1 second. Now, if this is 10 radians per second, you're going to do 10 times 2a every 1 second. So you're going to lay down this this distance with the formula omega, you know what I mean, the velocity of a, you know what I mean, something going around this path is going to be omega times 2a. Perfect. Omega 2a. And that's the same thing. So it's just fascinating that was a struggle for me. The fact that this speed on the ground is omega 2a, which is the same speed as the center of mass. Cool. But you know, because circles or wheels are weird because, like, hey, this actual particle is not moving, but we're talking about the, you know, the laying down of the track, you know what I mean, the actual movement of the wheel itself, you know. And then, so what I'm going to do is draw this full circle, and so now we can actually get this distance. Once we know this distance, that will be our radius, you know, for this omega, because now we can say omega prime, or this thing, is going to be that velocity tangential divided by this radius. You know, this equation right here, velocity tangential divided by r prime. I'm just going to call this r prime, and 2a will be r. Heck yeah. Holy hell. Okay, sweet. And we know that we can find this just using Pythagorean's theorem. Here's a right triangle. This is 2L. And then this is 2A. So we're going to have, it's going to be A squared. So we have A squared plus B squared is equal to C squared. This is going to be our C squared term. We're just interested in C, or this C is going to be R prime, which is going to be the square root of A squared plus B squared. Okay, so hell yeah, that's going to be this term squared. So we have 2A squared plus 2L squared. And then the square root of that's going to be R prime. Cool. So let's just do it over here. This is going to be 4A squared plus 4L squared. You know what I mean? Anytime you have a product, you can do this. 2 squared, A squared, plus 2 squared, L squared. Hell yeah. All right. And the same thing here. If we take the, well, maybe we can. Now we definitely need to use this little thing. So what do we want? At the end of the day, well, I have no idea. Like, our tangential velocity is in terms of A. So yeah, let's get everything in terms of A. So we're going to throw in square root of 24, A for this term. So we're going to say this is 4A squared plus 4 square root of 24A. And then this is squared. You know what I mean? So if we had to break this, I mean, just the two things in here are squared. So we're going to have the 24 squared, A squared. Obviously, the square root of 24 squared, this is just going to be 24A squared. Cool. Times 4, which is going to be 80. Oh, 24 goes to basically 50, goes to 100, 96. Hell yeah. So now we have 96A squared plus 4A squared. Hell yeah. That's why you're supposed to be able to do this one in 5 minutes. Everything is kind of a little bit nice. But this is going to be 100A squared. Alright, and then when you take the square root of that, it's the same thing as taking the square root of 100 and the square root of A squared. So you're going to get 10A. Hell yeah. So that's going to be that. That's going to be 10A. Our radius is 10A. And does that make sense? You know what I mean? Hey, if this is 2, this is 1A. 1, 2, 3, 4, 5, 6, 7, 8. Sure, whatever. You know what I mean? It might not be drawn to scale. Alright, so we have 10A. That's that radius right there. And, man, this is really hard. Okay, omega prime is that velocity tangential. That's omega times 2A, and now we're dividing it by 10A. Hell yeah. And what do we see? A's cancel, and we get 2 divided by 10, which is 1/5, which is omega divided by 5. So that is the angular velocity for there, and that is a check on reality. Man, and I've already done that once, but, you know what I mean? If I look back on this, yeah, I'm glad I doubled down on that little setup, of just like, hey, I really don't know how wheels work. You know what I mean? What's the speed of a wheel? So we did that, and man, and then this was the one that I was just gonna do a short video on. So yeah, maybe I'll just end it right here. And thanks for joining me on this one. And hell yeah, that's a video. All right, hell yeah. Now I'm not pumped up, but I think I have enough steam to hopefully finish this out. We'll see. But yeah, I watched a video, and it just makes me question. It's just like, why the hell am I watching? Why the hell am I making videos if other people are just covering the same stuff? You know what I mean? So obviously it's the method. You know what I mean? It's why I won't just solve the problem at hand with the letters. You know what I mean? I want to know as much foundation. Well, what is it called? Fundamentals. You know what I mean? Proofs. You know what I mean? I need to know in my mind, like, what the hell's going on. So so what we're gonna do is, because we have two different things here. You know what I mean? If we have a wheel that's rolling, you know what I mean, and we're just gonna say, hey, there's no contact point with the ground, but we're just gonna call that point A. If I want to know the angular momentum about point A, there's a thing called the parallel axis theorem. So we're gonna do something, same 10 radians per second. We're gonna do a radius of 1 meter, And, you know what I mean? Hey, and what do we have for, is it just 1 kilogram? You know what I mean? 2 point, kind of a, for how big that is, it's a pretty lightweight wheel. Anyway, so, and now, so we have this omega. We know that for a disk, 1/2 mr squared, this is the second moment of mass, the mass moment of inertia of a disk. You know what I mean? It's not a hoop where all the mass is on the outside. That's mr squared. You know what I mean? That is the definition of mass moment of inertia. You have a chunk of mass out at the hoop, and it's the distance, and we're just going to square it. That's the second moment part. Cool. All right. So and I'm so glad. You know what I mean? Even in this problem, this is such a prerequisite for this problem, and I don't know, what do they say? It goes without saying. Anyway, yeah, this after I watched a video, you know what I mean, the person explained it in a hell more technical jargon, but it's just like, huh, you know what I mean? Like, you have to prove to yourself that a rolling wheel, you know what I mean, lays out track, you know what I mean? And that velocity that it lays that track out is the same velocity of the center of mass. So that's kind of fascinating. Yep. Cool. And that's how we solved that one. But anyway, so back to this. If we want to know the angular momentum from this point, you have to use the parallel axis theorem. You know what I mean? You basically have to take the angular momentum about the center, and then you're going to say, hey, this point is a distance of 1 radius away, and then so you know what I mean? It's this md squared term. You know what I mean? Hey, here's the distance. So we have you know, the mass of the wheel times r squared. So we're gonna basically, and holy hell. And this is obviously multiplied by an omega. Oh, okay, yeah. So now I don't know if it's the moment, the moment of mass. Oh, that's fascinating. It's just this term they're talking about. So I think it comes down to, hey, the moment of inertia of the center of mass is mr, or 1/2 mr squared for a disk. But if we take the moment about point I, so the second moment of mass, and it doesn't have anything to do with the omega, you know what I mean? We're just saying, so now that we're saying, whoa, like this mass, this chunk of mass is 2 radiuses away. You know what I mean? So that would be a video that I would prove in Excel, is like, well, if we do shift this point, you know what I mean, like, it is, you know what I mean, and we take, you know, this mass is that far away, this mass is now that far away. When we were at the radius, this mass was just there, and this mass was there. So anyway, but the parallel axis theorem says, hey, it's just it's the moment of mass, the second moment of mass, from the origin. You know, typically what you'd get for you know, those values you just look up. We know them for disks, and they're going to be about the center of mass, plus the mass times the distance squared. Cool. And then, so you could think about it in 2 ways, though. You know what I mean? Because we said this is we said the moment, the angular momentum about A is the angular momentum about the center of mass plus plus this md squared term omega. You know what I mean? So and then this term is I omega. You know what I mean? So there's, if we separate, if we like factor out an omega, the angular velocity, we get I of the center of mass plus md squared. So you could think about the angular momentum also in terms of this parallel axis theorem, is like, hey, it's the momentum about the center, and then with the parallel axis, theorem to that location. And I guess the only caveat or caution about the parallel axis theorem comes in its name. You have to move parallel, or you know what I mean. So if right here, if we're about this axis, you know what I mean, we do the right hand rule. Hey, some of this mass is moving, yeah, never mind. If we're just doing mass moment of inertia, you know what I mean, hey, we're just going up over here. We're moving in this plane. So if we're moving from the center, we're moving to the plane. You know what I mean, hey, this disc doesn't have a chunk of steel, you know what I mean, welded to it over here, where now we're not moving. You know what I mean, we'd be moving that way, and then so here we'd be moving at these angles to get to that mass, and here we're moving in a different plane. See, this plane is different than that plane for figuring that one out. But here with a circle, if we're about the center, hey, we're going over there, we're going over there, and so we're still in that plane. If we take it from the center of mass, we're still, hey, taking this mass from that distance, this mass from that distance. So there you go. We're still in that plane, and the value that we get, if this is omega, and we're saying, hey, the mass in this direction, the tangential direction, the velocity direction of that mass, because that's kind of that's the only thing that makes this a scalar, is the fact that the moment of inertia, this I term, is perpendicular. Is that right? You know, am I saying that right? Is I omega itself also a vector quantity? You know what I mean? Is it a dot product? Yeah, that's interesting. I mean, could we figure out if it? I think it is a dot product. I mean, let's take a moment. Okay, because what we're saying is hey, this is the distance r, and this is a chunk of mass m, and then it has some velocity. Cool. And we're saying that angular momentum is that distance cross product with mv. You know what I mean? Mass doesn't change, or your mass doesn't have a direction. You know what I mean? So that's the only thing that doesn't have a vector. But your velocity does, and your radius does. And it just happens to be when these are 90. Hell yeah, that's the definition of a cross product. You get that moment of mass times velocity, moment of momentum. You know what I mean? So it's angular momentum is moment of momentum, or moment of linear momentum. Cool. And that is going to be perpendicular, and it's in the same shoot. I don't know if you'd call it in the same direction. It's in the same plane as omega. Yeah, it's definitely. But if we say omega is its own vector, you know what I mean? So let's draw this again. So we're going to go up to here with an r. We're going to go there's the velocity tangential. Here is the chunk of mass. But if we do put an omega on here, you know what I mean? Hey, the omega has a right-hand rule too, so it's in plane with. I mean, I shouldn't draw these in 3 dimensions. I'm thinking that's into the board, but we could just say behind this is down into the board, and so it's going to rotate this way. And then so we do, well, I guess let's just throw a vector. So there's the vector into the board of omega. And now you have, okay, but this cross product is going to be also the distance. So if we're taking it from this point, we're going to be going up and then this direction. So we are also into the board. You know what I mean? So this angular momentum is in the same direction as the angular velocity. You know what I mean? So these vectors are totally parallel, and so it can't be a cross product. What the hell am I saying? I omega. Yeah. So if we do this, we have radius, mass, and then velocity is omega times radius. And if we just rearrange, then we have r squared m, or I'm sorry, we have mr squared omega, and this term is I. Oh yeah. So this is the oh, funny. Okay, so here is the vector L, or angular momentum, and it's the it is yeah. It is the magnitude of this multiplication. It's I omega. Like it is, but it's only when this is at 90 degrees. I think if you had something that, yeah, I forget, if it's like asymmetric, then this is not, this has components. This would, this is this a vector where you have a second moment of mass because you have a radius? That's the only thing, is the only thing that I want to learn from this is like this moment of inertia. It's the second moment of mass. It's mass times the distance squared. Now like if it's the yeah. Now, if this is the chunk of mass, and then this is my distance, do I take it to be a 90-degree angle? Just as yeah, that's bothersome to me. Or is it just the yeah? It seems like that is the how am I saying this? Yeah, no, this is because you have a, yeah, can you take a cross product of radius and mass and then square this? You know what I mean? I know mass isn't a vector. Yeah, that's the only thing. That's like literally the only question I have from this whole deal of learning about about vectors. It's just interesting when some things like this is obviously a vector. It comes up all the time as a vector. And then a cross product of the vector, hey, you know what I mean, just like the wrench, you put a force and a distance, and then you're you know what I mean, into the page where that bolt is, it is your direction of torque. You know what I mean? Torque is synonymous with that axis. So that's the direction of the vector when you do put a distance. So there's your distance vector, there's your force vector, and then into the page is your torque vector. Alright, hell yeah. So I want to finish up with the angular momentum of a disk, because that seems really important to this problem, because we got a disk and then at an angle. But anyway, so the angular momentum of a disk. Well, I guess. Well, do we have two things? Yes, and we do. We have two things. So if we just have a disk that's spinning, you know what I mean, not touching the ground, we can still take the angular momentum about point A. And so we're going to give an omega, that's 10. We're going to give a radius, that's 1. And we're going to give it a mass, obviously that's 1 kilogram. That's kind of what, that was our MO for this whole problem. Or for, this whole series. Cool. So we're going to say the second moment of mass is going to be the mass times the distance squared. And then just for a disk, you know what I mean, we just know this. It's not a hoop, and so it's a 1/2 just by defining it. You know what I mean? Somebody else derived this, you know what I mean, in either a calculus way or like a analytical way, throwing it into an Excel and chopping it up into a billion bits. Anyway, so we have 1/2 mr squared, and cool. And then if we say, so yeah, we can just do it a couple ways. We could say, hey, what's the angular momentum about, no, not angular momentum. What's the second moment of mass, or moment of inertia? That's also what this is called, mass moment of inertia. It just sucks that it's got 3 terms. That's why I think I'm going to continue calling it the second moment of mass. You know what I mean? And it's going to be the parallel axis. You know what I mean? We take I/O, and then we got, you know what I mean, the mass d squared. And here's the d. So there you go. So we're going to have we're going to have this IO plus md squared, and that's going to be 1/2 mr squared plus mr squared. Cool. So this is the crux of the whole spinning disk problem, taking the moment of inertia about you know, the contact point. And I don't even think it matters whether this thing's spinning and not rolling, or I thought it did. No, it does. It does. Yeah. But if it's not rolling, then this is your term. And then so that's your term that we're going to use, and this becomes 3/2 mr squared. Now we're not done, because we need to find the angular momentum, which is, you know, r cross mv. And I always start here because, you know, you can kind of see the masses where they are. But yeah, this is where I would like to get, on most problems, some sort of just overall understanding of what masses have velocity, you know what I mean, and what distance they are away, and yeah, so there you go. But we also know this equation to be I omega, you know what I mean? Who cares, I guess. And so, yeah, I'm just saying who cares at that point, because you might lose all sort of intuition for the problem the second you cross from here to there. You know what I mean? And it's just a bummer, you know what I mean? We should be doing 100 or 1,000 different tiny problems that spell out on a daily why this is 1/2 mr squared. You know what I mean? And that's what I'm doing right now. You know what I mean? That's the problem that I'm doing, not even this problem. And hopefully we get something cool out of it. All right, so here's my I term, and then there's an omega. So this just becomes 3/2 mr squared omega. This is the angular momentum of a disk. Now, if the disk is rolling on the ground, then the angular momentum is, I think it goes like this. It's the angular momentum of about A of its spin, you know what I mean, of the spinning part, plus the angular momentum oh yeah, this is bizarre. This is just the angular momentum of the center of mass. This is why I think I got really close to this. You know, just from an intuitive perspective, I was just like, well, what's the angular momentum of the center of mass? Well, it's just like all this spinny stuff is going through O. You know what I mean? So you know what I mean, none of it really counts because it's all directed through. So, you know, it's like if you have that wrench, you're just, and you put a force this way or you put a force this way. Hey, those aren't wrenching motions, you know what I mean? So none of that counts. But then you have some other, you know what I mean, force prime that does count. So that's the same thing when we do angular momentum is r cross mv. It's the first moment of momentum, you know what I mean? So mass times velocity is momentum. It's the first moment of it. So then we can say, well, it's kind of a bizarre thing, but you just say, hey, well, let's say just all the mass is about at the center, and then it's moving tangentially that direction. Cool. So now we have that distance. And that's where we didn't get 81. We got something less. So I'm just going to say, hey, this is the actual angular momentum about center of mass is less than 81. I'm going to say this one is the untrue one. If we got that one right, I have no idea. Like, I just, you know, it's unfortunate that you can't pull these without, like, just glancing. And I think 3 of these are true, and then 1 is not true. That's all I know, you know what I mean? And for sure I know D is true. Cool. All right, so yeah, but I thought this was very fascinating. And so for the momentum, it's just R cross MV. And, you know, you go up your distance, that's the radius. You pick your mass, that's the mass of the whole thing. You know what I mean? So for our problem, that's going to be 5m. And then you pick your velocity. You know what I mean? The velocity of this is the tangential velocity. And for this problem, that was, you know what I mean, more or less just this distance. Yeah, no, it was this distance. If you're taking about point A, it was literally just that distance. That was L. that was 2.5 plus 1.8, you know, or whatever it was. I don't know if we actually solved that one 100%, but I think we got close enough. Because, yeah, we just said this was 25, like 5A. L was 5A. And then we just moved on with life. Anyway, so, but yeah, this part of momentum is just that tangential velocity taking all the mass about the center, which is bizarre, but it's going in that direction. So that is the only thing that drives the momentum about this point A. So that's kind of fascinating, because all the other momentum aims right at it. And same thing with the z-axis. Oh, you know what? I think these two questions answer themselves. Because if you take the magnitude of angular momentum about the center of mass, about point O, I think you get this answer. You know what I mean? You get, let's say you did. Let's say you got 55. And then why would that be true? Well, we just showed that, hey, like all this spinny stuff, it's a vector. You know what I mean? This mass is moving. Sure, this chunk of mass is moving that way. It's a distance that way. But as a vector, as a cross product, hey, that angular momentum, L, is a vector and it's going this direction. And it not only goes through O, but it points directly at the z-axis. You know what I mean? So none of it is you know, just like a force, just like this could be opening a door. You know what I mean? Hey, this is a doorknob. This force opens a door. You can't open a door with a force that way and a force that way. You know what I mean? So that means that all the spinny stuff is just a shadow for this supposed to be a 5-minute problem or whatever. All right, hell yeah. So and that's the take-home point of, like, you know what I mean? That's where my question is very, very satisfying. It's just like when we do this equation, when we do the second moment of mass, when we say, because I know what area is. Like, we already know that for an I-beam. I just don't know it for rotation. The only thing I know about rotation is, like, well, hey, let's say this is coming, like if we have an omega this way, hard to see, but let's say we are rotating about this, and this is coming at us. This chunk of area is coming at us, and so we're going to say, hey, these chunks of mass are coming up out of the page at us, and so that would be the direction. So if we did the right-hand rule, we'd go up to those masses, and then we would go this way. So we would have a second moment of, so if this was a vector, and I think it is, second moment of mass for this one, and how should we define this? Should we define this as the x and the y, and then the z's coming at us? For those masses, we would have a second moment of mass in the x-axis. You know what I mean? So that would be the component. Or if we said the vector on that, it would be this chunk of mass times, I'll just say distance, and then we're going to distance square it, and that's going to be I hat, you know, because x is I hat, j is j hat, I mean y is j hat in the z direction, you know, x, y, z is k hat. Alright, hell yeah, some more juice in the camera. And yeah, so that's interesting. So this shows that the angular momentum of this disc that's not rolling is going to be less. It's just the parallel axis theorem to get that I times the omega. Okay, but we do the same thing here. You use the parallel axis theorem to get that I at that point A. But then you also add, for the angular momentum, you also add that term, you know what I mean, hey, this center of mass has a velocity of the center of mass. Okay, so that's very fascinating. And I think we're done with this, because I'll save maybe this. If I can answer the problem now, I'm going to save this for other videos, because what I want to do is see if my stick figure for a circle, you know what I mean, like how can we make it better? And yep, and I don't think well, shouldn't I be able to do that just like right now? Holy hell! So we're gonna say this has an omega. the center, and this is 2 kilograms, this is 1 and 1. You know what I mean? That's kind of the stick figure I was going for a 4 kilogram circle. 10 radians per second, 1 meter on the radiuses. So the angular momentum about A of this object is going to be the angular momentum about the origin. So that is going to be, and we have and you could do it in two ways. You could also say it's the angular momentum. It's the second moment of mass. So you could find the second moment of mass about the origin, do the parallel axis theorem to get it to IA right there, and then just multiply by omega. You know what I mean? So like that's the easiest. Or you could say, okay, but yeah, that's just one component of it, and then you're going to you're going to use oh man, yeah. So yeah, well, I guess let's do it the easy way. So the angular momentum about the second moment of mass about the origin. Well, that's just the distance squared to the mass. So our distance is squared is just going to be 1. So it's literally just the mass. This is 2 kilograms. So this value is just going to be 2 plus 2. And then should we do it 100%? This is mass distance squared, md squared. And our distance is 1. You know, to this one, we're going to have 2 kilograms times 1 meter squared. And then to this one, we're going to have plus 2 kilograms, 1 meter squared. You know what I mean? There is no distance to this mass in the center. That's, oh, and hell. You know what I mean? Whoops. So this mass in the center is 2 kilograms. These on the end are 1 kilogram. Now, I don't even think that's what we did for our problem, actually. So I actually need to take a step back. Alright, hell yeah. Yeah, I have to totally take a step back because we were saying these were 0.75, 1.5, and 0.75. Oh, yeah, but we just say, yeah, we could do a 1, 2, 1. Sweet, so we're good there. And why we can do that is because I of O is 1/2 mr squared. That's from the textbook. And if we say, hey, this circle that we have is a 4 kilograms, so we have 1/2 times 4 kilograms times 1 meter squared, hey, we're going to get 2. So we're going to get 2 kilograms meter squared, yeah, that's a kilograms meter squared, second moment of mass. So that value is 2, and then when we just did it, where did we do it? You know what I mean? We had, the mass was 1 kilogram, so that's where I had to apologize, because we just have 1 kilogram times 1 meter squared plus 1 kilogram times 1 meter. So that is equal to 2. So that is basically, we wanted to make an object that was chill with this 1/2 mr squared, and this object is chill with that. But if we start rolling this object, it definitely needs to be chill with this term, the fact that the angular momentum about right here, the angular momentum of a circle about the contact point is 3/2 mr squared omega, and that we do not know if we are chill. So I guess okay, cool. And yeah, this should be so easy, but man, it's just making my head spin. Okay, so we found so yeah, we're chill here to get this 2, but now we got to use parallel axis theorem. So we got to do 2 plus md squared. The mass is the total mass of the whole thing, so that's plus 4 kilograms, and we're moving a distance of 1 meter squared. So cool. For this, we're going to have 6. So now this is IA. And does that jive with a circle of a mass of 4 kilograms? Because if we have a circle with a mass of 4 kilograms, IA is 3/2 mr squared, which is 3/2 times 4 kilograms times 1 meter squared. And I don't think this is going to jive, because this will be 2 times 3. This would be 6. No, that does jive. Sweet. So we're 100% correct. I'm digging this. You know what I mean? This is my favorite part about rotational stuff, is making problems simpler. And most people don't. You know what I mean? They just use the equations. And most people have an understanding of what the hell the equations are. But when you're teaching it to other people who do not have an understanding of what the equations are, you know what I mean? Nah, like you have to be professor level status to actually know what's going on. Or you could use the equation, sure, but you're not going to gain like what the hell? You know what I mean? That's what I think I can do. Not in this, not today. You know what I mean? This is like, I was thinking about titling this video. You know what I mean? I bet you can solve this problem faster than watching this video. You know, something like that. It's just like, hey, make it a challenge. Like, try to solve this problem before this video ends. You know what I mean? That would be pretty cool. All right, but we got one more thing. So that was just a check on the second moment of mass using the parallel axis theorem for a disk about the contact point. So that's useful because if we want to find the angular momentum of a disk, that's IA omega. But then we got to say, hey, well, we also have to do the distance r times the mass times the velocity. So we also have the d plus d times the total mass of the thing times the velocity. But we know velocity tangential is that something. You know, it's radians per second times radius is something normal. You know what I mean? So we do know. Damn it! All right, hell yeah. So we're back. So we do know we can write this in terms of we know d is the radius. So we got radius times mass times velocity. Mass times velocity is mass omega r. So cool. So this thing is r squared m omega, and then you can see that this term is like the parallel axis theorem. It's still, hey, it's the mass times the distance squared omega, or maybe it just happens to be. I don't know if that would be on every problem, but it is on this one where you're just adding another mr squared omega. You know what I mean? So that is fascinating. Yeah, that's weird. Yeah, it's as if, but that's not the point. You know what I mean? The point is to get the angular momentum about point A using the parallel axis theorem. We're saying angular momentum about point A is IA, which is using the parallel axis theorem, times omega. So this is I naught plus md squared. You know what I mean? That's where that term goes. But then, you know, that's just for a disk pinned to a wall. But like, hey, this is rolling, so we need another term, and that's the angular momentum of the center of mass from point A. You know what I mean? So that's going to be the radius times the whole mass of the whole damn thing, and then times the velocity. You know what I mean? So, you know, the angular momentum is r cross mv, and it just happens that v is r omega. So there you go. Yep. And yeah. All right, cool. I'm just thinking like just how omega could be a vector. You know what I mean? It could be in this direction and a little bit in that direction. You could have a and then you still want to get the angular momentum about. Yeah, that'd be interesting. I don't know. But, okay, so where are we going to go from here? So we want to figure out our little thing of 3. And so I don't mind breaking out some paper to do that. All right, so we know that the angular momentum of a disk about point A is IA omega plus what? Plus just the angular momentum, r cross mv, just r times mv, you know what I mean? And you don't even need to cross price. Perfectly 90 degrees. So there you go. This is a velocity tangential, and the distance is straight up. So you don't have to do a cross product. It's just the multiplication of that. But this is also Rm omega r, which is also mr squared omega. So cool. And then this is going to be IO plus md squared, the parallel axis theorem, times omega. Okay. And for our little thing, you know, I mean, could we still do it just from scratch? We have, and then the definition of second moment of mass is mass distance squared. Cool. Or just like mr squared. Cool. So we have this mass, a distance of 1. So yeah. So we have 1 kilogram, 1 kilogram. So this is going to be 2. Plus this is going to be 4 times 1. So there you go. This is going to be 4. And now we have omega. We know that's 10. Cool. But now we're going to add it to the total mass, which is 4, times the radius, which is 1 omega. So cool. So now we have 10 omega. And what we want to know, that's for our object of 3. We want to know if that's the same thing for a spinning disk. So a spinning disk, we're going to have the IO term. That's going to be 1/2 mr squared. Plus this term is going to be md squared. And then that's omega. Plus the actual velocity of the center of mass. This is where it gets kind of tricky, because the velocity of the center of mass, this is where, like, hey, this disk lays out. This disk is laying out linear distance. With this omega, the linear distance that's getting laid out is the tangential velocity if the disk was just pinned and not rolling. And that tangential velocity is omega times r. And that tangential velocity is the velocity when it is rolling of the center of mass. You know what I mean? That was the hardest thing to explain, and you know, I want to make a bunch of videos on that to get better at explaining it. I don't think that's super intuitive. It's kind of bizarre. It's like when I bike, yeah, hell yeah. If I want to get my speedometer dialed in, you know what I mean? The wheel goes past the magnet every time. You know what I mean? And then I know the circumference of my wheel. So every rotation, that circumference lays out that amount of track. So that is linear distance. And it just sucks that we have to work with radians, but it is the same thing. You're laying out a distance of radiuses every second. And that is linear motion, you know what I mean? And so, hell yeah, the velocity of the center mass is just omega r. So cool. So when we go to find out RMV, it's just it's just another mr squared omega. So I think we proved that. And now we can throw in for our problem, just for the disk, because we want to compare it to 10 omega. So we have 1/2, and we're going to say 4 for the mass, 1 squared, plus 4. The distance is 1 squared. Cool, so what is this? This is 4, and this is going to be 2. Hell yeah, so we're good there, like we thought. That term we double-checked already. But how about this term? Now we have 4 times 1 omega. Hell yeah, so we have 10 omega. So I think this is the coolest thing that I won't make official videos, you know, until this problem is done. But man, the fact that a circle is a spinning disk, or a rolling circle, a rolling disc, a wheel, you know what I mean, can be like, hey, it's where the center is, you know what I mean, twice the outsides. So if we have 2 kilograms here, 1 kilogram there, 1 kilogram there, we can model this as a perfect, simplistic example of a rolling disc. You know what I mean? So I think that's cool, because I'm going to use this to simplify a lot of problems. You know what I mean? Because if you had this problem and you just had a chunk of mass there, a chunk of mass there, it would probably get more confusing. No one, and then this would be double. No one definitely would know what the hell to do. All right, so now I think. Well, let's check out this. I think this is the only one that I have no idea. The magnitude of angular momentum of this assembly about its center of mass. Holy hell. Okay, but the same thing, you know what I mean? If I'm trying to find, yeah, this is fascinating. Because anytime that you're taking the angular momentum about, you know, we already said the angular momentum of center of mass, the angular momentum of center of mass of the assembly about point O, like, well, that was an obvious one, but the z component of the angular momentum, well, it's just like, well, all this stuff has a momentum vector that points towards O, points towards z. The only component is the fact that the center of mass is the center of mass of both of these are moving tangential. You know what I mean? So M1 and this is the only thing that's causing angular momentum. Like, so if we did angular momentum about point O, those are the ones that are causing it. There's a 90-degree angle there, so it's literally just the distance times this chunk of mass velocity. So this would be mvt, and this would be 4mvt. And obviously this would be vt prime because it's different, and this would be a faster tangential velocity. This is going to be omega prime times that distance r prime, and this is going to be omega prime times, I guess, the whole distance we're calling r. All right, hell yeah. So yeah, but yeah, these are the magnitude of angular momentum about the center of mass. Yeah, this kind of trips me out. But if we're about the center of mass, again, all these things that are spinning are putting the vector for angular momentum through that point. So those don't count. So we have to figure out what else counts. So then we would say, well, we do have, if we're just taking an instant, like an instant point, like about right there, then we know that this velocity is going that direction. So we can say, you know, we have a distance this way. So we have a radius, and then we have a mass, the center of mass, or the total mass, basically the center of mass, and then we have that velocity tangential. So it's the same thing that we did about point O, you know what I mean? And if we did it about point O, that's where we could figure this about point Z. How you would do it about point Z is that you would just need this distance. So you would have to take, and then this is the one that I wanted to figure out, because if this is A, this triangle is different, right? You know, that's the only thing I couldn't figure out about this problem. Is just like, well, it's like, you know, here's your components. This is one component. This is the other. This is the hypotenuse here, and then you're saying, yeah, this is a tricky trigonometry one, where this component right here is the hypotenuse for these components. And I probably will end this video really doubling down on the geometry, because for this problem you don't want to use angles. You want to use you want to figure out your hypotenuse in terms of Pythagorean's theorem. We know that this is L and this is A. So you would figure out the hypotenuse being the square root of L squared plus A squared. We just did that, and we actually get a term. And if that's the hypotenuse right here, then we use this value for the hypotenuse to find components. So vector components. Because if I have, let's see, yeah, let's say I do have an angular component L of the angular momentum in this direction, and I want to know, yeah, so I could easily find this perpendicular component. Oh, how does this work out? Oh, damn it. Oh no, I think we're about there. Yeah, the angular momentum about O doesn't mean that the vector Yeah. So the angular, so if we go this distance times this tangential velocity of that mass, we're going to get a vector that's perpendicular. That's going to be our vector about O. It's going to be in that direction. And then if we want to figure out what the magnitude of that is in the z direction, then we know this hypotenuse, and maybe we know this side. So let's say this side is A, this side is B. And so what we would do, and this is just, I'm doing a horrible job, but is that you would just take the magnitude of that angular momentum that you found kind of easily, which was this one, the magnitude of angular momentum at the center of mass about point, holy Toledo, yeah, I need to take a break. Alright, hell yeah. So I took a little break, but we definitely have to move on from this concept of, but if we know this vector, let's say it's 100, and we know this component is, the hypotenuse is 10, and this is going to be like 8, and this is going to be, the 3, 4, 5 triangle, this is going to be 6. Well, then we know the component in this direction, let's say that that's the direction we wanted to find it in, then we would just say that component is 8 divided by 10 divided by the hypotenuse. So if we get some sort of term for the hypotenuse, even in terms of A and L and whatever, or an omega, with an R and a mass, then we can say, hey, what's the ratio? Well, you can just take no, never mind. Like these would be directions. So this would be in terms of A. You'd have some number in terms of A as your hypotenuse, and then you would divide it by a smaller number in terms of A, your length of B, and then so that ratio is going to be. That's why you're not going to find angles and then say the sun is shining on the sine or the cosine. You're not going to find the cosine components for this problem. You're just going to use hypotenuse and then the as a length term, and then you divide it by your other length terms to get that. So anyway, so I think we're going to move on from that. And hell yeah. So I think, I don't know, so I think I can solve, I think I can do this. The magnitude of angular momentum of the assembly about its center of mass. You know what I mean? And should we do the center of mass again? We have, 4 mg, and then we have 1 mg. And now we want to put a force of 5 mg up. And we're going to go some distance from like that direction. And so the torque is going to be 5x equal to, this is L, equal to L. So x is equal to 1/5 L. So there you go. So and I guess we can just use that term. So we're going to be over here 1/5 L. So that means this is going to be 4/5 L, and this total distance would be 9/5 L if we wanted to do that. But if this is the center of mass, there you go. So we have 1/5 L and then 4/5 L, and now we know that this tangential, well, we know the center of mass is 4m, but the velocity tangential is going to be this omega prime times this, this is interesting, because this, so we found, and the center of mass of the assembly rotates about the z-axis with an angular speed of omega. Yeah, the whole thing, the center of mass, anything along this rod, which is the center of mass, or is that true or not? No, is it just the center of mass? Holy Toledo, I think that's another principle of like, now for this problem, if this is the center of mass, you're laying out the track, you have an omega, and then so the center of mass moves with a tangential velocity, just the same as if you pin this wheel to a wall, spun it, and then you would figure out that, hey, this is your velocity tangential, which is omega r. These are going to be the same. The velocity of the center mass is going to be, if the wheel was just spinning from a fixed position, but then But then how about any other point on here? You know what I mean? Because this point's going to be double. Velocity of the tangential. The tangential velocity is going to be 2 times velocity tangential. Here's not moving at all. And so, yeah, so we do have this kind of unique relationship where, like I'm saying the track speed. The track speed is the tangential velocity. That's going to be omega times this radius. That's what I thought we solved for. You know what I mean? This was this was the hypotenuse, and we solved that for the radius, and then we got that number. You know what I mean? And that's how we knew that this angular speed was 1/5, or omega divided by 5. So that was the check. But yeah, now, and then from that, can we say that this point also moves with the tangential? I don't think you can, actually. It feels like you can't. Oh, yeah. No, you can say that every how should I say this? Yeah. Every point along this center, you know what I mean, and you know, because the track that this lays out isn't connected. Like, this point is literally not moving. It's just it's kind of like that almost seems fictitious to me. But it's not a point. It's not a point on the wheel that's moving that direction. It's just the track speed of a wheel. But the center of the wheel is moving with omega prime, but we don't know its tangential velocity. To get its tangential velocity, and we know it's moving about this z-axis. Because of this track speed, because the track is on the ground, and we found that track speed, the omega is the direction of this omega prime is in the z-axis. And then, so if we wanted to find the tangential velocity, we would have to go over to these points. And that's where I just thought it gets a little bit geometrically difficult. Because now I know my hypotenuse, but I don't necessarily know this vertical height. Ugh. So that's kind of a bummer there. And but I guess don't I know something about these triangles? Like, does that make these triangles related? You know, I mean, do you need to know something about how triangles are related for this one? Man. Alright, hell yeah. You know, I didn't take too much of a break, but let's play around with this. You know what I mean? Let's say we got a 3, 4, 5 triangle. You know what I mean? So we got 4, 3, and then 5. And then, so we got 1, 2, 3, and then we got 4, and then we got 1, 2, 3, 4, 5. Now, and then we do another triangle off here that's, now how would we do that? So, if this was the 3, and this was the 4, and this was the 5, how this is working is now it's saying, hey, the 4 is going to be, you know what I mean? So, and I guess I'll just go this direction. Is that how it went? Oh yeah, let's draw it like they have it. So we have 1, 2, 3, 4. So that's our 4. And then we have 1, 2, 3. So that's our 3. This is going to be the 5. Oh, did I not? Oh, damn it. I feel like I didn't draw that very well. Let's come down here. So we got 1, 2, 3. Oh, yeah. I didn't make that 4 anyway. 1, 2, 3, 4. So we got 4 there. That's what I didn't do. Cool. And then we got a 5. So it kind of looks similar to that. We just didn't put this down on the flat. So maybe we should do that. So we got 1, 2, 3, 4, 5, 6. That's 1, 2, 3, 4, 5. And then we're going to go up. Because these things are what has to be 90. And that's kind of hard to do. 1, 2, 3. 1, 2, 3, 4. I wish I had a ruler. 1, 2, 3. 1, 2, 3, 4. Yeah, so something like that. So you have a 3, 4, 5 triangle. There's 5. There's 3. And then there's 4. And then what they did is say that this is the hypotenuse 4. So that doesn't do us too much good for a 3, 4, 5 triangle. So, well, let's see. So this has a hypotenuse of 5, this is 3, and this is 4. So now we have a hypotenuse that's only 4. Okay, so this has to be dimensionally less, right? Because now if we say this is 4, and then we're going up at a right angle, and then just across, I don't know if this gives us any information at all. That's kind of interesting. No, but I think we got it. So let's find this angle, and we can say this angle is inverse tangent 3, 4, 3 divided by 4. So sweet. I'm going to store that as alpha. Then 90 minus that angle is this angle. That's 53. So if I knew the hypotenuse, and then I wanted to know the sine component, I say sine of this phi, I'm going to call this phi, that's 53, I'm going to store it as alpha w, and sine of phi is going to be this opposite, divided by the hypotenuse. Okay, so then that means the opposite is going to be, and I should have known that. If I know the hypotenuse, hell yeah, the sine, yeah, the opposite part is just h hypotenuse sine phi. So we're going to have 4 sine phi. So we got 4 sine w, and this is going to be 3.2. Cool. So if that's 3.2, then this, a lot of ways you could do it. You could do 4 squared minus 3.2 squared, square root that. This is 2.4. And is this a 3, 4, 5? You know what I mean? So if we did, how do we get this to be 3? So 2.4 times what is equal to 3? That's going to be 3 divided by 2.4. Cool. So that's what we're going to multiply it by this, and we're going to do. We're gonna multiply everything by 3 divided by 2.4. So 3 divided by 2.4. Store that as x. We got 2.4x. That's 3. 3.2x. That's 4. Holy Toledo. Yeah. So it is the same. So there is that ratio. Man, you know, this stuff, I have to spend like a whole day learning. You know what I mean? So that's where this problem sucks, because you do need this distance. You could just guess. You know what I mean? You could just guess, but you really want to figure out exactly, I think. All right, so hell yeah. So how do we incorporate the fact that, like, what's the ratio here? Like, cause like I know my hypotenuse now, and I know my sides. So how do I find? So yeah. So how do I work backwards and find just that one? You know what I mean? So what would I do to work backwards to find this one? I would say, I have no idea. Let's see. Oh yeah, so we do have ratios here, you know what I mean? Hey, like this divided by the hypotenuse is a ratio. So we have 3/5. That's going to be the ratio between that and the hypotenuse. You know, the shorter side and the hypotenuse is going to have a ratio of 3/5. So the shorter side, so maybe we should go back and figure out what the hell the hypotenuse was. I totally forgot in space to do that. So we have, you know, 2a squared times L squared. We're going to add those together, take the square root. L squared was 24a, so we're going to have 24a squared plus 4, 4a. No, what the hell was this? Yeah, 2a squared. That's going to be 4a squared. Yep, so then, well, 24, you're going to have 30, 38. How did I mess this up? So we have 2L. This is a 90-degree angle. So a squared plus b squared is equal to c squared. So a squared plus b squared square root of it. So we have a squared, which is 2a squared. That's going to be 4a squared. I just kind of want to do this fast. And then we have, oh, 2 times L. Yeah, no duh. So yeah, that's going to be 2 times L is going to be times 2. So if we square this, that's going to be 4 times 24. Yeah, that's 96, duh. 96a squared. And then we get 100. Yeah. So there you go. We got 100, and then we take the square root of it as 10a. Yeah, so I remember that. I just couldn't, I couldn't figure it out. So hell yeah. So even just right here, 10a, this is 2a, 10a, and this, you know what I mean? I don't think you, I think you just want to keep it as L, 2L. This is 2L. Because that's not going to be a nice number. That's for sure. That's going to be 2 square roots of 24a. Cool. Okay, so this side is going to have a ratio of 2a divided by 10a, which is 1/5. So the shorter side to the hypotenuse will be a ratio of 1/5. So now we can say the shorter side right here, I'm just going to call b. The ratio between b and the hypotenuse, which we know, which is 2L, is 1/5. And cool. So now we can say that b is 2L divided by 5. And hell yeah, so I think we got b. That's 2L divided by 5. Okay, perfect. So now this makes sense. And now we have a ratio between 10a. No, I'm sorry. We have a ratio between this one. So we have a ratio between 4 divided by 5L. Is that right? Oh, that's a bummer. No. 2. Which one did we just do? We did 2a. This side divided by the hypotenuse would be this side b divided by the hypotenuse, which was 2L. Cool. We really wanted to find this length c. And so I guess by this little demo, and let's try it out. You know what I mean? Because let's say I didn't know this 3.2, but I see that the longer side, 4 divided by 5, is a ratio, and between this longer side and the hypotenuse. Okay, but now I know my hypotenuse is 4, and wait, the ratio between the longer side and the hypotenuse is 4 divided by 5. Cool. So what I know is that the longer side is this opposite. So I'm going to say opposite divided by 4. This has to be a ratio of 4/5. Okay, so let's solve for the hypotenuse. The opposite is 16 divided by 5. Is that what we get? 16 divided by 5? And we get 3.2. Holy hell. Yeah, that see, stuff like that just melts my brain. But at least I know how to set up something similar. See, this has been doing this for a couple months. It's like, hey, find the simplest problem you can do that you could be like a total check on reality. And then work backwards to see what the equation was, and then we can do it. So man, let's grab some new sheets. Okay, so hell yeah. So this is going to be 10A. This is 2L. I'm just going to write 2L so I don't forget. Now we're going to draw a triangle right here that has a hypotenuse. We really just want this distance C, let's call it. And so we're going to say C divided by 2L. Just get that ratio right off the bat. Is the longer side divided by the hypotenuse. That is going to be this longer side 10A divided by, no, damn it. It's going to be the longer side, which is 2L, divided by the hypotenuse, which is 10A. Okay. So, yeah. This longer side divided by the hypotenuse is this longer side 2L divided by the hypotenuse. These ratios should be the same, so we can say C is 4L squared divided by 10A. Cool. Hell yeah. So this should actually get us something fairly decent, because this is 24, like L squared is going to be just 24A squared. And then times 4, that's that 96, divided by 10A. So we're going to get 96A. Holy hell. Alright, so is that length? You know what I mean? Is it 96A? I don't think it is. Yeah, I guarantee it's not. Yeah, well, how did we just do this and it made sense and then we got to here? So if I know my hypotenuse and then I know the longer side, is that what we have? I know my hypotenuse, I know my longer side. It is a ratio of 4 divided by 5. I don't know my opposite, but my opposite is my longer side, and I'm going to divide it by the new hypotenuse. And then I'm going to solve for that, yep. So, well, why didn't I write it like this first? So the longer side is 2L. So cool. 2L is the longer side divided by the hypotenuse, which is 10A, is equal to C, which is the longer side, divided by the hypotenuse, which is 2L. So, yeah, and that jives with, you know, this 4 popping up twice. I don't know the opposite, and this 4 pops up twice. And then so we say this this opposite is 2L squared. And let's do this. It's 2L times 2L. That's going to be 4L squared. Yeah, I thought we did this. So we got C is 4L squared divided by 10A. L is the square root of 24A. We're going to square it. And then divided by 10A. So this becomes 4 times 24. A squared divided... Oh, did I not divide by 10? Holy hell. Yeah, I didn't divide by 10. No duh. So I got 96. I didn't divide by 10. So it's 9.6A. Okay, yeah, there we go. Alright, so yeah, we figured it out. 96A squared divided by 10A. Didn't divide by 10. And we got 9.6A. Alright, well, I'm glad I double-checked that. Whew. Okay, so yeah, we're on a roll because now we found out what that was, you know, and that's useful because now we can find our tangential velocity. We can say this omega prime is 1/5 omega, and omega times our radius is velocity tangential, and so for this term, Oh, and then our angular velocity component about the z-axis. I think we're just doing that one. So the angular momentum is going to be this 4 mass times the tangential velocity, which is omega prime, times c, which is 1/5 omega times 9.6 a. Yeah, that's a bummer that didn't clean up. I mean, were they expecting it to not clean up? Huh. Yeah, I hope I didn't just do it wrong. I don't think so. Alright, so that's going to be the tangential velocity component. Angular momentum is the radius. That's going to be that c times mass times velocity. So we just found the velocity, and then we know the mass. The mass is 4m. And see how this c term comes up twice? We just included it right there. Oh, so there you go. That's not going to help us though. No, 9.6 squared. Yeah, I don't know why that term doesn't come out nice. It seems like it would. I don't think I'm doing anything wrong. But whatever. Yeah, that's a bummer. Okay, so angular momentum is, you know what I mean? And then, so the fast way for this is just I omega, which is, and then I is mass mr squared omega prime. And that's going to be mc squared 1/5 omega. So that is going to be the angular momentum for that one. But then for this one, I guess we're just going to have half of c. So we're going to have m half of c squared, and then just 1m. This is 4m. Sorry about that. So we got 4m. You know, just in general, it's the mass. You know, this is generalized. But we have 4mc. Yeah, so maybe we should keep this as 96a divided by 10, just in case something cool happens and it comes out a little bit nicer. Okay, so this is going to be 1/2 c, but then we got to square it, and then we're going to add it to 4m. Oh, we haven't done everything, and then multiply by 1/5 omega. So sweet. So if we just factor out the 1/5 omega, then we're gonna have and I guess we can factor out the m, because this is just 1, but this is 4. Yeah, did I do everything right? That's the omega prime. That's the r squared. And yep, so now you're just going to have 1/2 c squared plus c squared. Cool. So this is going to be 1/4 c squared plus c squared. So it's going to be 5/4 c squared. Cool. And c is 96a divided by 10. So we're going to have 1/5 omega mass 5/4 times 96 divided by 10 times a. That squared. Okay, we're going to square it again. That didn't really help us though. Okay, and then yeah, that got a little confusing. Hopefully I didn't make big mistakes. Alright, so and then we got that. You know what I mean? How the hell are you supposed to do this without a calculator? You know what I mean? Maybe you're supposed to have a calculator. I have no idea. But the 5 will cancel. This 96 is 4 times 24. You know what I mean? So the 4 cancels. Cool. And now we have 24 squared. You know, we have 24 squared. 24 squared divided by 100. And we get 5.76. Huh. Yeah, let's try to do that one more time, because that seemed like it didn't work. All right, and what we should do is just be like, well, you know what I mean? Let's just guess. Let's just assume this is 5a and this is 10a, and then just totally just get on with life. So and then we have an omega prime of 1/5 omega. So we're basically going to have angular momentum is radius times momentum, mass velocity. And we know that's going to be r times mass omega r. So yeah, so I guess angular momentum is going to be mass radius squared omega. And so for this first term, we're going to have one mass. The radius is going to be 5a squared, so it's going to be 25a squared. And then omega. Plus the second one is going to be 4 times the mass times 100 squared. So it's going to be 100a squared omega. Now the omega is omega prime for that. So we're going to divide by 5. So yeah, keep that in mind. Because now we're going to divide. You know, this is going to divide by 5. This is going to divide by 5. So we're going to just have 5 over here. So this is 5ma squared omega, you know what I mean, adding up to that. And then this is going to be 20 times 4, which is 80. So the 5, you know what I mean, 100 divided by 5 is 20, times 4 is 80. So now we'll have, if we just guessed, we would have 5 plus 80. We would have 85 ma squared omega. And they get 55. And I just don't think this little extra is going to do anything. I mean, just this little less distance is actually gonna make a difference. All right, so let's try this one more time using this 9.6a, you know what I mean, as our C value. So we have this one is, so we have this idea that this is I omega, that's mr squared omega. This is going to be omega prime, so we're going to have 1/5 mr squared omega. Cool. So for this one, we're going to have 1/5 m. There's just one of them. The radius is 9.6 squared a squared. Oh, but it's, damn it, this one's definitely divided by 2. So 9.6 divided by 2 squared, and then omega plus 1/5. You know, then times 4m. 9.6 squared a squared. So let's do this one. So we have 1/5, 1 divided by 5, times 9.6 divided by 2 squared. Okay, plus 1 divided by 5 times 4 times 9.6 squared. All right, and so this gives us 78.336. So I'm going to say this one is not true. You know what I mean? I think we've proved that this is actually the actual answer to that one. And I'm going to say that one's not true. Sweet. So we got this one to be true, this one to be not true. And I think we should now be able to figure out the other two fairly easily. Alright, hell yeah. So we got a new sheet of paper. And, well, let's do this one about the center of mass. You know what I mean? If we didn't already forget how far away those things were. You know, what wasn't this 1/5? Yeah. So your center of mass was 1/5 L, and then we had 4/5 L. And now, is this going to be right? The only, yeah, that's the only one that's kind of bizarre to me. You know what I mean? Is it the, well, yeah, this is fascinating. The angular momentum of the assembly about its center of mass. Because it seems like if we have a spinning disk, you know what I mean, the angular momentum about the center is I omega, you know what I mean. That's the angular momentum about the center of mass of a spinning disk. Now that's a vector that so yeah, damn it, that's the thing I don't get. So when we take the angular momentum about point O, isn't the angular momentum about the spinning disk, yeah, is it relevant? Yeah, that's the only thing. I have no idea. You know what I mean? I would assume that the spinning disk itself, the angular momentum, is in that direction. And it's a vector in that direction. Just like, hey, the angular momentum of this point is in the z direction. If this is x, y, and it's coming out of the board, this is the z direction. That is the direction of the angular momentum vector. It is just all k hat. Oh, this is bizarre. Oh, okay. Yeah. And man. Oh, but it's like different than yeah, I'm getting this kind of confused. So, like if I was torquing a bolt, and then the vector was into the page, and then here's the distance vector. I wouldn't say, oh, my vector is in line with the bolt, therefore it's not useful. No, this torque is extremely useful. It's the definition of useful torque. You know what I mean? Hey, the torque vector, and I think that's like sometimes these get double arrows just to make sure it's not a force vector. You know, it's a torque vector, and hell yeah. So if I go up to a door, and then here's the hinges, and then I see that someone has applied a torque vector in the direction of those hinges, I'm going to be like, hell yeah, and guess what? The door is going to open this way. You know what I mean? So, yeah. So that's all. I wanted to leave this problem, you know, just not being dumber and not being confused. You know what I mean? So if I do have this idea that the angular momentum vector is pointing in this direction, then that's a useful quantity. To me, that's like a double arrow quantity, and it's along this line. Yeah, that's interesting. And then so, you know, if I said, hey, this is along this line and this is the point O, well, what's the torque about point O? Well, it's the torque vector that we just found and is going through the torque vector itself is going through point O. So yeah, that's fascinating. That I guess I just didn't really understand. You know, I was thinking like this was a force vector. If you have a force that's directed at point O, your hinge, well, that's not going to do anything. So if I have a force directed at this hinge, that's not going to provide a torque. If I have a force directed at the hinge this direction, that's not going to provide a torque. Yep. Even if this force is at the door right here, it's a distance away, but the cross product, there's no cross product, you know what I mean, for that distance. Hey, the distance is that vector, and then these vectors are in line with each other, you know what I mean, so there is no 90, and there's even no component that is tangential. And it's cool, because the reason I caught my error on this is like, yeah, cool, I choose the center of mass here. Well, guess what? You know, I go down to this chunk of mass. Sure, it's not moving. You know what I mean? But then, you know what I mean? I go up to this chunk of mass, and hell yeah, it's moving. It's moving tangentially. You know what I mean? 2 times the actual velocity of this disk. And if I go to here, to that chunk of mass, this chunk of mass is moving that velocity. And then go over here, you know, same thing. This is moving with 2v vt prime. This is not moving. yeah, so that's fascinating. I just, that was the hardest thing about this problem, is just like, I don't get what the usefulness of these terms are, or even just how to calculate angular momentum about the center of mass. Yeah. I mean, yeah, that's what got me on a disk, and I was just like, oh, holy, I'm totally wrong, because, yeah, there is an angular momentum about the center of mass. Just because the angular momentum vector goes through the center of mass, it's because, hey, this is your distance vector, hey, this is your mass, and then this is your velocity vector. So there's your distance, your r cross v, and then you will have, and it's going to be in this direction. You know what I mean? So that is the component. And so this component is going to be real big, and guess what? It's downward, but you'll still have a component in the z direction of this. Alright, I think I want to take a huge break from this problem. Holy hell. Alright, hell yeah. So it's the second day, you know what I mean? And we're just going to continue plugging on with this problem. Now, I did, after turning off the camera yesterday, I was able to, you know what I mean, kind of tackle it just from a not explanation point. Like, that's the hardest thing about this, is like, you know, talking into the camera of what I'm doing, and then, you know, maybe making, you know, just horrible graphic errors. But I think there's 5 questions here, you know what I mean? You could break this down into 5 questions. It says, given the setup, the angular momentum about point O, you know what I mean? They just say that's L. So we could answer that first. What's the total angular momentum about point L? Okay, cool. And then you have you know, question A, B, C, D. A says the angular momentum about the center of mass. Cool. And then B says the z component of the angular momentum. So if we find the total angular momentum, you know, and it's going some direction, we can figure out the z component of it. It's just going to be, I mean, if we find that the angular momentum is going that way at point O, then the z component will just be less, and it'll be that fraction less, you know what I mean, using vectors. Cool. And then C says the magnitude of angular momentum of the center of mass. So this one's very particular. It says just the angular, what's the angular momentum of the center of mass, you know, of the assembly about point O. Like nothing else. Just the fact that the center of mass is moving like that direction. And then so in our problem, this is omega, and then what I'm going to state is that this is omega prime. I've already solved D. D says that the center of mass, basically everything along this shaft, the center of mass is going to be 1/5 L, 4/5 L of this dimension L. Center of mass is basically right there. And that's going to have an omega of omega prime, and that's going to be 1/5 omega. Cool. All right, so that's the setup. So now we can just solve for the total angular momentum about point O. You know what I mean? And if we just do the equations, you know what I mean? Hopefully it just spells itself out. It's a cross product between the distance of O crossed with mass times velocity. Now, and for this problem, we're definitely going to need. I'm actually gonna kind of make this nice and crisp because we need to kind of figure out this rectangle right here. And this wasn't something that I went over. Like, I was going over similar triangles, and I was just like, oh, well, these have to be similar. You know what I mean? And I was just like, I didn't know why. And the reason why is like, hey, if you call this angle theta, you know, anytime that you have two parallel lines, you know what I mean, and then you do this Zorro, you know what I mean? Anytime you get like the Zorro, well, hell yeah, this is, you know, that same angle. You know what I mean? So things to look for is just like, hell yeah, those two angles are the same. Okay, but you do have something kind of unique with this triangle, is that this is the hypotenuse down here. And this is L, so, you know what I mean? We figured out what the hypotenuse was by doing the, you know, a squared plus b squared. I mean, basically, you're using Pythagorean's theorem. And we're just going to dole this out. Even if I have to repeat myself 1,000 times and this video is 20 hours long, I just do not care. I want to, you know what I mean, make sure that when I get to the spot that seems difficult, I just want it to be a layup for me. All right. And so we use that. What we're trying to find right here is the hypotenuse. And so you can solve for the hypotenuse. That's just a squared plus b squared square root. And in our case, a squared is 2a. So we're going to have, you know, once we square this, we're going to have 4a squared. I think we can agree with that. And then once we square this, we're going to have, this is 2l. So once we square 2l, we're going to get 4l squared. I think we can agree with that. Cool. And so plus 4l squared. Now, L is square root of 24a. If we square this, I think we can agree that we get 24a squared. Cool. So we're gonna, this is going to be 4 times 24a squared. Cool. And this is going to be that 96. You know, so I'm just going to cross this out and do 96a squared. So we can see that this, and this all has to be square rooted. Yeah, so we get that 100a squared, we square root it, and we get 10a. So this term right here is 10a. Hell yeah. But then, and then, cool. And then we were able to figure out, like, these distances. And how did we do that? I showed it with, like, a 3, 4, 5 triangle. But I think one way to do is just remove the a values for this. So we're just going to say this is a value of 10. And this length is a value of 2. And now we can figure out what this length is. And we don't even have to use a's or l's no more. You know, I mean, we already have these numbers. So this is the hypotenuse. If we wanted to find this length, and I guess we know what it is in terms. It's just going to be 2. It's going to be 2 times this. So we got 2 square root of 24. So, and I'm going to store that as, well, what should we do? AB. I'm going to store that as alpha B. So this is going to be 9.798. I'll just go to 3 decimal places, but we'll have this stored in our calculator as alpha B. So now from here we can say that there's a relationship between the longer, I'm going to call this the longer side, this is the shorter side, and this is the hypotenuse. So the ratio between the longer side and the hypotenuse, so I'll just say, and I'm just going to call that L. And I'm going to store that as L. So this is going to be the longer side. That's going to be B in my calculator divided by 10. So we have alpha B divided by 10, and I'm going to store that as alpha L. And yeah, and we know about vectors. Like if this is like 100%, you know, if I say this length is 10, well, look at this. It's almost 10. It's almost, you know what I mean? It's 98% 10. You know what I mean? If we took 10 and then 98% of that, that's going to be like, look at this. It's literally the same length. That's because this angle is about 11. You know what I mean? And we can even find that. This angle is the inverse tangent of opposite over hypotenuse. So inverse tangent of 2 divided by 10. Now this is the stuff I probably got to stop doing. You know what I mean? We already went over that, but we do. This is a new. This is a new element to what we're doing, is we're finding the ratio of this longer length, we're calling it S, is B divided by 10. So we have alpha B divided by 10, and we get, and I'm going to store that as alpha. I probably already did that. Holy Toledo. So, and this is always going to be, anytime you're doing a ratio between one of the sides and the hypotenuse, again, it's like sine cosine stuff. This number is always going to be between 0 and 1. And it's, so it's 0.979, I'll go one more. So there you go. So and this is going to be stored as L in my calculator. And now we're going to do the shorter side S. And that's going to be 2 divided by 10. That's real easy. So that's just 2 divided by 10. That's 1/5. 1 divided by 5 is 0.2. And I'm going to store that as S in my calculator. So now we have the ratio of the longer side to the shorter side. Hell yeah. You know, yeah. And this is the ratio. So how does this work? If I know the hypotenuse, I multiply by the hypotenuse times this ratio, and hell yeah, I get this. You know what I mean? If I do 10 times alpha L, hell yeah, I get this 9.78. If I do 10 times alpha S, I get 2. You know what I mean? So sometimes this is heady for a lot of people, though. You know what I mean? So yeah. So I have the ratio, and the ratio is cool. That's like the sine cosine. If I want to know if this is the angle, sun is shining on the sine, and this is the cosine, because here's the right angle, here's the hypotenuse. I want to know this length. Well, I'm going to take cosine of this angle times the hypotenuse. And that's exactly what we did. So this value for L, for the longer side, is the cosine. This is the sine component. And so maybe that is just visually easier. It'd be like, oh, well, if I have an angle, well, hell yeah, the sine component is going to be, and I know my hypotenuse now. You know what I mean? So in this regard, I know that this is going to be sine. I take the sine of this angle, which is the shorter one. It's going to be 0.2 times this hypotenuse. Hell yeah, and I get this side. So now I need to. This is the shorter. I'm going to say this is alpha t. So we're going to store this as alpha t, and then the longer side, I'm going to come up here and store this as alpha. We'll go alpha m, just because it's consecutive. This is you know, the longer side is L, and then M for the long. Anyway, so how would I find t? Well, I'm going to take the hypotenuse, which is b, times the ratio of the smaller angle. You know what I mean? Which is 0.2. So I'm going to take b times s, and this is going to be this 9.798 times this 0.2. So cool. So alpha b times alpha s, and we said we're going to store that as alpha t. So now this one is going to be 1.95, and it's going to be 1.95a. You know what I mean? Because these I just got rid of the a's just for a second, just to actually get the ratios. You know what I mean? But we definitely have to throw this a term back in, and so this is going to be 1.996a, and then this m term is going to be the hypotenuse, which is alpha b times alpha l, this component of the longer side. And this one comes out just spot on 9.6, so that's kind of cool. This is just 9.6a, and this is probably the one that we'll use for our problems. Okay, so hell yeah, so we did it. And I think that was, like, for me to do this, like, 100% in my mind, just to make it make sense, I definitely think that was something that I needed to do. Now from here, I'm going to try out my little axiom. And you might just hate this, because you're just like, why don't you just solve the problem? You know what I mean? Well, we could, but we're going to try to do it two ways. So, kind of my axiom, if you have a circle, I kind of proved earlier in the video, I guess, that you can take a spinning disc and treat it like it's 3 sets of masses, 1 in the center, and then 2 on the outside, where the one in the middle is going to be twice the outside. So if this is a total mass of like m, we're just maybe call that like 1 kilogram, or just like 1 m, you know what I mean? Well, you're going to have, this one's going to be a quarter, this one's going to be a quarter m, and then this one's going to be a half m. And then here, if we're splitting up 4, hell yeah, this is going to be 2m, 1m, and then 1m. Alright, and so why we do this is because it can be more visually understandable about what momentum is. Angular momentum says, hey, I have a chunk of mass, and it's moving that way. Cool. You know, we're going to multiply those two things together, and then I'm going to multiply it by the distance away from the point that's happening. Cool. The only one caveat is like, hey, it only gets to multiply because I'm going to say, like, I'm just going to do this, like this is the tangential velocity tangential, if this angle is 90. So if I'm going up from O, and then I get to here, and this velocity is 90 degrees, well, hell yeah, then I can multiply those two together. But it's the right-hand rule. My hands go from this distance, the cross product, go up through here, and then if I shove my fingers into the velocity vector, and that is a 90, cool, I get to multiply both numbers 100%. But that gives me a vector that's perpendicular. So this is what I also wanted to just try to make the problem as kind of clean as possible. Okay, so we're just going to draw this line right there. So hell yeah. So if I go to this one, this is the vector that I'm going to get. Cool. And for the sake of this problem, I do need to do one at a 90. You know what I mean? And this is cool because I actually can explain components. And other people can explain this just in probably about 3 sentences, but we slow roll. Okay, but yeah, so we're going to get all of that. We're going to multiply this distance times this mass and its velocity tangential, and that is going to give us a quantity of angular momentum. Now, it's just going to be in this direction, and I'm going to do double arrows for angular momentum. Cool. And this one is only in that direction, but we are just, you know, hold on for a second. We are going to get one in here. Now, these masses down here, because we have a rolling wheel, these are not moving. These are totally stationary at any instant that they're actually touching the ground. And I think it's because, you know what I mean? And then let's just spell it out. But this velocity, well, we're going to try to keep these parallel. This velocity is twice. So we're going to say this is 2 this velocity tangential. We're going to kind of do the same thing here. We're just going to call this VT prime, and then this 2 VT prime. So twice this. Okay, hell yeah. So now we can actually start. There is going to be something funky on these ones because we're not just going, you know, if we do the right-hand rule, we're actually going this direction, and then the velocity might not be at a 90-degree angle. You know what I mean? So we kind of have to figure out what we want to do with that one. And damn it, I thought I had it spelled out, but we'll see if I run it. Just looking at this at a tilted angle is kind of wonky. All right, hell yeah. So let's at least do, and we'll do the ones out here. Well, no, we'll work from here to the outside. Cool. So this first, this mass isn't moving. So in our equation, we can take a distance to it, but then when we go to multiply the mass times the velocity, this has no velocity. So it has no angular momentum component. And again, angular momentum is just, hey, we find a mass and it's got some sort of velocity, and we take the distance to that. But the only caveat is those have to be, the distance and the velocities have to be perpendicular if you want to multiply the numbers together. If they're like this, they're 0. You know what I mean? And if they're pretty close to perpendicular, but just a little bit off, hey, you pretty much just call it perpendicular. You know what I mean? If it's at like a 60-degree angle, that's where we get half. So this is just kind of our knowledge of vectors and trigonometry. And, you know, it's always good to mentally have that picture. You know what I mean? And, like, how could I do this? If I'm trying to torque, we're not, well, let's just get into it. Okay, so we have this distance to here to there. Now, this distance is, okay, this value of 9.7, alpha b is 9.797, but, you know, it also, and that's this distance from here to there, but that's also just 2L, you know what I mean? So keep that in mind. 2 times, so that's 2 square roots of 24, but we're just going to try to use these L terms and then change them at the end, just to kind of make the problem simpler. So for our radius, for this first one, we're going to have a distance of L. We're going to get to this mass. It's going to have a mass of 1/2 m. Now we need to multiply by the velocity tangential, and that's when we have to use this angular velocity. Because what is the tangential velocity? You know what I mean? We say that radians times radius gives us something normal, and that's tangential velocity. So right here, I'm going to write omega, and then I'm going to write, well, I'm going to need to do the radius. So the radius isn't this, it's the radius of the disk, which is a. So then I throw an a term. Cool. And then we want to know kind of what direction this vector is in. So we went from here and then crossed it in, and this is going to be a 90-degree angle. And so we get to multiply all of it. You know, we don't have a sign. Like, if this isn't 90, then if this was like 120, then we would have to take the sine of 120. You know what I mean? So sine of 120 would be 0.866. So it's like, again, it's going to be 30 degrees up. It's not going to, it's almost 100%, but it's not quite. You know, you don't have that perfect 90, which is the definition of what, it's the moment arm. You have a mass and velocity going that way, and you want a nice perpendicular. It's like torquing a wrench. Is like you definitely want to, you know, here's your bolt, and then I really want to like torque at 90-degree angles. You know, if I try to torque this wrench by pushing that way at a 30-degree angle, well, you know what I mean? At the end of the day, it's probably just fine. You know what I mean? You're almost putting 100%. You're putting 87% juice into it. It's like, who cares? All right, so we got our first component, and guess what? We got like 4 more. Okay, and then we just want to know kind of the direction of this. So if it is a perfect angle, you know what I mean? Like, hell yeah, this is going to be our angle, and this is going to be our direction. And I'm just going to call this up. Cool. So we have that one up, and this is up. You know what I mean? Yeah, it's just kind of a cool way to label it. I mean, you could say this is the z-axis, and this is k hat, and you could call this k hat prime, maybe. You know what I mean? Who cares? All right, so now we're going to go, let's do this next one. This next one's easy. You know what I mean? So we're going to go plus 2L. That's our distance to here. We have a mass of 2m. Okay, and then so look where we are in the equation. Distance to there. We have that mass, 2m, and then we need to know its velocity. Again, velocity is angular velocity. Tangential velocity is angular velocity times the radius. Radius in our case is 2a. So we're going to do omega, and then we're going to go 2a. All right, hell yeah. And that one's the same direction, so we got up. Okay, Perfect. We only have 2 more of these, you know what I mean? But we'll have to do 4 more because you know what I mean? One way to do it is you could get this distance to there, you know what I mean? And then this is no longer going to be 90, you know what I mean? You're not going to have just a nice 90-degree angle. And I don't even know, like visually, I can't even confirm that this tangential velocity is 90. I think it is because these discs are tilted, and if these discs were horizontal, that would be 90. And I think the tilt, you know, just makes it so. You know what I mean? If I'm going up on this tilt to here, and then this tangential velocity, I think that's 90. You know what I mean? I truly do. I think. I don't know. Maybe not. You know what I mean? But anyway, such is life. Yeah, that's where it's just like, I at least want to do this problem once, and then just be like, okay, I did it. You know what I mean? And I think I'm fairly right. And then just look at the answers and go back and then really chisel in on what, like, maybe assumptions that I made. I think it comes down to the assumption. I don't mind making algebraic errors, but it sucks to make assumption errors when you're just like, no, this angle wasn't 90. You can't assume that. You know what I mean? That's what sucks. All right, this might be a little bit of a head scratcher. So, yeah, because if we take the distance to here, you're essentially, you got 2 components. It's the same thing. So yeah, let's do that. Because here to here, it's just, so that's our radius vector, and we can like kind of bold that in. Now it's going to have a component this way, and it's going to have a component this way. Cool. And then you can also, it's a parallelogram, so you could also go up and then over. You know what I mean? So this way to that way is the same thing as up to over there. And when we take this distance, you know what I mean, we're still at O, and for this upward component, you know what I mean, we well, let's see. Well, let's do the horizontal components, because if we do the horizontal component, it's identical to this horizontal is it? Yeah, it's like O is up here now, for whatever reason. And this is one of those places. It's just like, well, like, can you assume that? Well, we're going to do the same thing with this upward component. You know what I mean? Well, once we take the upward component, its angular velocity is going to be that direction. You know, it's like if O was right there, and then we're just going to take that component up. You know what I mean? And so the components of this, and maybe it's just like, nah, you can't do that or something, but I think that's definitionally what you do. You know what I mean? If you take this cross product to here, you're already going to have 2 components. You're going to have a component in the yeah. And then if this is the z direction, like what are our other directions? You know what I mean? Because we have you have, if this is the z direction, you do x and y, and then you'll point in the z direction. So if I say x is out of the page towards me, then this would be y. So right here, if I'm saying this is in the negative x, and it's not something I want to do, but it's like, obviously I could come back to this and kind of clean up my work. But this is going to be the I hat direction, the positive x, and then this is going to be the j hat direction, or the positive y direction. Now this is going to be the negative x direction, or negative I hat, and so if we did the cross product, well, this distance has a component in if I go from here to there, we have a component in the z direction and the j direction. I mean, in the k hat direction and the j direction, in the z direction and the y direction. And so if we do that, if we have a j component and a k component, and then we cross that into an I component. There you go. So, and this is just in you know, negative I. Then we're going to have J cross I. And how I do the cross product is I, J, K, I, J, K. If you go in order, it's going to be positive. So if I go I cross J, I get positive K. K cross I get positive J. You know what I mean? So if I go J cross I, I'm not going in the right order. So I'm going to, and then, so it's going to be negative, and then obviously J cross I is K. You know, you can't, you're not going to cross two things together and get the same letter. So you're going to have J cross I is negative direction. We already have a negative, so that's going to give us a K direction, and then K cross I is positive, but that's going to be positive J, but we do have that negative sign, so we're going to have negative J. So there you go. So we're going to have two components of this. One is going to be in the positive K, and the other is going to be in the negative J. And that's kind of what we're setting up just visually. I'm just saying, hey, I'm gonna like even this one has a positive, has a K direction and then a J direction. And look what we get. We get a vector that's in the positive K and then the negative J direction. See? So it's like, so we have a check on reality when it comes to doing that. All right, hell yeah. But I just want to make the assumption that this is, if we take just this component, hell yeah, we're going to be just in this same direction I'm calling up. You know what I mean? K prime. Because I just want all of them to be in that direction, and I want the others to be in this direction. You know what I mean? Because we're off axis here. I don't want to turn everything into Cartesianal. I mean, I could. It's just mentally, I just don't want to do that. I just want that layup. You know what I mean? So here we go. So we're gonna break up this to this mass, which is the quarter mass. We're gonna break it up into two things. We're gonna do the up direction first. So we're still gonna have this L over. So we're gonna go L to this quarter mass, and we're just following this equation. Our distance to the mass. And then we need the velocity. And again, that's omega times the radius. So we have omega times A. Cool. Now this is in the up direction. Hell yeah. But now we're going to get one in the I'm going to call this the left direction. Cool. So we're going to get a component down this. And these are at 90-degree angles. So hell yeah, when we're done, we can actually find the magnitude using Pythagorean's theorem. You know what I mean? Because if we're saying one goes this way and then one goes that way, you know what I mean? Or you could say one goes this way, one goes that way. Well, you know, you stack the vectors together, and then hell yeah, we get Pythagorean's theorem for the magnitude of the total vector. You know, A, B, and this is going to be square root of A squared plus B squared. Cool. All right, hell yeah, and cool. So yeah, we did this component. Now we're going to do that vertical component. So its distance is just A. You know what I mean? We're just going up the radius. So we're going to go. So this R is just A. The mass is going to be that quarter mass. And then our velocity. You know what I mean? This is going to be twice. That's the only mistake I could algebraically make. Is twice. So we have a factor of 2, and then we do omega times A. You know what I mean? Omega R is that tangential velocity. And we got twice that. 2 omega A. Cool. And this is going to be left. Alright, so now I'm kind of running out of room. But that was good. So to get the angular momentum of this, and I think this is like 100% accurate. That's the cool thing about, you know what I mean? That's the gold of this video. It's just like, why do I spend so long on these? Is because I come up with stuff that, you know, people aren't going to come up with. You know what I mean? Turning a disk into just a 3-point mass rod. You know what I mean? It's on a massless rod, and that is spinning. You know what I mean? And then because all we're doing is trying to find the instant angular mass at this instant, and it's going to be the angular mass. I mean, sorry, I don't know why I'm saying angular mass. We're trying to find the angular momentum at this instant. And as long as omega is constant, this thing's going to be spinning around the same speed forever. You know what I mean? So we are also finding the angular momentum at any given time. I don't know what the hell I was talking about. Okay, so now we got to go to this one. Booyah. Yeah. So I think because after this, I'm going to probably spend another hour. You know, the next thing is just like, well, just do it normal, you know what I mean? And then, are you going to get the same answer? And I think I am, and that would just be remarkable, and that would be cool. But yeah, lately, my brain is just not, it's fuzzy, you know what I mean? So we just have to, like, 1 step forward, 2 steps back. Okay, let's do this one. So now we have, yeah, we're done with this. Yeah, we went to there. That was that one component. Oh, no, my bad. Yeah, I'm glad double checking. This was to here, cool. This one was to there, cool. And then we had to do this tricky one that had 2 components, and now we got to do that tricky one that has 2 components. So we have a component of the a component that way, but its actual R is right there. This is the actual R vector, but it's got 2 components, one that way, one that way. And you can do the parallelogram where you can say it's up and then over. You know what I mean? And I think I am pretty right on this. It's like if O was right there now. It's like if O was right there now, taking that component. You know what I mean? And if you take those components, this is still 90. See how if I go up and then do tangent, like, all right, hell yeah. So yeah, like with this component, your distance is up, and then you're going tangent with your fingers. And the right-hand rule is, hell yeah, just write down this line, which we are calling left. And then if we go from here over to that and then do the tangent, the right-hand rule is up. So booyah. And now we're just doing this tricky one. So we're going to go 2L over to it. And then it has a mass of 1 m. It has a tangential velocity of 2 omega times its radius, which is 2a. Okay, cool. We're done. Hell yeah. And now we're going to take this component upward, which has a distance of 2a, and this is the heart of like what is it called? Like in statics and stuff, where you turn things into Cartesian coordinates. You know, where you have x, y, z coordinates, because then you can get things that are perpendicular. And when you have something with the cross product, you just get to multiply all the numbers together if it's perpendicular. And again, if it's not, you could just guesstimate. You know what I mean? Even right here, I could just say, well, forget the 2 components. I'm just going to say, you know what I mean? Hey, this angle is a little bit more than 90. So I'm going to multiply the numbers together and then multiply by 0.9. You know what I mean? It's really close. Or 0.95 even. You know what I mean? Maybe even it's just 0.98. Who the hell knows? But that's when my angle like starts to go this direction. And then I just lose sense of like where the hell that is. You know what I mean? But I could probably use yeah, and the way it's drawn, I really can't tell if this angle is the same as that angle. I think it would be. You know what I mean? If I'm just, even if this is, I don't think so though. I don't think so. Yeah, or like if this is straight up, if I go 1, 2, and then have a 90-degree angle, these angles are hella not the same. Because check this out. Let's say this was 10 and this was 1 and this was 1. The angle of both of them would be inverse tangent 2 divided by 10, And then this one would be inverse tangent of 1 divided by 10. And if we said this was, and we're going to double that, and we do not get, you know, if I double this, so this scenario is not true. So, but I'm sure there is some angle that you can make this where the halfway point is true to reality. And but I just can't confirm that that's the case for this one. That fascinates me. It seems like this angle might be the same as that angle. Have no idea. Yeah, I won't even know how to go about proving stuff like that, but that's why we do long videos. You know what I mean? If I had the mental energy, we would totally stop and do that. We're not going to. Alright, so where are we at? We're at this one. We got the component this way. Now we're going to do the component up. Cool. And it's going to go left. So we got 2a times the mass. It's 1m. Times its tangential velocity. Again, it's 2. So we have that 2 out there. Omega. And then the radius is 2a. Okay, hell yeah. We're totally done. You know what I mean? That was hell. But we did it. So this is left. This is just up. Sorry, I didn't label that one. Yeah, so we have two components that are this left. And so now we have to kind of add like terms. We can't add them all together. We have to add the left ones and then the up ones. And so we're going to get a number for the up and then the number for the left. Okay, so if we add these up, this is a half. This is 2 times 2 is 4 times, this is 8. This is 1/4. Okay, and then this is another up one. We have now. Is that? I swear the 1/4. Yeah, I guess so. I thought I did this problem before and it was a little bit different. But yeah, this is that 1/2. Oh yeah, no duh. This is 2VT. So yes, I did mess up. Good. Because I'm glad I caught my error. So if we go out to this one, this is L out to it, but the mass is 1/4. But the angular velocity of this one is times 2. You know what I mean? So yeah. There you go. So we're gonna have 4 components. 1, 2, and then 3, 4. So because these two things have like 2 components to them, we're gonna have four of those things that are a multiple of 2. This is twice the tangential velocity. So I'm glad I caught that error. See, we have the 2 there, the 2 there, the 2 there, and the 2 there. Because I have done this problem. You know what I mean? It's so interesting doing a problem for the camera and then just doing it in like 2 seconds. You know what I mean? I feel like I'm in a black hole. Alright. Cool. So yeah, so this is definitely a half. These halves add up to 1. And then this is 8. And then this is also 8. 2 times 2 is 4 times 2 is 8. So we're going to have 16 plus 1. We're going to have 17. Cool. So, and that's all the up components. You know, these are the 2 left components. We'll add those up. But these are we're going to have 16 Lm omega A. Okay, now the left components, we're going to have 1/2, because we got 1/4 times 2. Oh, it's A squared. It's A squared. No, it's not. Oh, no. This one's A squared. Yeah. My bad. This one is Lm omega A. Straight up. Alright, so this is going to be... Yeah, see, this has an A and an A. So we're going to get m omega A squared for this one. Cool. So this is 8. 2 times 2 times 2 is 8. This is a half. So cool. So that term is going to be 8.5 m omega A squared. So we need to get this one in terms of A squared too. So we know that L is square root of 24A. And then so this one is just going to be 16 times 24. And this becomes A squared. Cool. Yeah, because this L is square root of 24A. I just popped the other A over here. So now we have This is the up direction, and this is the left direction. So this is going to be 16 square roots of 24. Now this is going to be my A. So like, hey, we're going to, if this is, you know, if we want to find the total vector C, that's going to be C is the square root of B squared plus A squared. So we're going to do that. So we're going to go 16 times the square root of 24. We're going to square that. And then we're going to add it to 8.5 squared. And then the square root of all of that. And I guess we just have to store this as a letter. I'm gonna store it as alpha W. Okay, so hell yeah. So this was the total angular momentum about A. And let's get values on this. So we have 16 square roots of 24. So this was going to be 78.38. And then this is 8.5. I think you get it. So we have 8.5 and 78.38. Now if we look at our problems, they're all in terms of ma squared omega. Alright, hell yeah. Got some more juice in the camera. And yeah, so this was 78.3, and then W was 78. The total was going to be 78.84. So you can see that we had a vector that was 80 long, like 1, 2, 3, 4, 5, 6, 7, 8, and then it was only like 8 across. So there you go. So see that? See how this was 84 and this was 8, and then we're like, hey, what's this length? You know, again, I do this 100 times. You know what I mean? It's just like, hey, this component, or like if this is your hypotenuse, it's literally this component. You know what I mean? These two are basically the same. If I say this is 100, this is 100. You know what I mean? And it literally is. Holy Toledo! If I had something that was 100 and then just up 10, hey, what would be the hypotenuse? 100 squared plus 10 squared, square root of that, and we just get 100.5. Just nothing. You know, they're equivalent. They're basically the same. So just keep. Yeah, I love going over stuff like that. Alright, so we did it. We finally have some sort of check on reality. And get this. This is literally, let's see. So let's not say anything. But we have ma squared omega. So that's just how it's spelled out. So now we have that, and that's going to help us kind of have a check on how the problem is laid out. But I did say that we weren't going to do it with my little 3 little point masses and turning 2 disks into you know. So we'll try to do it like normal. All right, and all right, hell yeah. So so let's do it. So we're gonna say that yeah, we want the angular momentum about O. So how do you do that like normal? Well, you say that this is a spinning disk, and it's spinning, and if it's spinning and use the right-hand rule, it's like, hell yeah, you're just pointed towards O. So you're going to have this component, and surprisingly, this component's the weak sauce one. You know what I mean? And then I'm going to draw the perpendicular, because we'll definitely get into that in a second. But now that we've done the problem, you're just like, oh, I get it. It's like that was actually the weak sauce one. What is angular momentum? If I'm standing at O and like, hey, I have this system and I have to like slow it down, like how much torque does it have? You know what I mean? Like how much power does it have? How much leverage? You know what I mean? Angular momentum is leverage. It's mass times velocity, and it's leveraged. The fact that this stuff is spinning is like, well, that's not a big deal. If this was not rolling, if you had a pivot right here and these were not touching the ground and it's spinning at this omega, it would only have back to our problem. Its component would only be 8.5. You know what I mean? Like we already solved for that one. You know what I mean? And check this out. This will be the first check on reality. It is like my little masses jive, because that's it. 17 divided by 2, that's 16 divided by 2 plus 1 divided by 2, you know what I mean? So that's 8.5. So this literally is 8.5. So the spinning part of this is only 8.5. And so that's just a visual representation of like, yeah, I'll say it one more time. So you're going to take this and just lift it up a little bit. Still have it like have them still spinning at the same speed, but you just took the juice out of the sails, you know what I mean? Like the second you lift up a car and then just have the wheel spin, you know what I mean? You don't have that much, you know what I mean, leverage. You don't have that much mass velocity out at, like this, you know. The fact that this is actually spinning around a circle at this omega means that the energy input to get that thing up to speed was way more. Just like if you lift a car off the ground, you know what I mean? Hey, let's spin the wheels. That's easy. Put the car on the ground, spin the wheels the same amount. You're gonna burn some fossil fuels. You know what I mean? So that's the most fascinating thing with angular momentum. And then from this, doing this long form is like, I can think of like now about 10 different small little videos, and we'll try to do small videos. You know what I mean? I think people only watch 2 minutes anyway. But yeah, we'll try to do that. You know what I mean? To kind of explain that, hell yeah, like angular momentum is like leverage of mass and velocity. You know what I mean? So if we have this leverage of mass, so the most part of this is actually this magnitude of angular momentum of the center of mass. You know what I mean? About the assembly point O. Like and what this means is the magnitude of angular momentum of the center of mass. The magnitude of angular momentum of the center of mass. So we take the center of mass, and we've already solved for that L divided by 5. I really don't want to solve for that one again. But if we take that, we know it has a tangential velocity, because we know we have an omega prime that's just 1/5 this omega, but we have such a huge leverage arm, you know what I mean? Way bigger distance than just these little things spinning. So the angular momentum, like the mass times velocity with a huge leverage arm, that's the moment part. The moment. Yeah, that's why I don't like angular momentum, because you're almost like the Latin of this. You're almost trying to say two things at once, because mass and velocity, that sounds like momentum. You know what I mean? But moment, it's the moment of mass and velocity. It's the moment of linear momentum. You know what I mean? So it's like angular momentum squared. I don't know. Yeah, but yeah, that's where this term, like just even written out, isn't very. I would rewrite terms. Yeah, I think I would. Almost making people say them in like, I don't know. Like, definitely try not to simplify things. That's for sure. And then, yeah, anyway. So yeah, you're going to have so much more leverage of this whole mass system, like traveling around in a circle, compared to just being lifted off the ground and then spinning. Cool. And we even just solved that, because this says just take the angular momentum. Just take the center of mass and know that it's going that way with the leverage arm up to it with this omega prime, and that's going to give you a number. And then not find the angular momentum of the actual spinning wheels. Neglect that. But from our problem, as we already said, the max number that could be from point O is 78.84. So if they say 81, hell no. You know what I mean? So that's one check on reality that this is not the answer. And we'll do a couple more for sure. Alright, hell yeah. So, yep. Now, people get this confused, or even I do, is just like, well, what if you took the angular momentum about point P out here? Well, it just goes up, you know what I mean? Your angular momentum equation is radius crossed with the masses and velocity. Go find what has mass and some sort of velocity. Travel out the distance from your point, and if that if that stuff's at 90-degree angles, multiply it all together. If the mass and velocity is actually headed towards your point or headed away from your point, then you can't count it at all. You know what I mean? And then if you're off by just a little bit of an angle, then you know, it's just only a proportion. So that's the idea of leverage. Yeah, oh man, I really want to go over this because we said that R cross MV gave you a vector that's called angular momentum, and this vector, I throw 2 arrows on it to show you that this is a useful thing about point O. You know what I mean? This is actually useful because I kind of do the door analogy where it's just like if you're trying to open a door, you know what I mean? Hey, you want to put a force this direction, and you go out to a hinge. You know, we'll say it has 3 hinges, but we're going to go to this hinge, and it's the distance d. And let's reverse this because the right hand rule sucks. But anyway, so and then I stick my fingers in D, and then I do this into the force. It's at a 90-degree angle because we know that torque, that's what we want, is D cross F, or more generically R cross F, and the R is this D. So we have R cross F, and then we're going to get a torque that's going right up these bolts, or right up the hinges. And so that's where I'm going to put a double arrow on. I didn't do a very good job, but we'll do a double arrow like that because this is where it gets confusing. Because if I take this same door and you know, with hinges, and I do this, like, hey, I want to open this door with and I want to do that with my force. Is that going to open the door? No, it's not. Okay, I'm going to put a force this way. Is that going to open the door? No. But then you get, like, I think mentally, there's a lot of times where it's just like, yeah, you get this scenario into your head so much that the second you actually get a vector that goes along these bolts, you don't like. I didn't think it was. I was like, oh, that messed with me. It's just like, no. I spent my whole life being like, yeah. If you're trying to get torque, which is moment, like this is still a moment equation. It's the moment of mass times velocity, and you know what I mean. But if the components are acting at the thing that you want to torque, so we want to torque these bolts, and we want to get this vector of torque, this torque vector, in the direction of the bolts. That is how a door opens. And so the same thing with angular momentum. If this z-axis, you know what I mean, if I have double arrows on this z-axis of a term called angular momentum, that's a big number. That means, holy hell, all this mass and velocity is moving tangential to this axis, like some big distance away. Either a big distance and a small mass and velocity going, or a combination of a distance and a mass and velocity with that 90-degree angle. And you know what I mean? That's going to be like this number of the cross product. And again, if you don't, the scalar component of this is just R, M, V, sine theta. So if this is 90, did I do that right? Hell no, I didn't do that right. No, I thought it was. Yeah, sine of 90. If the angle is 90, sine of 90 is 1. Cool. If it's 0 or 180, you know what I mean, where you're, yeah. And then, yep. And in the case where you just do a force here, that your angle is still 90. Well, no. In that case, your distance is just 0. So it would be nonsensical to even yeah. But if your force is just really close to here, hey, your distance is just really small. That's what's causing no torque. But when you put this same force this direction, you know, in D, then you say, well, I'm going in D this way, but then the force is this way. You know what I mean? Maybe this angle is 180. So that's where sine of 180, this becomes 0, and you don't have, in our case, you don't have any torque. So even torque is RF sine theta. And if this is 180, that would go to 0. Alright, hell yeah, I kind of forgot what we were doing, but hell yeah, we're trying to solve this one legitty. So, how do we do this? We're going to have, see, that's where you have to break this up. That's where using, like, a moment, or I mean, mass moment of inertia, second moment of mass, I omega. So, angular momentum is I omega. But then angular momentum is also the distance to the center of mass, and then that center of mass, the mass, times its velocity. You know what I mean? So both of these add up to the total angular momentum. And yeah, so that's kind of just fascinating as well. Yeah, so yeah, you know what I mean? Because let's say this disk didn't exist, you know what I mean? And then so that's how you can totally break it up into components. Like one is you can do this I omega for this disk and say, hell yeah, it's pointing this direction. That's going to be this vector. That's going to be the left vector. And that's why this one was the small one. This one was the 8. This one was the 80. Remember that? And because we are going to get this up vector. This is going to be the left vector. Cool. But that's why this problem is kind of cool, because it's just like, well, you can also say the angular momentum about O is just the center of mass and its tangential velocity. If this is the center of mass, it would be like the whole mass is located there, and then it has a tangential velocity, which in this case is the moment arm to this mass, which if this is L divided by 5, this is 4/5 L, then you're going to have a distance, and this is 5/5 L, if that's the way you want to look at it, and then you're going to have a distance of 9/5 L, and then that velocity tangential, which in that case is, I mean, this is your distance to it, so that would be your R. Your mass is the whole mass, but your velocity is omega prime times this, oh, and in this case, that's where it's just like, I didn't want to get fouled up. It depends on what you're taking the angular momentum from. If we're taking the angular momentum from Z, then hell yeah, you gotta get that distance across. But we're taking it from O, so you're still this distance. You know what I mean? Hey, you know what I mean? You're still going to the center of mass, so that's still going to be that 9/5. So that distance shows up again. So this distance is the same as that, and then that is going to be the angular mass of the whole thing. So I think that was a good enough explanation, and I might as well do, at least one thing simple. So the second moment of mass, we've talked about this. That's yeah, if you have like a hoop, you have mass out here, you have a distance to it, and that's your mass. And then the second moment part is like, take that distance, so square it. So you're going to have that mass and then that distance squared, like mr squared. So a hoop is mr squared, you know what I mean? But this is like a, you know what I mean, the mass 1, and then you're going to have mass 2. And then, but the whole thing for a hoop is mass total r squared. It's just mr squared. But for a disk, you just have to look this up, trust it. Like, I have not done the actual proof on it, but it's just 1/2 mr squared. It's just something that we just know. But it's the same thing. It's like, obviously it's not going to be bigger. You know, you can use your noggin and be like, well, the only reason this is mr squared is because all the mass you're just assuming is out at r. But here, some of the mass isn't even at r. You know what I mean? Some of the mass is actually a distance of almost 0. You know, from the center. Some is like halfway. Like the majority of it's kind of near the end, maybe. I don't know if you'd call it a majority, but because you're squaring that, yeah, if this was just mr and you had this, oh hell no, it wouldn't be half. You know what I mean? Because most your mass is it seems like, well, I actually don't know. I don't know. Mentally I can't do that right now. I don't even know if it would be bigger or less than mr squared. I think it would actually be bigger for mr, but don't quote me on that. No, yeah, I have no idea. But anyway, but if you're taking these masses, taking the distance out, and then squaring those distances, then hell yeah, the sum of that is 1/2 mr squared. Cool, so we know that. So then we can figure out the angular momentum of a spinning disk is the direction, the right-hand rule, the direction it's spinning. So the angular momentum is going to be this left, and it's going to be I omega. That's what confuses a lot of people because they don't turn it into a vector. You know what I mean? A disk is, you know what I mean? As long as the disk isn't wobbly, your disk is always going to have a angular, you know, all the mass and velocity, the mass and tangential velocities of those masses are all going in that direction. So if you're taking from the center, going that distance, hey, you're always going to get a 90-degree angle. And then all of those are going to be facing the, even if you're down here, you know what I mean, hey, you're going from here distance in, and then tangentially these are going that way. And then you do it like the problem is lifted off the ground where it's not touching and it's just a spinning disk. Because that's why you have to do it in two parts. You take the angular momentum of just the spinning part, and we said that was pretty dinky, 8.5. And I think those are the take-home points. It's not to get the answer right, it's to realize that, oh yeah, spinning stuff just in general isn't, like there's not much angular momentum there of the wheels themselves, but the whole mass, you know, turning is like, yeah, it would be like a car. If a race car was turning around a track, the angular momentum, even if you're on the inside of the track, you know, and then let's say it's almost like a toy car that you're holding on a string that's going around the track, the angular momentum of the spinning wheels is super negligible. I mean, it's just a small component of that actual mass traveling from that pivot point of that string. All right, let's see. So cool, I think we can do it. So angular momentum about O is going to be this I omega. So that's going to be 1/2. This is a mass of 4m. The radius is going to be 2a squared. So we're going to have 4a squared. I just did that like that. Okay, and then we're going to multiply it by omega. Cool, and that's it. That's the angular momentum in this left direction. Cool, let's do this one. You know what I mean? So that's how this problem takes 2 minutes. You know what I mean? 1/2, we have 1m. And then we're going to have r squared. That's just going to be a squared. Cool. So right here, you have 4 times 4, 16, divided by 2, that's 8. And then you have right here, you have 1/2. So here you go. You got that 8.5. You know what I mean? And we're done. You know what I mean? I mean, for one aspect of this, I mean, we're trying to find the total about O, but you can totally see how we're coming up with this 8.5 quite a bit. Like this one obviously checks the bill, and but this one is kind of interesting because it says the magnitude of angular momentum about the center of mass. Now, if we look, well, let's talk about that one, because if we look, that angular momentum is a distance away. It's like, hey, we have some sort of mass and velocity way out there, and then we're right here. Oh, hell yeah, that's a lot of what do we call it? Well, it's just angular momentum, you know what I mean? But I think we called it a certain, like leverage. Yeah. It seems like that's a lot of mass and velocity. That's a lot of leverage out there. That if you had to stop that, you know, from where you are, like, man, and you just had to apply like some sort of torque on a wheel to stop all that stuff, it's like, holy hell, that would be really difficult. You know what I mean? There's a lot of leverage of that mass and velocity from where you are. Now, if you're just right in front of it, being like, hey, you know, putting your hand in front of this, well, maybe you could do it real easy. But just like if there was just a little piece of wood that you just had to pinch, you know, and try to stop all this with like a torquing motion, you know what I mean? Hey, no, because there's a lot of leverage from that point if that's the point that you're trying to stop that leverage. Cool, got it. But why this problem jives is if you take the angular momentum, you calculate that about the center of mass, well then sure, the center of mass does have a velocity, and it has a total velocity, a total mass of 5m. But guess what? The distance, if you're already at the center of mass, hey, what's the distance to the center of mass from the center of mass? That's 0. All right, so there you go. So it's like, hey, I have a force in the right direction when I go to a door, but I'm pushing on the hinges. It's just like, cool. Yeah, that's cool. Like, you're not doing anything. I think it's similar to that scenario. Like, your distance to this force is nothing. You know what I mean? So that force isn't causing a torque. Same thing here. So if I I don't even know how to. Yeah. But anyway, yeah, not 100% analogous, but I think close. All right, so yeah, that's why this problem is just this component that we just solved. It's literally only, but then it's kind of bizarre because you're just like, whoa, we did this disk, and then we did the right-hand rule, and then whoa, we have this vector that actually goes through the center of mass, and that's what throws me. Where you're just like, oh, we have this vector go through the center of mass. Does that mean that angular momentum is 0 through the center of mass? No, the actual opposite. It is that number through the center of mass. Just if I ever get this torque vector that goes through these hinges, this door is opening with that torque. You know what I mean? That is the number that is doing what we want it to do, if that's what we want it to do. All right, hell yeah. So, man, I think I'm getting my second wind. So yeah, we got that 8.5, you know what I mean? And then the units on it are M. We forgot the omega. I apologize. Because what the hell was this one? This was 1/2 M. Oh, whoa. Yeah, because the angular momentum is I omega. So we did the I part, but we didn't do the omega part. But yeah, hell, this was just I omega. That's also why, like, energy equations, that's why I think I might strike YouTube gold explaining stuff. In terms of, I'm not trying to make the problems more complicated, but I'm showing you where those things come from. And I think that's the question everyone, you know, if you're just using I omega for the rest of your life and then not even in questioning where this comes from, it's not going to be a useful thing long term, you know what I mean? So that's where we, you know, invented making this 2 mass, 1 mass, you know what I mean, 3 mass disc, you know what I mean, just a 3-point mass on a massless rod. That is the definition. I can't wait to make that video kind of short. All right. So now we did that, and so now we got to do. You basically have to add this to this problem. This problem was what we just did here. This was that 78.38. It was the component in the up direction. That was the center of mass, you know what I mean? Because, okay, cool. So let's do that. And how would we do that with these simply? How would you do it if, like, let's say you didn't know that, hey, if you just take the center of mass and the tangential velocity. Well, again, let's just remove this disk from the equation, but this disk is moving. You know what I mean? The center of mass of this disk has a tangential velocity. And it's just this omega times 2a, you know what I mean? It's the omega r, and that's 2a. And so if that's the case, we still have to take that component, the distance to that mass, and its velocity. So it's still and this is, if you look at it, it's still an mr squared omega, you know what I mean, it's still an mr squared omega term. And some would call this an, I don't know, mass md squared omega, you know what I mean? Oh man, I think that's where the parallel axis theorem, nah, never mind. Like, well, let's not go over that, because parallel axis theorem would be like, hey, I'm moving this direction on the disk. I found the angular momentum about the center, but let's say I wanted to find the angular momentum about this point? Well, I'm moving in a parallel plane. I'm moving parallel this direction to that point, and then it's just 1/2 mr squared plus md squared, and this would be your distance that you're moving. Cool. But yeah, I don't think I would get that confused with, hey, momentum is something spinning and then something translating. Those are two separate components of angular momentum, as I know it. And I've only been looking at this stuff for a couple weeks. All right, so hell yeah. So we have this one. It's a distance. We're gonna use this equation. It's a distance of 2L. What else do we know? It's a mass of 4, so the mass is 4m. And the velocity is omega. It's this omega, and it's going to be the radius, which is 2a. And I apologize. I said, what did I say? This term came up twice? No, this term is totally different. You know what I mean? Because, hey, this is your distance from point O, and then mass and velocity. Velocity is omega times r, but sure, here's your r in that case. That's the only thing that might get you mixed up with this equation of r cross mv, because v is also omega r, and you're kind of using the same r term just for distance, but this r can be that, and then this other r for omega r is that. Cool. All right, so we have that term. So let's do this one. Same thing. It's L, m. And then we have, so we have Rm, and then we have omega A. Cool. So right here we have, this is 4, 8, 16. So this is 16 m omega A squared. This, whoa. No, it's not. We have an L in here. So we have L m omega A, and this is going to be 1 Lm omega A. So we're going to have 17 Lm omega A, and this is where we have to throw in L is square root of 24. So we're going to have 17 square root of 24. Man, I feel like that's a little bit off. Didn't we get 16, or did we get 17? Or maybe I did the problem just a little bit off. We only got 16. So let's see if we have a hiccup. What we were trying to find the angular momentum of the center of mass. No, we did it the same. So we had 2L. Yeah, because we want this up term. So this first one was going to be L. Yeah, and I guess we just did the half. Huh, interesting. All right, so this was a half. This was a half. This was 8, and this was 8. Oh, yeah, so duh. So we have 8 and 8 plus 1, that's 17. I don't know where I messed that up, but yeah, we'll have 17 Lm omega A, and then there's going to be 17 square root of 24 m omega A. So let's clean this up. Holy Toledo. So we're going to have 17 square root of 24. That's 8. Yeah, this is 80. I thought I was a little bit off. I apologize. So this is 83.2826. And that, yeah, because I remember doing this, and this number was bigger. You know, it was actually bigger than 81. And this is the angular momentum of the center of mass. You know, that's that component. The spinning stuff is just 8.5. That has not changed. So I'm going to store this as W. Of the center of mass, and then we're going to do alpha W squared plus 8.5 squared, square root that, square root that, and then we're going to store that as alpha V. So the total is alpha V, and that's going to be 83.71. So yeah, that's like, obviously for multiple choice, if you just do something wrong and don't get the answer, you're going to be like, oh hell yeah, oh hell no, you know what I mean? That's a no-go. But it's still a no-go because the magnitude of angular momentum of the center of mass minus the spinning stuff is 83.28, and then the total is just a fraction more, 83.7. And so that's the take-home point, is like both those vectors are about the same. This one is just slightly bigger, 83.7 compared to 83.3. Cool. 83.3. All right, hell yeah. And so, yeah, this is absolute gold. No one's going to watch this deep, though. But just the fact, so I'll have to make shorter videos about this. But yeah, the fact that I can take a disc and turn it into a point mass, two in the middle, one on the ends, it gives you the same answer for angular momentum. And just visually, you can see what the hell's going on. This mass is stationary. This mass is moving. And then this mass is twice. You know what I mean? We get that. We get that with wheels. Okay, so we basically did it. And this is going to be 17. It's going to be 17 square root of 24. We get another a, so it's MWA squared. And hell yeah. So we get this, which is 17 square root of 24. That's going to be that 83.3. So now we can kind of start memorizing these numbers. This is 8.5 m omega a squared. And that's what you're going to see right here. Because, and this one checks now, fully checked. We don't even have to do it, but we will maybe at the very, very end. But if you take the angular momentum about the center of mass, the distance to the center of mass moving is 0, so therefore there is no angular momentum about that moving, you know what I mean? So, and it's like this. This is the classic. If I have a 1 kilogram, you know what I mean, mass, and I have an omega, and we'll just say it's 10 radians per second, and a 1 meter, because this thing's going 10 meters per second. That's pretty fast. It's 22 miles an hour, you know what I mean, spinning around this thing. And so what's the angular, and I'm going to call this point B and this point A. So what is the angular momentum about point B? Well, we do the cross product times mv. So what you want to do is, we got 30 seconds before my camera burns up, so that's fine, we'll talk through. Yeah, what you want to do is you want to find what has mass and velocity. This does. It's got a mass and velocity. And then if I'm going to start at B, okay, then now I'm going to go with a distance to that. Oh, I can't move. This is 0, therefore it's 0. All right, I got to let my camera cool off, and I'm going to catch you on the flip side. All right, hell yeah. So I took a big break, and I really want to solve this problem kind of with my setup where I make this mass double and these masses, you know what I mean, half that. And we're gonna take the center of mass. Well, we're gonna do this: angular momentum of the center of mass. So I'm gonna call this Cm, and this is L divided by 5. L 1/5 L. This is 4/5 L. Cool. And we know that this one is going 2 times velocity tangent. This is 2 times velocity tangent prime. This is going velocity tangent, and this is going velocity tangent prime. Cool. This mass is 2, 1. This is going to be a half and a quarter. Okay, so let's just start taking cross products. We're going to go from here to there. You know what I mean? If we do this R down to here, this thing's not moving. The velocity is 0. The tangential velocity is 0. Cool. All right, so we have angular momentum is R cross mv. Cool, let's do it. So angular momentum of the center of mass, we're going to do this one first. So we're going to have a distance of L divided by 5. I don't want to do that. I want to do 1/5, and then we have L. The mass is going to be 2m. And then the velocity tangential is going to be omega times 2a. Cool. All right, now we are going, and then now that is going to be in this up direction. So yeah, we have to kind of keep, I think we have to keep tabs on this. You know, maybe not. Yeah. I mean, because if you know, if we're doing the momentum and we're saying, hey, that one's going this way, cool. But then if we go, this one is going that way. So I swear it's just like, from my perspective, they're canceling. We'll see if we actually get the right answer. Man. I don't know. Yeah, we'll see. Okay, so we did that one. Let's do this one. So that's going to be up. Oh, and I better just draw this in. And then here is down. And I'm going to do double arrows. Just so you know, that's the angular momentum. And so this is down. Cool. Alright, so that's up. And let's go to this one. So we're going to have, this one's going to be down, but we have a distance of 4/5 L. The mass is 1/2 m. The velocity is omega times a. Cool. Nice. And that is down. Alright, now should we go to this one? This one, you know, we still have that same, you know, 1/5. So we're going to have 1/5 L. The mass is just 1 m. And then we're going to have omega 2a. And that's going to be up. Now this is also going to have a component this direction. Let's see. Yeah. So we will get a component this direction. Oh, interesting. And that's going to be, you know what I mean, just because these are going through the center, that's what we want. So yeah, we're actually going to get a component this direction by going up 2a. So I'm going to say this is left. So we're going to go up 2a. So we're going to go plus, so we're going to go 2a. The mass of this one is 1 m. The velocity is omega. Well, and it's twice the velocity, so it's holy Toledo. So it's 2 omega, and then that's 2a. Cool, and that's going to be left. Alright, so now we're done with this one. Yep. So, yeah, because that had two components, up and left. So now let's do this one. We're going to go 4/5 over there, 4/5 L. That has a mass of 1/4 m. Cool. We have 2 times the omega, and then it's a. So cool. All right, and then that one is that is down. So there you go. So we have a component down. All right. So yeah, the down component's gonna cancel, you know, the up components. You know what I mean? Depending on their magnitude. And okay, let's do that one. So now we're going to go up, you know, the cross product up, and so we're going to go plus a. This one we went up 2a, so we're going to go up plus a. This one's going to be left. Let's see. The mass is going to be 1/4 m. And then the velocity is, well, it's 2 times omega, and then we have a. Cool. So this turns out to be, this is just 1/2. Cool, so that's the term there. This is 2/5. Oh, and let's see, that was to the left. Okay, so we have components that are up, and then we do have components that are down. Those are going to cancel, and then we have components that are left. I feel like I'm doing it wrong, and this isn't the way to get that number, but I don't know. I'll be surprised. So this is 2/5. This is up. This is 2/5 up. So it looks like we got 4/5 up total out of those two. And now we get 4. No. This is 2/5. So this is 2/5 down. And, well, let's see. Let's see if I'm even doing this right. No. This is 4/5. Holy hell. Okay, so this is 2 times 2. So we got 4/5. This is 2 times, this is 2/5. Right here, this is, this can't, so it's just 2/5. And then this one is, hey, these 4's cancel, and this is 2/5. So this is 2/5 up, down, up, and this is down. Okay, and this is left, and we have another one that's left, right here. And this is going to be 2 times 2 is 4, times 2 is 8. So this is going to be 8. And that's where this term right here is 8.5 that way. So let's see if the downs and ups cancel. I mean, because that's the only way that's going to be a check on reality. If the down components, and that's what we were thinking. You know what I mean? Or is it what we were thinking? I have no, yeah, because those are the, I think, yeah, those are the components that are the actual velocity of the thing going that direction. You know what I mean? All those components. It's only the components that are this way in the left direction that actually jive. And if we just have a disk spinning, you know, at that angle like this omega, we use the right hand rule and say that, hell yeah, that's going to be the direction of our L. So yeah, so these will cancel, and so you probably see it before I do. So we have a 2/5 down, and then damn it, why aren't they easily canceling? Because this is 4/5. Yeah, well, I guess yeah, I'm sure it's right, but 2/5 down. So 2/5. So this is 4/5 down. This is 4/5 up, and then this is up too. Oh, damn it! Because that's the only way that this is going to make sense, right? All right, let's slow it down. So how did we get these? So we went from the center of mass 1/5 to this mass that was 2m. Cool. And it has a velocity of 2a. Perfect. Cool. Then we went to this one, the down one, and we said we went 4/5 to a mass of 1/2, and it had a velocity of a. Cool. Then we went to this one, which was 1/5, to a mass of 1. Yeah, that jives. And then we have a velocity of 2 times. Yeah, we need a 2 here. Hell yeah. So yeah, because it's twice. Yeah, it's twice the velocity. I knew I was going to make that algebraic mistake every time. But yeah, so this is 4/5 up, cancels. So this is 8/5 up. And no, that makes it even worse. Oh, damn it. Okay, we'll just continue on. So this is going to be 1/5 to that mass of 1, and it's going to be twice the angular velocity, and it's 2a. So this becomes 4/5. Okay, and then we do this one, which is this other down one. It's 4/5 over to this mass of 1/4. Then times 2 times the angular velocity. And then for sure these are the left terms. You know what I mean? Because we have 8 and then 0.5. Yeah, and those are going to be up a, up 2a, and then up a. Man, these should cancel. And I don't know what I'm doing wrong. So we have 2 times 2 is 4/5. This is going to be 2/5. And then this is 2 times 2, which is 4/5. And then this is 2. I mean, these 4's cancel, right? So it's just 2/5. Holy Toledo. Alright, I gotta look at this one. You know what I mean? See if I have an error somewhere. Alright, hell yeah. So I think I'm just fundamentally wrong on this thing. And you know, the one problem that could kind of prove, you know what I mean, is like if I have a string on like a you know, chunk of mass that's rectangular, and I'm going to say, hey, there's the center of mass, and then it's spinning around with an omega. The angular momentum about this center of mass, is it 0? You know what I mean? That's what I'm. Yeah, if we have this scenario, yeah, okay, that makes sense, because, you know, going back to if I just say this is the center of mass, and then I want to, you know, spin this with an omega around a string. And if I do take the you know, this omega, this driving thing that spins it around, has no, so that's going to be this omega prime. It has, there's no angular momentum about the center. You know what I mean? It's almost like it's just like moving linearly. You know, this thing's not just spinning in place. You know, if it was spinning about the center of mass, then you would have something. And that's why, so at the center of mass, the only thing that's kind of spinning around the center of mass is these disks, where, you know what I mean, the disks are spinning. And so only those components are, you know what I mean. So even though, like, I was trying to do it a certain way and these didn't add up, but there's something fundamentally there's something fundamentally wrong about those, about that proclamation. Now, because it would be this scenario where, like, hey, let's say this point was fixed, you know, and you put a stake in the ground, and then you're spinning these masses around that stick. Well, then sure, then you would, but then even that, they don't add up. That was the interesting thing, is you would still have some net angular momentum. So let's try that. You know what I mean? Let's put a 4m mass right here, and then we're going to go out over here and just put a 1m, and then we're going to spin it with an omega, and I'm going to say, hey, that's the center of mass. And then in this problem, you know, this problem is different than this problem. You know, I mean, we again, I think we proved that, hey, it's more set up like this, where there is no angular momentum, because it's not spinning about its center of mass. But if it is spinning about the center of mass, then you are going to get some net. You know what I mean? Just because this is the center of mass, you are going to get net angular momentum. Well, oh, no. I'm going to say, hey, this one spins this way, but then this one spins the opposite way. That's, you know what I mean? And these, for whatever, I don't think these will cancel. If this is 4/5 L and this is 1/5 L, I don't think they will cancel. So we have, well, what's our equation? We have the radius, R cross mv, is that our equation for yes? And then here's the center of mass. So L about the center of mass is the distance, that's going to be 1/5. L, the mass is 4m, the velocity is omega, and we're going to say these things are spinning with the same omega, because that's what we have in our problem. Okay, and it's going to be omega times that radius. Oh, this one might actually work, but this one for sure. Yeah. Let's see what we got going on. So 1/5 L, 4m omega, and then just 1/5 again. Okay, so that's the other one, and we're saying, hey, that could be equal to this 4/5. Oh, and this is L. So 4/5 L with 1m times omega, and then 4/5 L again. So this is going to be 8/5 L, 8/5 L squared omega m. You know, m omega L squared. Okay, cool. This one is going to be no. This is 8/25. We have 5 down below. So this is 8/25 L squared omega, and this one is only going to be 4/25. So yeah, we are this. Which one's going to drive? I guess this one's actually going to be the driving factor. And is that what we found? Not really, but this is two different things. This is the distance there and it's spinning the wrong way. So anyway, I apologize about even going down this route. It would be questions that I would want to do. But I think it goes back to this. It's like, hey, the center of mass, you know, it is moving. You know what I mean? The whole 5m is moving about the center of mass that way with this omega and then maybe this distance 2L. But the distance to that, if we're taking the angular momentum about the center of mass, there's no cross product because you can't take the distance to this velocity of the center of mass. So that's zero components. So it's only these components, and you know, we already said that those we found them was that 8.5 ma squared omega. Okay, so now I think the only other one, I think that's it. Or no, this one. Yeah, this will, and then I gotta go to bed. So the magnitude of the z component of the angular momentum is 55. So we're gonna try that one and maybe call it. But yeah, this will be cool because, you know, I gave it the best college try, and then once I do this one, hell yeah, I'm just going to look up this video 100 times on the internet because I'm fascinated about it, you know what I mean? I think I gave it my best, you know what I mean? And, you know, up to this point I haven't cheated. I just have some fundamentals that, you know, I need to look at some answers and do more of these to actually not make... Yeah, because that did not make sense. There was a lot of cool stuff that I've done in this video, but that was not one of them. Okay, so now what we need to do is the magnitude of the z component. Okay, so check this out. So you know, let's do this the simplest possible. You know, I mean, might as well finish with simplicity. So I'm going to draw a line there. And then we're going to do a perpendicular. So I need something that draws perpendicular lines. Whoa, oof, darn it! After all that work. Okay, so I'm gonna get kind of the two angular momentum vectors. One's gonna be to the left, and one's gonna be up. So from this spinning disk, I'm gonna get one going that direction. Well, what are they asking? Yeah, the z component. So see how this has a component in the z direction? And then we need to get our s. So we have alpha L is in our calculator of 0.979796. You know what I mean? And then alpha s is just 0.2. So these are the ratios. So if we get this vector in this direction, hey, we want to know the component of this vector in the z direction. Well, cool. It's just going to be 0.2. You know what I mean? That's where we're there. Now this one, when we get this one, this is going to be the center of mass. You know what I mean? The whole thing is going with an omega that way, omega, and then so it's r cross mv, and then this is going to be the total 5. You know, we're going to have 5m for the mass. Our distance is going to be to the center of mass. That's 1L and then 4/5 L. That's 9. So we're going to get 9/5 L. And then the velocity is going to be omega r, and so omega prime, and then our r is going to be that 9/5 again. So we're going to get 9/5 L again. Omega prime is going to be just omega times 1/5. You know what I mean? So that's the definition of omega prime. So look at that. We already just solved it in 2 seconds. And that's going to be this component. Now, if we wanted to know the component of that in the z direction, well, hell yeah, we'd have to get 90.979796, 98% of that. So whatever this is, 98% of it is what we're going to get. So even just right there, well, I don't know if right there is just like, well, you're not going to get a number that's nice. But you never know. Okay, and what else? And then so that's going to be the positive z component, but this is going to be the negative z component. So whatever this is, we have to subtract it. So again, this is the spinning let's see. Yeah, this component's that spinning this, so we already know it's like 8.5 ma squared omega. Cool. And then this one, you know, we kind of just did it. Hey, it's going to be 9/5, and then we're going to square that, and then we're going to have L squared, and then we're going to have 5m, and then we're going to have an omega, and then 1/5. Cool. And then we're going to multiply it by L, or 0.97. You get it, 979. Yeah, so we're going to have this. L is going to be square root of 24, so this just becomes 24. But we do get an a squared, and that's where we get a squared mw, and that's what this is, m a squared w. Cool, so this is it. This is going to be our positive one, and if we don't have to do the problem a million times, we have that, and then we're going to subtract 8.5, m a squared omega. Cool, so yeah, and this is 9/5 squared, so we got that, times 24, cool, times 5, divided by 5, so I guess we didn't have to do that, and then times this L, so alpha L. Whoa, times that. Cool, so we get 76.18 for that, minus 8.5, and minus 8.5. So we get 67.688, and it's just not 55. You know what I mean? So this is 67.68 ma squared omega. It's not 55. So no. This one was no. We did that one way a long time ago. This one was yes. And then and this one, yeah, we did within the video. You know what I mean? So hell yeah, we did them all. But yeah, I still am not rock solid on angular momentum. You know what I mean? And then I get where I'm running into a trap when I say, hey, if I'm fixing myself, I don't know, like fixing myself to the point, well, nothing is spinning about that point. Everything's just kind of going kind of linearly. You know, the center of mass is going that direction, but nothing's really spinning around this center of mass. I just don't know how to prove that, or if that's even a true statement. Yeah, but I think that's a true statement. Because if I have this, and then it's spinning this way, you know, just a mass like a golf ball on a string, it's not spinning. You know what I mean? It does not have any omega. So that's the same thing as this. If this is spinning with an omega, like the center of mass, it's not spinning around itself. I think that's a safe bet to say. But so that's my 2 cents. You know what I mean? So I think that's where we kind of ran into that trap. I think we explained it well. But I'm definitely going to, that's where I'm going to put my, there's a few places in this problem that I'm going to put my focus where I just didn't have the best understanding. So that does it. You know what I mean? This is JEE Advanced. This is paper number 2, 2016. People have wanted me to do it. And, you know, it doesn't show my brawn. That's for sure. Or maybe it does show the brawn, just not the brain. Anyway, so yeah, we did it. And, but yeah, I don't know. You know what I mean? Yeah, and this was going from really not knowing anything about angular momentum. You know, I mean, just all I know about angular momentum is just this little cross part, and I get it. It's leverage of mass and velocity. So yeah, so from this point, I get from that center of mass. That was the only place that I got that hiccup. Well, there is, you know, you're not getting a leverage of mass and velocity that way and then that way. I don't think you're everything's kind of moving that way. That's why you take the center of mass and say it is moving tangentially with this omega prime, and the whole mass, the whole 5m is there. So I think that is going to be the biggest hiccup for me. Like, hey, if I have a wheel, you know what I mean, the wheel is spinning, but then I actually put it on the ground, the wheel is still spinning, so you still have so that's where this comes up. Hey, if I'm taking the angular momentum about the center of mass, when the wheel is not touching the ground, same omega, angular momentum about the center of mass for this one is the same as this one. these are equal, even though that this one does have a velocity tangential of the center of mass. Cool, yeah, this is so good. So I'm glad I'm ending kind of on a higher note of explaining that. But then the thing is like, usually you want to come down here to point A, still not touching the ground, but this point A is touching the ground. So if we take the angular momentum about this, and then, well, the angular momentum about the center of mass was just 1/2 mr squared. Cool. Is equal to 1/2 mr squared, because the velocity tangential goes through the center of mass. There's no distance. So r cross mv. Cool. You have this whole mass and it's going that way. But if you're there's nothing to cross it into. I mean, there's no distance here. You know what I mean? Forget what angle. You know what I mean? The cross product is kind of like, hey, the angle part. You know what I mean? Like, hey, if I do have a distance, I'm going to cross it into the other one, and perpendicularness is what we're going for. We're going for what did I call it? Angular momentum, where you have, like mass times velocity. Leverage of mass times velocity. That's such a good term. Leverage of mass times velocity. Cool. But then if you come down to this point A, yeah, things get a little different, because right here your angular momentum is just the parallel axis theorem. You take 1/2 mr squared and then plus this distance, md squared. Well, d is just r again, so you're going to go plus mr squared. Cool. And now you're going to get 3/2 mr squared for this one. But this one you're going to get more because this one actually is moving on the ground. You're still going to get the same components with the spinning wheel in place. You're going to get that 3/2 mr squared, but now you're going to get an additional component of actually the whole mass. That's going to be m. Well, the distance to the mass and its velocity. So you're going to have a distance r. We don't have to put that r right there, but and then mass and then velocity, and velocity is just omega r. So you're going to get the distance to the whole mass times the velocity is omega r, and this is just m r squared omega. So you get another mr squared omega, and then you get 5 squared mr. And I hope I'm right on this. You know what I mean? I just watched a video on it yesterday, and so hopefully my understanding of that. But that's pretty cool, because that's part of this problem. It's like, hey, what's the angular momentum about the center of mass? Well, you know what I mean? Like the whole system is going that way, so you can't. So yeah, I'm bummed that I can't. Like that's one scenario where I can't break up my little circle into 3 little point masses, and so I'll have to revisit that. But as long yeah, I don't know. Yeah, I'll have to revisit that. Cool. All right, and that's it. So thanks for joining me. And guess what? That's a video.